натисне? Аз не го знам неговия, той на какво е. Как да му обясна сега това? Окей, sorry.
So, I don't know what to do.
No problem, we wait, Vesselin Drensky is here. Vesko,
Okay.
help us because the professor Bokult can't share your screen.
Okay.
И така,
Maybe
смотрите.
try to explain him because
Значит,
they understand.
откройте вашу презентацию сначала.
Ну, yes, I open. Веселин, я вот вижу себя вижу. А где
Дело
вы?
в том, что откройте свою презентацию.
А как ее открыть?
Ну, я послал ее вам.
Нет, я открыл ее, у себя я открыл.
Она видится или не видится на экране?
Ну, а как я вам перешлю?
Ничего не надо пересылать, просто откройте ее на экране.
Ну, вот у меня на экране, как
Значит,
я...
сейчас внизу на экране у вас есть, там, где конференции, есть зеленый квадратик, где написано Share Screen. Или поделить экран, или там... Видите стрелочку?
Квадратик. Ну вот я на него нажимаю.
Нажмите, и получается ваш экран.
Ну, у меня не получился. Ну, вот я его нажимаю.
Ну, когда нажимаете, напишите Share Screen.
Да тут ничего не написано. Понимаете, тут ничего не написано. Вообще непонятно. Представляете, вот шерится. А вот сейчас.
Если видите вашу презентацию на экране,
да.
На квадратике, который появляется, когда нажимаете зеленый квадратик, Share Screen, появляются прямоугольники, там появляются какие-то картинки.
Нет, вы знаете, что-то... Сейчас, подождите, я...
На мониторе есть Share Screen внизу? Или открыть там или что-то такое?
Так. Ну вот.
Here is microphone, after that camera, after that participants, chat, and after that share screen.
Нет, я что-то ничего не понимаю.
Ну, в принципе, откройте страницу конференции, она у вас открыта, и вы видите себя, видите и меня тоже, и Майю. Внизу есть Share Screen, такой зеленый квадратик.
Понимаете, у меня своя... Я не вижу вообще этой доски. Внизу обычно я вижу эти доски. Сейчас, подождите, еще раз. Я еще раз зайду. Может быть, как проще зайти к вам? Вот проблема. Наверное, я не...
Excuse me, професор Бог. Да не видя му на цял екран, това и то да не ни вижда нас и да не вижда бутона отдолу, който е.
Значит, такой вопрос. У вас презентация на полном экране или на частичном?
Сейчас я еще раз, знаете, что я еще раз войду.
Хорошо.
Да, вообще, вы знаете, это... Так, значит, Дренский. Так. Вот, International Conference. Вот. Это самое первое ваше, это. И вот здесь я нажимаю.
Ну, вы сначала должны выйти из
Я
конференции, чтобы
нажимаю,
нажимать второй
значит,
раз.
очень длинный адрес. Вы мне давали короткий адрес, но вот я нажимаю длинный адрес.
Хорошо, нажимайте длинней.
Так, теперь открыть приложение Zoom. Нажимаю.
Да.
Вот. Ну вот, значит, я вас вижу. А, вот сейчас лучше, да. Вот здесь получилось.
Окей.
А, но я свою еще не открыл. Я сейчас свою открою.
Откройте презентацию
Yes.
Да. Сейчас.
и нажмите Share Screen.
Сейчас я открою презентацию. Так, сейчас я открою презентацию. А, вот сейчас презентацию надо открыть. Так, сейчас. Так, сейчас ваш сегодняшний. Так, вот, я его открыл.
Сейчас
Okay, now share screen.
на странице, где конференции, внизу есть, вы видите много образов, много квадратиков, некоторые с фотографиями, некоторые без. И внизу есть Share Screen. Зеленый прямоугольник.
Сейчас. Значит, теперь мне надо вернуться надо. Я вот сейчас не вижу экран. Вот, значит, как мне вернуться? Значит, сверху у меня 3 кнопки, 3 точки. Может, 3 точки нажать?
Не знаю.
There is to share screen here.
Сверху у меня 3 точки.
А внизу есть такое меню.
Нет, так вот оно еще не выскакивает.
Try with.
Ну, вы знаете, если не получается.
Ну вот.
Леонид Аркадьевич, здравствуйте, это Миша. Смотрите, внизу у вас должна быть кнопочка Zoom.
Понимаете, ну у меня была кнопка. Вот я сейчас вижу презентацию, и я где-то открыл. Слева у меня открыл.
Escape in full screen, and after that you see.
Нет, по-русски говорить.
Если будете на этом, значит, если на странице презентации, нажмите Escape. И она получится меньше.
Escape. Это на что надо нажать?
На клавиатуре. На клавиатуре Escape. Слева сверху.
Ну, вы знаете, Леонид Аркадьевич, я открою вашу презентацию, и вы будете говорить, я буду показывать.
Конечно, я буду вам читать. Откройте, и я буду читать, и все.
Сейчас ждите, тогда я сделаю это.
Ну, конечно, да, что вы меня
Майя, на USB?
Yes. Тодор, дай. Да. Yes, you have.
О, мы уже 4 минуты прошло.
No problem. We wait you.
Майя, мне ще права, ако не си ми дала.
Дали сме ви права, трябва да можете да се споделите. По-хосте.
Share трябва да напиша.
Yes. Okay. Maybe Control L. Yes, Control L. To full screen.
Сега ще го направим Control L.
Так, ну что? Я себя не вижу. А вы меня видите?
Yes,
мы видим,
we
да.
see you. No problem.
Ну все, и у меня, я могу начинать?
Да, начинайте.
Так.
Ага, окей.
A minute, please. Окей, готов си, Веско, нали?
Да, готов съм.
Okay. Morning to everyone. Let's start the morning session in this conference. The first talk is presented by Leonid Arkadievich Bokhut, and the title is Unpublished Results of Anatoly Illarionovich Shishov. Please, Professor Bokhut.
Thank you. So, unpublished results of Professor Shishov. So this is a picture of Shishov. So I begin with Maltsev's letter to Soviet Academy of Sciences with recommendation to Shishov be a member of our academy. So he mentioned in this paper, in this letter, he mentioned his results in Lie algebras and special journal algebras. And he mentioned two famous foreign mathematicians who connected with Shishov paper very close, Jacobson and Witt. So it is a very good, very successful letter. In 1964, he was a member of Russian Academy. Shishov was a member of Russian Academy of Sciences. So I will speak about his PhD thesis, Moscow 1953. It is have
recording in progress.
Yes, it have two parts. First part, supposed to be very most important. He proved that any subalgebra was freely algebra is free. This is now called Shishov-Witt theory. And in the proof, he used whole basis. It was published in 1950. And in Moscow, it was 1991. So 2 years before this PhD was in, yes. So, and also he used Lazar-Shishov elimination. Of course, Lazar did it 7 years later, but because of Bourbaki, they know this result, they didn't know Shishov result. So this is now Lazar-Shishov elimination. And the next part, second part, it is most, speaking about pages, this is most big part of the thesis. And the problem is that no one of this result from the second part is published in some sense, because the main result of the second part was published after 10 years. And when he submitted this in Siberian Mathematical Journal, he told me, "You push me to publish this paper." That's very strange. Because I was waiting 4 years to publish my result. I will talk this result later. And other result of the second part, not published until now. So this is very strange situation. So, so what about second part? Oh, sorry. Sorry. So the most important part of this second part, this is so-called whole Shirshov series of wages, but this is in some sense abstract wages, just some idea, and this idea you may succeed to find linear basis of real algebra, or you may not succeed. So this series now has only 4 concrete linear bases. This is whole basis. Yes, whole basis. And so no. This is not so. Yes, whole basis. Very small whole basis. Whole Shirshov. Yes, whole Shirshov basis. Yes, this. Don't be quick. And so one is whole basis, 90-50. Another 2 was in this dissertation, and he didn't publish this 2, but later some people, of course, joined. They found Linden-Shirshov basis, and Shirshov did it in 58. So now from 58, there is another one. So this is 3. This is 3. So one is 2 here, Linden-Shirshov basis, and another basis in the thesis. But only now only known whole basis and these 2. And another one I found in 1959. Oh, sorry. Yes, 59, and published only 63, because Shirshov published his result about whole Shirshov basis. So now only 4 bases in this series. And it is called whole series, but actually this is whole Shirshov series. Okay. So next. Yes. My basis. This is polynilpotent basis. So this is depends of order of monomials, non-associative monomials. And so whole basis, this is at the beginning we fix deck order, length order of monomials, non-associative words. And then scheme of whole basis. So already in 1953, Shirshov probably knew Linden-Shirshov basis 58 and Linden basis 1954. Okay, next. I will read. Okay, do it. The papers of Shirshov, freely algebras. In this paper, it was necessary to use non-commutative. No, before. What is what is, yes. Okay, so I will read.
No, next.
Yes, no, not yes. No. Yes, this one.
Okay. Sorry.
Discovery of the abstract series of bases in a free algebra of a field or commutative algebra. This is included in the PhD thesis and is published in Chershov Algebra and Logic 1962. Each specific basis of this whole Chershov series is based on some partial ordering of non-associative monomials on the generators. The result covers the whole basis 9050 based on Deklerk's ordering of the monomial from this thesis. And this is whole basis. It covers also the Chershov basis from his PhD thesis based on complex ordering of monomials in terms of their commutative basis. So example, the commutative content of the monomial A2, A3, A1, A3, so it must be, okay, this one is A3, A3, A2, A1. So this is commutative word. This is monomial, but without without this paraphrases. This Chershov basis of complex, I call it complex order of monomials, has not yet been published. Okay, next. Chershov used this new basis to prove a sufficient condition for the validity of the Poincaré-Birkhoff theorem of a Lie algebra of a commutative algebra, dissertation. The proof is not published, as I told you. The statement of this sufficient condition is given in the paper Chershov representation of Lie rings in associative rings, 1953. So the statement, it was published in 1953, and this very good paper, 1953, representation of Lie rings and associative rings. This is generalization of Poincaré-Birkhoff theorem for some Lie rings, not of a field, but of a commutative ring. So it was the first result, and he didn't include this paper in the dissertation. That's a very strange. It is connected to the published. Okay. So later I will explain all of this very strange psychological problem. Okay. So an example of a Chershov Lie algebra of a commutative algebra that cannot be embedded into an associative algebra is given. This work quickly received a response abroad. In 1958, the work of Pierre Cartier, Paris, appeared with a citation and a further continuation of the work of Chershov with another example. More examples of such Lie algebras were proposed by Paul Kohn in 1963. The examples of Chershov and Cartier were over commutative algebras over the field of two elements. Cohn's examples were over all fields for any P, finite field of P element, P prime. So far, there is no example of a commutative algebra of characteristic 0. Okay, next. It is important to note that the non-complex order, another order of monomials in terms of the non-commutative basis, is also suitable for the whole Chershov series. An example is the non-commutative content of the monomial A2, A3, A1, A3 is the associative word A2, A3, A1, A3. In this case, we get the Linden-Chershov basis, and with it, omitting brackets, the Linden associative words. Next. Without a doubt, Chershov investigated this order as well, and he was sure that it is also suitable for his abstract basis. The proof is the same as in the complex order case. It is a rare piece of luck to find an order which gives rise to a new abstract basis, and Chershov could not miss one more specific basis of his scheme. Even now, only 4 particular, okay, next. No, sorry. No.
Yeah.
No. Ah, well, yeah, here. Oh, no, before. Yes. This is beginning. No, next, later. No. Father. This is beginning. Next one. Vesselin.
I think that's here. Vesselin, unmute your microphone, you'll not hear you.
Without doubt, Chershov investigate.
Okay.
Yes. Next one.
The next one was this one, and you already had this.
This one. Even now, only 4 particular bases of Freely algebra from the series of abstract bases are known. In addition to those mentioned above, we shall mention a basis corresponding to the polynilpotent order of monomials. This is my paper, a basis for free polynilpotent algebras, Algebra and Logic 1963. The initial pieces of the basis give a basis of the free polynilpotent algebras Lx over polynilpotent ideal. In particular, for Ni is equal to, we obtain a basis of free solvable. So already in 1953, Chershov probably knew the Linden-Chershov basis 1958 and the Linden words 1954. Okay, next one. So this is another paper, was application of those results that I mentioned before. From the second part. The paper of Chershov on Freely algebra, 1958. In this paper, it was necessary to use non-complex basis to prove the theorem on the embedding of countably generated Lie algebra of a field into 2 generated 1. Chershov could not use his abstract basis theorem because it was not published. As a result, he used a new definition of the Linden-Chershov basis in terms of the scheme of whole, but starting from his knowledge of regular boards, the Linden boards. But we know that he knew Linden boards in the 1953. This paper of 1958 became another milestone work. Here's a list of discovery in the paper. The discovery of the factorization property of regular boards, the same as Linden boards. So any board is a product increasing series of Linden-Chershov boards. Using this property, Chershov defined a special arrangement of the parentheses on a regular board with a fixed regular subboard. This property was cited in the work of Schutzenberger 93 with a reference to the work of Chershov and by mistake with citation of the work of Chen Fox Linden, 58, please. See Linden board, Wikipedia, Melanson. So this is all of this history. At last, it was formulated factorization theorem explained Chershov, not Linden. In Linden, there is no this formulation. Yes, and another important result. He discovered Gauss elimination of leading board in the Lie polynomial f with the help of another polynomial g. If g is supposed to be defined relation g is equal to 0, and the leading monomial of g in some sense is a submonoid of leading monoid of f, in some sense, it means without brackets. With brackets is not subboard. But if you miss brackets, associative case, it is subboard. But still, if it's g is equal to 0, so this f, leading monomial of f, is not 0. But his linear combination of Linden-Chershov boards that is less than leading maximum monomial of this f. So this is Gauss elimination, very easy for commutative algebras, freely algebras, associative algebras, but very tricky for Lie algebras. Because to be subboard, it means associative case. You forget about brackets and how to use this g is equal to 0. That's a problem. Okay. So next one. So he found the next one. Yes. And at last, it was his second part of his thesis. He used it for the theory of Grobner-Chershov bases. This is now the most popular and most important part of Chershov results. Because, you know, Grobner bases, this is great subject. And Grobner-Chershov bases for non-associative, non-commutative algebras and universal algebras. This is, of course, they call it Grobner basis, but it is really Grobner-Chershov basis because Chershov did it. All the other, together the systematic use of inclusion of freely algebra Lie-X of a field K into the free associative algebra Kx served as the beginning of discovery in the theory of Grobner-Chershov basis for Lie algebras and associative algebras in the work Chershov, Siberian Mathematical Journal 62. it remained for Chershov only to add the definition of the operation of composition of two associative polynomials as polynomial in the theory of Bulgarian. Then Chershov discovered the composition for Lie polynomial with a special arrangement of a parentheses pieces in the associative compositions. Okay, so this is almost after all of this paper, it was very easy for him to find Grobner-Chershov basis theory for associative and Lie algebras. Thank you. So sorry, I am so sorry.
No problem. Thank you. So
By the way, Vesselin, we want to publish the second part, and we discussed this on conference Chershov 100. Rowan want to support, and all of this. And if we will have some idea how to publish it, maybe in Bulgaria, second part of his thesis. And you know, everyone may read this. I sent to Vesselin this source of PhD degree of Chershov, and we may see, and maybe you will also have some idea how to publish it.
Okay, thank you.
Okay.
Questions, remark?
Yeah, this is the link of the thesis of Chershov.
Okay.
Yes, at the very beginning, yes. In the
Yes,
title,
yes.
under the title, there is a, yes, there is a, this link.
Okay.
Okay, but there is no time for the next presentation. Please.
Sorry.
Thank you again, the speaker. Okay.
Okay.
The next talk is by Hristo Iliev. Please share your screen, Hristo. Okay. Maybe Ctrl-L to full screen.
Yes, I'm here at the Institute of Mathematics. I'm just getting the computer right now. Todor was here before me, I know.
Okay. Okay, the next talk is titled Regular and Sub-abundant Components of the Hilbert Scheme of the Smooth Projective Curves, and presented by Hristo Iliev. Please.
Thank you. I'd like to thank the organizers for including me into this nice event. And although that my talk is not exactly on combinatorial ring theory, I do not feel strange to this conference because I have known most of the participants or got to know them during the last 15 years. And as for the other people, Academician Drensky has played an important part in my career as well, because he was chair of the department at the Institute of Mathematics when I joined here in 2006, when I returned to Bulgaria. And yes, okay. So my talk will be algebraic curves, and in algebraic geometry, by algebraic curve we usually mean a smooth, reduced, irreducible, complex projective algebraic scheme of dimension 1 and genus G. And here I focus on curves that are embedded in PR of genus G and have degree D. So such curves are in fact represented by a functor which works on the category of schemes over C and assigns to each such scheme S a family of schemes parameterized by S, so that the fibers of the family over S have all Hilbert polynomials of this form here, dt plus 1 minus g, where d and g are these invariants that we have fixed here. Now, this object, HDGR, is known as the Hilbert scheme of projective algebraic curves at genus G and degree D. But since this introduction may be not so illuminating, I would like to go into probably a bit more comprehensive view on this object. So, for this, consider a projective algebraic variety X in PR, or in other words, the common zero locus of some set of homogeneous polynomials from the ring in R plus 1 variables, polynomial ring of R plus 1 variables of C, which are denoted by S. Then we have the ideal of X, which by definition consists of all polynomials in S that vanish at all points of X. We have further the coordinate ring of X to be just the quotient of S by the ideal of X, and it has a natural gradient that is induced by the gradient of S. And we denote this coordinate ring by gamma X, and the corresponding graded pieces are just gamma XN. Then we know the notion of a Hilbert function of X to be the function that returns the dimension of the n-graded piece of the coordinate ring gamma X for any n that we can consider here. And further, there is this polynomial that we call Hilbert polynomial of X, which is a polynomial with integer coefficients such that its values coincide with the values of the Hilbert function of X for the large values of the argument. Now, what we have is that the degree of this polynomial is exactly equal to the dimension of the variety X. Its leading coefficient is equal to the degree of X divided by the factorial of the dimension of X. And in particular, if the dimension of X is equal to 1, then this Hilbert polynomial of X is simply a linear polynomial of this form. So what we have here in this form, namely t the argument, and then the polynomial is dt plus 1 minus g, are these two invariants d and g. So this d is in fact the degree of the variety, and this number that we have seen here, g, is known as arithmetic genus of the variety. And now, as our objective is to discuss parameterization of all curves in PR that share such invariants like G and D, this is in fact something that amounts to identifying an object, ideally algebraic variety, which I can say ds, so that the points of it are in bijection with all such curves. We want such a correspondence to be natural in some sense, and what I mean by this is that if we vary the points in H, then we would like to have that the coefficients of the polynomials that determine this X vary continuously as well. And what is such an object like? So that's what I'm going to say briefly about before I move to the geometry of this object, HDGR, that I introduced at the beginning. I want to mention that if we fix a polynomial P of t equal linear polynomial like before, t plus 1 minus g, then there exists a number, positive integer number, for which any variety x that has this polynomial has Hilbert function which coincides with this polynomial for all values of t that are greater or equal than n. And also the ideal of Ix, or what we have here on the left side this truncation that I have here on the left side is in fact generated in degree n. Or if we look at this geometrically, that would mean that the zero locus of this n-graded piece that I have here on the right, in fact, gives exactly x. And this number n that we have here in this claim is known as a regularity number, and it depends only on the polynomial that we started with, that is PFT. And of course, this statement is valid not only for curves, but it's valid in general. So there is such a thing. And further, let's fix such a polynomial, linear polynomial, linear form, PFT dt plus 1 minus g, and let's choose a regularity number n. Let's denote by n of t the dimension of the vector space st minus 1 here, and let's take q of t to be the codimension of the vector space ix t inside the vector space st. Now there is such a map, or at least set theoretic map, that can assign to any such variety x with Hilbert polynomial p the projectivization of the t-graded piece of the ideal of x. Or in other words, this is a subspace in the projective space of dimension n of t. Or in other words, what we get in this way is some map from the varieties x with such a polynomial to this Grassmannian that we have here. This map is called Hilbert map, and for each point x, that is to say variety with this Hilbert polynomial, the image psi of x in the Grassmannian is called Hilbert point. And the entire image of the map psi is known also as the Hilbert variety. And now this object that was probably not so illuminating in the beginning is just the closure of this image that I have here of psi. And before I go further, I would like to say only mention that this image in fact can be identified as quasi-projective algebraic variety by asking for ranks of some linear maps to be equal to some specific number. I'm not going to specify this, and I'm not going to talk about this. The important trick is that we get this object, HDGR, and that's what we want, in fact, to investigate further, but somehow the problem is that this object is very big. It is huge, in fact. So this object, a priori, can have components of many different types, from which I'm going to identify 3 kinds of components. So I have divided them here in this way, so that they should be finitely many indeed, but they can be very many and very weird. But nonetheless, we can identify 3 principal types of them. So first are the so-called regular components. And these are components that are characterized by being generically smooth and having the so-called expected or minimal dimension. This condition, in fact, can be rewritten like the first cohomology of the normal bundle of a curve represented by a point of such a component in PR being equal to 0. And then further we have those S components here that are known as superabundant components. And these are components that are generically smooth, but of dimension which is bigger than the minimum possible dimension denoted here by lambda, or these are components that are non-reduced. So both of these conditions can in fact again be written in terms of cohomologies of the normal bundle at the curve that corresponds to a point of such a component. And the condition is this one that you see here, that the dimension of global sections of the normal bundle is bigger than the number lambda. And finally, here we have the P components that are just topological components. They're also interesting, but they're very difficult to tackle because of their structure. So these are components that have no points, in fact, corresponding to smooth integral curves. And for this reason, our focus is on the first two types of components, the regular components and the superabundant components, which union are denoted here by IDGR. So I want to mention only that all of those components should have that a general point of them corresponds to a curve that is integral and smooth. That is, it is reduced and irreducible and smooth, of course. For this object that I'll call like a scheme IDGR, there is a map to the modular space of curves of genus G, a rational map. And when this number that you see here, denoted like rho DGR, is non-negative, then it possesses the so-called distinguished component that I denote here by I naught. So this distinguished component is regular, and it also has the property that it projects densely into the modular space of curves. That is, its closure, in fact, in the modular space of curves is the entire MG. And now to the motivation of this study and other studies on this subject. I can say that perhaps one of the principal reasons for studying this subject, or stimulus at least, has been that about 100 years ago, Francesco Severi formulated a statement that sounds as this: if this number D is greater or equal than G plus R, then the only component of IDGR is in fact the distinguished component. He said this statement in somewhat different terms, but that's how it sounds after the introduction of schemes in the 60s. In regards to this claim made by Severi, there have been some work since the mid-80s when I improved Severi's claim for R equal to 3 and R equal to 4 and gave examples that it is incorrect when R is greater or equal than 6. And then some results by Mazzetti and Sechiero and Keen gave additional examples for the reducibility of IDGR. That is, they showed that there exists some additional components to the distinguished component I naught. And further on, one of my co-authors, Sonja Kim, produced some results about the reducibility and reducibility of IDGR, which are formulated here. And after reading some of those papers, actually all of those papers, I figured out that if we fix G and R and track the number of components that IDGR can possibly have, it appears as if we get more and more components as D decreases. I have summarized, in fact, the picture here on this slide. So there are first the results about the reducibility produced by Harris when probably the attention to this subject was restored in the early 80s. Then the results of Ein, which kind of improved the irreducibility range of IDGR. Then the result of Sonja Kim fits into this picture. And then there are some numbers that I have denoted here, like eta 3, eta 4, and some more that should appear here on this axis, which mark some ranges when we observe more and more components, in fact, to appear of this scheme, IDGR. And after studying actually after discussing with Sonja and Yongguk Choi in like 7 or 8 years ago, we came to formulating several questions that are of interest to us. So, first one of them is indeed, can we characterize these additional components of the scheme IDGR as we trace the degrees of D from those numbers that I have marked here? Then, since all the components, additional components of IDGR that were constructed involved, in fact, families of curves that were at least triple gatherings of rational curves, we asked if it's possible to find additional components that, in fact, represent curves that are multiple gatherings of irrational curves, and in particular, if we can find double gatherers of such. And finally, which was, in fact, of principal interest to me for at least 10 years, the question whether there exist additional regular components in the Bulgarian case, or that's the case when rho DGR is in fact non-negative. Then we answered, in fact, to all of those questions in one way or another. So the first result was on this topic that we got together with Choi and Kim was about existence of components that parameterize double covers, and that result stimulated, in fact, our work to look further into the geometry of this scheme. And then we found, in fact, this theorem. We proved this theorem that I'll explain briefly. So, if we fix D to be equal to this number 2G minus 4 gamma plus 2, and if we restrict our attention to R, that is between the maximum of gamma and 2G minus 1 divided by gamma, and capital R, which we have taken to be G minus 3 gamma plus 2, then the scheme IDGR acquires some generically smooth components that we denote like DDGR, as in fact the same component that we have in this theorem, which is of this dimension that we have right here, and the curves in this component, they in fact arise in a completely geometric way. That is, we reconstructed those curves geometrically as curves on cones. So we, in fact, looked at curves in PR minus 1 with the degree that is G minus 2 gamma plus 1 and G minus gamma embedded in PR minus 1. And those curves, in fact, form a unique component. In fact, the Hilbert scheme with that invariance is irreducible, and it has some nice properties. The component has some nice properties. Then we looked at a cone, in fact, over such a curve, and we took the intersection of the cone with hypersurface of degree 2. And then those curves that I have here on this picture in blue, in fact, represent the curves from the component that I described here. This, in fact, allowed the reconstruction of the component given here in this theorem in a completely geometric way, but more importantly, it allowed the computation of the tangent phase to such a family, which in turn gave the result about the generic smoothness of the component. What's the implication of this result? So that's what I'm going to say next. First of all, if we have that G and gamma are chosen in such a way that gamma divides 2G minus 1 and R is equal to 2G minus 1 divided by gamma, then this component I get here, DDGR, is in fact a regular component that is different from the distinguished one, which is the first result on the subject. about existence of two regular components at the same time. And one can check, for example, that when gamma is equal to 9, G is 46, and D is 58, then I 58, 46, 10 has two regular components. One of them is the distinguished component, and another one is the component from the theorem. And the second corollary is in fact something related to the original formulation of the Severi's claim of Severi's conjecture. Many people believed that what Severi really meant was that IDGR can have only one component parameterizing linear normal curves. But in fact, for specific values of G, gamma, D, and R, we obtained, in fact, two such components. So one is the component that we constructed in the theorem, and another one is a component constructed earlier by Mazzetti and Sehiero, which, in fact, corollary kind of provide the counterexample to Severi's claim in any possible sense. And I think that I probably should stop here because it's 10:25. And at the end, I would like to thank to the audience who listened to my talk, and also to the organizers of this event, in particularly Ivan Chipchakov, Applied Pushkov, and Elisa Hristova, who did a tremendous job in the organization of this event. And also Vesselin Drensky, who has been indeed the main reason for us coming together here. Thank you. Okay, I guess there are no questions, so thank you again.
Okay, sorry. The next talk is starts in 10:30.
Good morning. Can you hear me?
Yeah, you hear you. Please share your screen.
Yeah, good morning. Yeah, I'm trying to.
Morning. To be ready.
Can you see it?
Yes. Maybe Control L, full screen.
Control L.
L.
Oh, it doesn't work. Let me try something else.
You have to open in Acrobat Reader.
Yeah, I did actually. Can you see that now?
Yes. Everything is okay.
Good.
Okay. Let's wait a minute and start after that.
Yeah, no problem.
Okay. The next talk is entitled Quotient Groups of IA Automorphism of Free Metabelian Groups and present by Athanasios Papistas. Please.
Thank you very much. First of all, I wish to thank the organizers for the invitation to participate to this conference dedicated to the 17th anniversary of Vesselin. Happy anniversary, Vesselin, all the best. I would like to talk on quotient groups of automorphism of free metabelian groups of finite rank. It is a joint work with Kostas Kofinas. Let me start with some preliminaries. Well, G is a group for a subgroup X and Y of G. We write square X, Y square for the subgroup of G generated by all commutators X, Y. X belongs to X and Y belongs to Y. For positive integer C, let gamma CG be the C-th term of the lower central series of G. Just to point out that gamma 2G means G dash, which is the derived group, and G double dash is the derived of derived group. By odd G, we mean we denote the automorphic group of G. For C at least 2, the natural epimorphism from G onto G over gamma CG induces a group homomorphism, say P or pi. From automorphic group of G into automorphism group of G over gamma CG. Let's write ICAG for the kernel of this epimorphism. Note that for C equals 2, we write I2AG for the IA automorphism groups, for the IA automorphism of G. And as inductive argument on C, we get gamma CIA of G is contained in IC plus 1 AG. And And for C at least 2, we write this calligraphical CIAG to be this quotient group. I'm going to use this one, this notation quite enough in this talk. In general, it is a very difficult problem to determine whether or not gamma CIG, the C-th term of the lower central series of IAG, is equal to IC plus 1 AG for all C, at least 2. Moreover, it is quite difficult to study the structure of the quotient group, gamma C over gamma C plus 1 of IAG. For positive integer n, at least 2, we write Fn to be a free group of rank n with a free generating set F1 up to Fn, and Gn a free non-abelian polynilpotent group of rank n. Some properties of this group is a residual nilpotent, and the second property is each quotient group is a free abelian group of finite rank. That's the result of Smelkin. The previous result was by Kuhnenberg. Now for C at least 2, we write G sub n comma C to be a Gn over gamma CGn. The natural group epimorphism from this group to another Gn comma C induces a group homomorphism psi or psi from automorphic group of Gn n comma C plus 1 to automorphic group of Cn comma C. It is well known that this map is on 2. Define A C plus 1 Gn to be the kernel of the above map, and A star C plus 1 is the intersection of image of P and the kernel of Psi. Just an observation, in fact, is the following result, that AC plus 1 of Gn is isomorphic to this group as 3 abelian groups, to the direct sum of these n copies of GRC Gn. And A star C plus 1 Gn is isomorphic to L calligraphic C INCN as 3 abelian groups. For any now subgroup H of IA automorphism Gn and the positive integer C, let H R to be the intersection of R with all these subgroups I, R, A, Gn. For any Q, let you note L calligraphic L1QH to be this group, this quotient group. And when Q is at least 2, L calligraphic Q2, H is the other one. I'm going to mention quite often these two quotients in this talk. Now, the natural epimorphism from Fn onto Gn induces a group homomorphism rho n from automorphism group of Fn into automorphism group of Gn. We write Tng for the image of this homomorphism. The elements of T are called tame automorphism of Gn. That means are reduced from the automorphism of Fn. Further, we write Hn to be the intersection of Tn with the IA automorphism of Gn. And for any positive integer R, at least 2, we write Hn R to be the intersection of Tn with the others IA automorphisms. Since now Gn over Gn dash is isomorphic to Fn over Fn dash, rho n induces a homomorphism, say rho dash, from IA automorphism of n into IA automorphism of Gn. I'm going to mention these two results, lemma 1.2 and theorem 1.1. Since these two results I'm going to use in the case where n equals 3. Just mentioning the theorem 1.1, for a positive integer n, Gn is a free non-abelian polynilpotent group of rank n. Then for all n and R, we have these two groups are equal. Well, before we state the main result, which I like to talk in, just some history on Fn. For G equals Fn, the problem I mentioned in the first page is known as the Andreadakis conjecture. It has been proved in Andreadakis that gamma CIAF2 is equal to IC plus 1 AF2 for all C at least 2. And that the first 3 terms of this series coincide in the case n equals 3. For n at least 2, gamma 2 IAFN is equal to I3FN. That's result can be found, for example, in Petet 2005. When n is at least 3, Petet showed that gamma 3 IFN has finite index in I4 AFN, and Sadov 2019 proved that these two are, in fact are equal. The Andreadakis conjecture is not true in general. It is shown in Baholti that gamma 4 IAF3 is not equal to I5AF3. Similar thing is for gamma 5 and I6. This is for, in fact, for n equals 3. He did this by using the computer. For n at least 4, the conjecture is still open. In 2017, Darnay proved that the stable Andreadakis conjecture is true. Namely, the natural map for this quotient group to another one, induced from the inclusion. Inclusion is surjective for sufficient large n. That's very, very short history on Fn. Now we move to the statement of the main result which I like to talk. First of all, by Mn, we write for the free meta-abelian group of rank n with this set of this set as a free generating set. The natural group of epimorphism from Fn onto Mn induce a group homomorphism alpha n from odd Fn into odd Mn, and let's write Tn for the image of this homomorphism. In a series of papers, Andreadakis, Bachmann, Suzuki, Chain, Romankov, it has been shown that alpha n, when n is different from 3, is on 2, and alpha 3 is not. Now we define this set, calligraphic M n, C, this set, which is Z basis of the quotient group gamma C over gamma C plus 1. And the rank of this quotient is this number. So the rank of this group is n times C minus 1, n plus C minus 2 out n minus 2. It follows by a result of Andreadakis, also Backmuth, that the rank of A star 3 is n times n out 2. Also by a result of Backmuth, we have the rank of A star C plus 1 with C at least 3 is this number. Now the result which I like to talk is the following. We have Mn is a free meta-abelian group of finite rank n. Then we have 1 that says that Andreadakis conjecture is in fact true, is valid for n equals 2. The second part is Andreadakis conjecture is not true for meta-abelian group, free meta-abelian group for n equals 3. And the third part is that stable Andreadakis conjecture is true, is valid for n at least 4. Well, let's proceed to give a brief proof of that result. The case n equals 2, this is in fact easy. It's coming for a result of Andreadakis and Backmuth, combining these two results. For n equals 3, we write H3, this intersection, who is equal by lemma 1.2 as mentioned before, with this row dash 3 of IA automorphism of F3, and H3 comma R, the intersection of these two groups. It can be deduced from the result of Orin chain that L calligraphic 4, 2, H3 is different from L calligraphic 4, which is, by the way, that is isomorphic to A star 5. By a result of Andriadakis, we can prove gamma 3 H3 is equal to this group rho dash 3I4 F3. But gamma 3H3 is equal to this one, this group. And so these two quotient groups are equal. Now, by theorem 1.1, I mentioned before, by setting Gn to be Mn, we have L calligraphic 3, 1, H3 is equal to this quotient group by the above relation. And since these two are not equal, we have these quotient groups are different. That means gamma 3 IAM3 is different from I4A. Okay, let's move to the case at least 4. For group G, we write ZG for the integral grouping of G. For elements X and Y of group G, we write y up to x for the conjugate x minus 1 yx. Since Mn dash is abelian, it may be regarded as right z Mn over Mn dash module in the usual way. If we write An to be the Fn over Fn dash for the free abelian group of rank n, and alpha I equals Fi Fn dash, this set of alpha 1 up to alpha n is a free generating set of An. The natural epimorphism P from Mn onto An induces an isomorphism from this quotient group to An. So we may regard Mn dash as right as Z An module. For W belongs to Mn dash and S belongs to ZAN, we write W up to S to denote the image of W under the action of S. Set of generators of N dash is given by these elements. Since Mn dash is abelian, any elements of N dash may be written in this form. Now, the natural epimorphism from Mn onto Mn over Mn dash induces a group homomorphism sigma tilde from this automorphism group to GL and Z. Since the natural homomorphism from mod Fn into GL and Z is surjective, and these two groups are isomorphic, this map sigma tilde is surjective, and the kernel of this is equal to IA automorphism of Mn. We define an action of G and Z on this quotient group by this form, G star, phi bar, and so on. The above action is a left action of G and Z on L calligraphic C IAMN. The action of G and Z commutes with the multiplication of the elements S, so this group is Z, G, and Z module. Just to point out that this group is G, GL, and Z submodule of this quotient. Now, write GR1QMN to be the tangent product of Q over Z of GR1MN. Identify this automorphism group with GL and Q with respect to this basis. The group GL and Q acts naturally on this vector space by this. Let's write GRCQMN to the Moventation product of Q with GRCMN over Z. Since GRCMN is a free Z module with free generating sets, as I mentioned before, we may regard this GRCMN inside GRCQMN. The action of GLNQ on GR on Q can be extended diagonally to this one, to this vector space, subject to this relation. Each GRCQMN is a Q GLNQ module. The group now GLNQ acts on this direct sum by this way. Here G bar UI means the canonical action of G on GRCQMN and the multiplication of 1 by n and n by n matrix. Each such QRCQ is a QGLNQ module. Next, we can connect the IA automorphism with this group using this chi-C map, sending phi to this n cubed, where phi is n element of ICAMN. This map is a group homomorphism. The kernel is IAC plus 1 AMN. This group is isomorphic to a subgroup and preserves the action. Now I have to move very fast. We define three QGLNQ modules. The first one is the PC, with the QGLNQ module generated by this set. The QC, which is this some module generated by this set, or actually is created by inner automorphisms, and another one, RC. Having defined these three modules, and using the result of Bulgarian Drensky, we have this module actually is the direct sum of these three. These three modules are reducible to GLNQ modules. In order to complete the picture and give the answer, we have to find the generating set for L calligraphic CIAMN. Well, unfortunately, I have to move very fast, actually. We defined this tau IJK are different, distinct numbers. This automorphisms of Mn, also some specific inner automorphisms of N, and this BIKJ and BIJ automorphisms, which in fact are coming from the paper of Backmuth. Now, using the result of Backmuth, we can find a generating set for L calligraphic Mn, consisting of these three types of automorphisms. Next step is to be more specific about LNIMN as a ZGLNZ module. Is generated as a module by these two types of automorphisms. And the third one is just to observe that this specific automorphism tau 1, 2, 3 belongs to these groups, to gamma C minus 1, IA of Mn. And before we proceed, the proof is actually based on the previous ones. Just as an observation for group G, if the center of this constant group is equal to this one for all C, then gamma C inner automorphism of G is equal to this this group. Now, just a quick recall for the statement of theorem 213, that's we need to prove that these two are equal. For n, comma C at least 4 by the previous result proposition 3.1, this module is generated by these two types of automorphisms. Since this one is linear automorphism and Mn satisfies the conditions of previous result, we have this one belongs to gamma c minus 1. Further by lemma 3.22, this automorphism belongs to gamma c minus 1. That means we got the result. Here I've got the references which I spoke earlier. That's it. Thanks for your attention. Happy
Okay,
anniversary, Vesselin.
let's thank the speaker first. Questions, remarks, notes? I don't see the questions. Let us speak. Thanks again to all of three speakers up to now. And
Okay.
10 minutes. Okay. And we start again in 11 in 10. Now break. Елица, чуваш ли ме? Okay. Не те чувам. Пусни звука.
Ето, чуваме се вече, нали?
Да.
Добре.
Извини ме на Христо, защото Христо там ли е?
Отвънка е на кофе.
Добре, после ще говорим с него. Че ми звъна спешно телефона. Росен Николов, нашия колега, е починал и ми се обади Първан. Не знам дали го знаете от анализа. Христо, извинявам се много за това, че не успях да се включа накрая, но просто ми се обади Първан, че Росен Николов е починал и аз, докато успея да му кажа, че съм на конференция и ти... Росен Николов от катедра анализ, за съжаление, с нощи е починал.
Той май беше асистент по диференциалних частник.
Не, по анализ. По анализ, по ДИС.
Скелета, тази грешка. Не, скелета е дявно.
Не е скелета. Росен Николов е... Окей.
Майя, ти ли звъня преди малко?
Аз звънях, че да се извиня на Христо, няма значение. Окей.
Нещо аз като такова и това
Точно защото в този момент ми звъннаха да ми кажат за Росен и аз не можах да съжалявам. Има неща, които не са предвидими.
Възможно той да бяха мисля, че като анализ на някой човек до убийци. Аз не знам това.
Да.
Не, то го пита, защото нали, той трябва да дойде, излезе той да кахне нещо.
Да, ама ние трябва да стартираме на време.
Да.
Направи си го с Ctrl-L, да ти е на пълен екран.
Не само да затворя, или Тодор ще затвори.
Okay, let's start again. The next talk is presented by Elica Hristova, and the title is Hilbert series and invariant theory of symplectic and orthogonal groups. Please, Elica.
Thank you very much for the introduction. In the beginning, I just want to say that I'm very grateful to Vesselin Drensky for many things, and that's why I'm very happy to be here on this conference. First of all, I'm grateful because when I came to the Institute 5 years ago, or maybe 6 already, he helped me a lot to integrate in the Institute, and also he agreed to be my advisor into projects for young scientists. So this is how our joint work started. He didn't know me before that, but he took the risk and agreed to be my advisor. And not only did he do that, but he also gave me a very interesting topic that was of common interest for him and for me, so we could work together on this topic. And that is why I'm very grateful, and I wish him a lot of good health and also very many years for productive work and beautiful theorems. And I also wish him to stay such a good example for us, the others, not only as an excellent mathematician, but as a good person that cares for the others. He always cared a lot for the department and did a lot for the other people in the department. So this is a very good example that we hope we can follow. And now let me start with the mathematical part of my talk. This is a joint work with Vesselin Drensky, as I said, and since it is about invariant theory, let me recall what the topic of classical invariant theory is. This was already mentioned in several talks, but maybe in slightly different notations. So let me introduce my notations here, or our notations. And there is one difference here with the previous talks. This is that we fix our base field to be the field of complex numbers, not any field of characteristic zero, but the complex numbers. And we fix it because we do some explicit computations later for which we really need this to be seen. Okay, so now we start with the topic of classical invariant theory. So we take G to be any group and V to be a finite dimensional representation of G. By C of V, we denote the algebra of polynomial functions on P. So G naturally acts on this algebra. Whenever we have a representation of G, then there is also an action on the functions on this space V. And so if we have an action on C of V, then we can consider also the algebra of G invariant polynomial functions, so this algebra of invariance. And the goal of classical invariant theory is to describe this algebra of invariance. And what does it mean to describe it? There are several important questions that we can ask here. The first one is this algebra finitely generated over C? If yes, then is it a polynomial algebra? And the more general question is, can we describe this algebra in terms of generators and relations? And if not, maybe we can give some upper bounds to the number of generators. And these are some questions that we're going to deal with later in our talk. Okay, and one tool that we use quite often in invariant theory is the Hilbert series. So let me also recall the definition of Hilbert series. It can be given for any finitely generated graded algebra, not necessarily algebra of invariance. So let me state it in the full generality. So if we take any finitely generated graded algebra over C, then the Hilbert series is this formal power series here. We just take the dimension of any homogeneous polynomial, homogeneous component of A, and we multiply it by a variable t to the I. And it is an important invariant, this Hilbert series, because it gives some partial information about the generators, which we asked for on the previous slide. For example, it gives information about the lowest degree for the generators and the maximum number of generators in each degree. So it gives an upper bound, even though a very big upper bound, but still an upper bound for the number of generators. And there is one more slide with the introduction. Now I want to introduce the setting that we are going to work with. So first we take lambda to be a non-negative integer partition. And by v lambda, we will denote the irreducible GLN module with highest weight lambda. Then we introduce the class of polynomial GLN modules. These are finite dimensional GLN modules which have such a decomposition into irreducible components. So the only irreducible components that are contained in the decomposition are of this above kind, given by just one integer partition. This is not the most general kind of finite dimensional GLN modules, but this is the kind of modules we are going to consider, and they are called polynomial. And now we introduce a class of algebras that we are going to work with. These will be again finitely generated graded algebras, but with one additional property, that each homogeneous component is a polynomial GLN module. So naturally, the whole algebra will be a GLN module, and thus we can take the algebra of invariants. And here in this talk, we'll consider the algebra of G invariants, where G is one of the following subgroups of GLN, either the orthogonal, the special orthogonal, or the symplectic group. And we want to determine the Hilbert series of this algebra of invariants. And before doing that, let us give some examples to see that this class of algebras is not empty. Okay, so the first examples are the symmetric algebra is in this class, and the exterior algebra is in this class. So here, the symmetric algebra, this is where a classical invariant theory stays, but we do not limit ourselves just to the symmetric algebra. We consider the whole class of these algebras A, and there are more general examples. If we take the tensor algebra of a polynomial GLN module and quotient it by any GLN invariant idea, then we get a whole class of examples. And here, in this class of examples, also stay the relatively free algebras, varieties of associative algebras. When we take I to be a T ideal, which we'll define later when we come to this point, then this quotient is exactly a relatively free algebra. So we may say that this class of algebras A that we consider is quite large. And now we'll move on to describe the algorithm, the algorithm that we develop for computing the Hilbert series. This algorithm is first invented by a group of other people, Benanti, Bumova, Drensky, Gemov, and Koev, for the symmetric algebra and for the algebra of invariants of GLN, of SLN invariants. So the subgroup considered is SLN, and the algebra considered is just the symmetric algebra, but we extend this algorithm to the other classical subgroups of GLN, the orthogonal and the symplectic groups, and we also consider a more general class of algebras, not just the symplectic. But let me continue. So first we need some definition of generalization of Hilbert series. When we have an algebra with a multigrading, which means in this case a grading given by n tuples of non-negative integers. So if we have such an algebra, we can define a Hilbert series for this algebra with respect to this grading in the following way. It's again a formal power series, and we take, similarly to the previous definition, the dimension of each homogeneous component, and we multiply it by this monomial here. And what is an example of a vector space with a multigrading? This, the irreducible module V lambda is such an example if we take the grading to be given by the weight space decomposition. Because all the weight spaces, they are indexed by such n tuples of non-negative integers. That's why the weight space decomposition is an n0 n grading for V lambda. And for this grading, if we take the Hilbert series of V lambda, it coincides with the character of the module V lambda, and therefore it is given by the Schur polynomial, which corresponds to the partition lambda. Okay, and then naturally, if we take any polynomial GLN module, since it is decomposed as a sum of V lambdas, it also has an n0 n grading given by the weight space decomposition, and it is very easily to determine Hilbert series. It is given again by this decomposition here. So this is the Hilbert series, and it again coincides with the character of the module W. Now, when we come to our algebra A, it has two gradings now. It has an N0 grading, which is given by the decomposition into homogeneous components. And it also has this N0N grading, which is given by the weight space decomposition of each module V lambda. And following the work that I already mentioned of Benanti, Bumova, Drensky, Genov, and Koev, which they did for the symmetric algebra, we introduced a new Hilbert series, which takes into account both gradings, both the N0 grading and the N0N grading. And it is a very natural definition. For each homogeneous component, we take the Hilbert series with respect to the N0N grading, and then multiply it by T to the I. And this is the expression we obtain. It is again given in terms of Schur polynomials. So this new Hilbert series, I'm repeating here the formula for it, is symmetric in the variables x1 to xn. And now again, following the work of Benanti, Bumova, Drensky, Genov, and Koev, we introduce a multiplicity series for A by taking the Hilbert series and replacing each Schur polynomial by this monomial here. And for us, so this is the multiplicity series, and we introduce a second multiplicity series by just this change of variables. And they are called multiplicity series because they carry the multiplicities here in the decomposition of A as a module over GLN. And so they carry the information about the GLN structure of A. And so this is the definition, and these are the definitions. And now what are the statements? The first statement is for the algebra of SLN invariants in A, and it is due again to this group of people. And it says that the Hilbert series of the algebra of SLN invariants can be given by the multiplicity series n prime that we just defined by substituting the first variables with 0 and xn with 1. They actually formulated this theorem for the symmetric algebra, not for any A in our class. But the proof is the same actually, so there is no harm to generalize their statement and give it for any algebra A in our class. And we use similar ideas, but of course now the representation theory of symplectic and orthogonal groups in order to obtain analogous statements for the algebras, these subalgebras of invariants. So for the symplectic group, we obtained that the Hilbert series of the subalgebra of symplectic invariants is given again by the multiplicity series n prime, where we substitute all odd variables with zeros and the even variables with ones. For the group ON, the statement is a bit more complicated than the Hilbert series. Not too much more complicated. So the Hilbert series of the ON invariants is given by another series Mn on T, which is defined inductively using this procedure. We first define M1 by taking the multiplicity series M that we define and substituting the first variable by -1 and by 1 and adding the two expressions. Similarly, then we define M2, and finally we define Mn, which appears in the formula above. For the subalgebra of SON invariants, we have a similar statement. The differences are that we take now the multiplicity series M prime, not the multiplicity series M. And the last step is different from the previous slide, that we don't take M prime of n minus 1 in 1 and minus 1, just in the point 1, evaluated in the point 1. So these are the statements, how we relate the Hilbert series that we are looking for to this multiplicity series that we defined. And now we want to see how we can use this to make some actual computations. So let us here recall the definitions of the two Hilbert series. And we see that if we know these multiplicities, then we can compute M and N prime. And by computing M and N prime, then we can compute also the Hilbert series of the algebras of invariance. And there are many cases that we know these decompositions or these multiplicities. Here I have given some of them. So if the algebra A is the symmetric algebra of the second symmetric power of the natural representation of GLN, then we can compute the Hilbert series for this one. If we take the symmetric algebra of the second exterior power V, we again know the decomposition and can do the computations. And these are two exterior algebras and another symmetric algebra for which we can do it. I'm not going to give the formulas because there are more examples, and let me now give some examples of relatively free algebras. Two examples we'll give of relatively free algebras. So the first one is the following. We take again B to be the natural representation of GLN, and we take A to be the quotient of the tensor algebra T of B, quotient by the ideal generated by all triple commutators. For the people that work in this field, they know that this is the relatively free algebra of rank N in the variety generated by the Grassmann algebra. And for this algebra A, we know the decomposition as the GLN module. It is given by this formula, where the set, so the decomposition is via all partitions that have one long row and one long column. So our set P here consists of all such partitions, and these are exactly the partitions that participate in the decomposition of A as a module over GLN. And so knowing this decomposition, we can compute the multiplicity series. And then using our statements from before, we can give explicit formulas for the Hilbert series. First, we have given formula for the algebra of Vesselin invariants, and then for the SP D2D invariants in the case when N is an even number. And with the help of these expressions, we can actually give generators of the two algebras. Remember, this was one of the questions in the beginning. Can we describe the algebra in terms of generators and relations? So here we see that these two algebras are finitely generated. And not only are they finitely generated, but they have just one generator in each case. So the algebra of Vesselin invariants is generated by the standard polynomial of degree n, and the algebra of SP2D invariants is generated by this polynomial. Then similarly, we have expressions for the Hilbert series of the algebras of ON and SON invariants, and we again can compute explicit generators. For the ON, we again have just one generator, and this is a polynomial algebra. Again, one of the questions that we asked in the beginning. This one is a polynomial algebra, the other three are not, but nevertheless, we give generators for all of them. Well, the fact that these algebras of invariants are finitely generated is not a new one. We have a general theorem by Vesselin Drensky, which says when such an algebra is finitely generated. So if we take again the tensor algebra V and quotient by a T ideal, where T ideal is any ideal that is closed under all endomorphisms of the tensor algebra. So this algebra of invariants is finitely generated if and only if T of V mod I satisfies a polynomial identity of this kind. This is the nth commutator. So this means that all elements of this algebra, when we substitute them here, we obtain an equality. Or in other words, the ideal I is generated by all nth commutators. In our example on the previous slide, the ideal I was generated by all triple commutators. So this was exactly an example of such an algebra, and that is why it was not surprising that it was finitely generated. Now we'll give one more example of a relatively free algebra, and this one we already see it won't be finitely generated. So it is given by Theory modulo the ideal generated of these products of commutators. And this is the relatively free algebra of rank n in the variety generated by the algebra of 2 by 2 upper triangular matrices. It is not finitely generated by the above theorem, but we can compute the Hilbert series for the algebra of SP2D invariants. We even managed to give an inductive set of generators by these formulas here. And for the ON and SON invariants, we give the expressions for the Hilbert series. And using this Hilbert series, we can prove specifically in this case, without using the theorem of Vesselin Drensky, that these two are not finitely generated, but we haven't given explicit sets of generators. Okay, this was this set of examples. Now, what can we do if we don't know the decomposition of mi lambda, the decomposition of the algebra A as a module over GLN? So if we don't know these values, well, we can try first to find the Hilbert series with respect to both gradings, and then from this Hilbert series find the multiplicity series. And we can do this for the algebras, the exterior algebra of module W and the symmetric algebra for module W, which is a polynomial. I will skip some of the details. Here we use the lemma of Barrel in order to go from the Hilbert series to the multiplicity series. And we managed to give many explicit results for n equal to 2, n equal to 3. And for the exterior algebra, we also have some examples for n equal to 4 and 5. For the symmetric algebra, the lemma of Barrel is not enough. We also need an algorithm of Benanti, Dumov, Drensky, Genov, and Koev, which is based on this lemma. And due to this algorithm, we can compute again many non-trivial examples for n equal to 3. These are here, I've given only the 3 most complicated examples that we have. This is a 15-dimensional vector space. And we managed to compute the Hilbert series for this vector space. And this is again a 15-dimensional vector space. And there is one last thing that I want to mention. With the help of this Hilbert series, we can go back to the question whether the algebra of invariance is a polynomial algebra. So if this is a very classical question, and for connected simple complex algebraic groups, this is answered. So for the irreducible representation, the answer is given by Katz, Popov, and Wimberg already in 1976. And for the reducible, it was given 2 years later. But the algebra ON is not connected, so it is not in the above lists. And we ask the question, okay, is this algebra polynomial or not? And if we use the Hilbert series, we get a partial criteria when it is not polynomial. If the numerator in the Hilbert series is not equal to 1, then the algebra is certainly not polynomial. If it is equal to 1, we don't know whether it is or not, but if it is not equal to 1, we know. And with the help of this criteria, we get these two small results for n equal to 2 and n equal to 3. So if we get, this is the last slide, so I'll just explain the 2 theorems and I finish. If we take W to be a GL2 module, a polynomial GL2 module, then the symmetric algebra of all 2 invariants is polynomial if and only if W is up to an auto isomorphism in this list of modules. So no other modules W give polynomial algebras of invariants. And for GL3 modules, so in the dimension n equal to 3, we get a similar result. So we have this list of modules for which the algebra of all three invariants can be polynomial, and for no other module can it be polynomial. So this is the end of my talk, and I want to thank you for your attention.
Okay, thanks to the speaker first. Questions, remarks?
And
Yes.
Would you please explain?
Okay, this is only blanks.
The rationality of the Hilbert series is interesting. Only for closed, the so-called closed presentation of the result. Or?
No, actually the rationality of the Hilbert series is interesting not only for this result, it is very important, and it follows here from the Hoster-Roberts theorem, which says that the ring of invariants is Cohen-Macaulay, which is some complicated kind of ring, but from this theorem it follows that the Hilbert series has this form. And of course, it is important that we just use it here in a very partial situation when we want the numerator to be equal to 1 or not to be equal to 1. But of course, this formula for Hilbert series is important not only for this. And about the rationality, also Drensky and Dom, of course, have results for relatively free algebras. Here I'm talking only about the symmetric algebra, but they also have results for rationality of Hilbert series for relatively free algebras. So this is an important question of its own.
Okay.
Thank you.
Another questions? I don't see. Let's thanks the speaker again. And the next talk is presented by Peter Delakov. Please, Peter, share your screen.
Hello. Okay, let's see. Can you see my slide? Okay.
Yes, see you. Try to move them up and down to work everything.
I believe I'm fine.
I think it's okay.
Okay, yeah.
Okay.
Yeah, we have a minute or so. Okay, I assume you can hear me. Okay? Yeah.
Yes. Everything is okay, but let us wait 1 minute and start in time. Okay, the next talk is presented by Peter Delakov from American University in Bulgaria and Institute of Mathematics and Informatics, Bulgarian Academy of Sciences. The title is Deformation of Vector Bundle Valued Higgs Bundles and L-infinity Algebras. Please.
Thank you. Thank you. So I'd like to thank the organizers for inviting me to this great event, and to congratulate Academician Drensky for his anniversary. I want to thank him for the kind of friendly science atmosphere that he's trying to nurture at the Institute. So it's an atmosphere of appreciation, not only of algebra, but also of music and language. And so it's really a pleasure to work in this environment. So in my talk, I'll try to say a few words about Higgs bundles of a kind that is not so often talked about, and I'll try to highlight some aspects that are tangentially related to Academician Drensky's interests. So, so since the audience is a little bit mixed, I'll say some general remarks to sort of highlight these relations. Now, this is part of this is work in progress, which is extension of earlier work of mine on the infinity description of Hitchin map, and also extending some results of Elena Martinengo from 2012. So just as a very general remark, earlier today, we heard Hrystreliev's talk where he talked about the Hilbert scheme. So in classical deformation theory, one studies moduli space of some kind of objects. These could be Riemann surfaces, these could be projective curves, or some complex varieties of whatever dimension. These could be some kind of sheaves of modules, vector bundles with some additional structure, you name it. So in the classical cases, one may have some kind of global moduli space, more often not have it, or it may have some deficiencies. But one might also be interested in looking at a particular object in your moduli space, right? You could be looking at a particular Riemann surface or a particular vector bundle and trying to study the nearby geometry of the moduli space. So one way to study the nearby geometry is to probe the space by taking some kind of deformations of your object, for example, taking one parameter deformations, taking some path in the moduli space, and so on. So I'm visualizing this here. Now, of course, you might not be able to write such a thing easily. You might not be able to write globally any actual deformation, but at least you might be able to write such deformation infinitesimally. So if you write the deformation of your object parameterized by the space of dual numbers, for example, then you would be actually getting a handle of the tangent space to your moduli space. So this sort of matured in the approach to formal deformation theory, where you're studying infinitesimal deformations of your point in the moduli space. You think of these as maps of germs. So maps from a spectrum of some Artin ring. So with an Artin ring, I mean a local Artin C algebra with residue field C. So everything would be over C in this talk, and occasionally homomorphic. So you can think of the spectrum of such a ring as a fat point, a point with fuzz, point to some infinitesimal information. So we are thinking of morphisms that send the closed point to the point you're interested in. So, so then in this way, what you're getting is actually a functor from, well, the category of local Artin C algebra with residue field C to sets which sends, well, which on object sends a ring to the homomorphisms of germs between spec A and the germ of M at X. Now, if this M happens to be a scheme, then you can identify this with the homes of C algebras from the local ring of your moduli space into A. Now, so the Grothendieck-Schlesinger approach to deformation theory is, in some sense, I'm slightly prophanizing, actually, prophanizing a lot for illustrative purposes. The Grothendieck-Schlesinger approach is forget M, so in some sense M may not even exist in your problem, but just focus on the deformation functor. Focus on this functor from arts to sets, again, which sends the Artin ring to the set of equivalence classes of deformations of whatever your object is, parameterized by spec A. So this is thought of as studying a formal neighborhood of X in M. Now, so this approach dates, I guess, back to late 70s, I would say. I think Schlesinger paper is 75 or 79, late 70s. And this philosophy has also been applied to, of course, deformation problems over other fields, but I will be just staying over C. Okay. Now, there is something specific here for complex numbers, and in fact, to any characteristic zero problem. This has been known as a folklore, as a folklore result called the Deligne principle. So in a letter to Milson, to John Milson in '86, Pierre Deligne said that actually his observation is that the deformation problems in characteristic zero are a special kind. They're controlled by deformation functors of very special nature. These are ones that come from differential graded Lie algebra, and quasi-isomorphic differential graded Lie algebras produce the same deformation theory. So actually, you can find the Deligne's letter on the web. Again, if someone is interested, I can show it actually now. It is full of various insights. So I'm going to remind you in a bit what is a differential graded Lie algebra, or DGOA. So it's a kind of graded Lie algebra with a differential, or if you want, it's a DG vector space with a graded Lie bracket. And so this was called the Deligne principle here, and in the 80s, Kontsevich was calling it a meta theorem. So this is a result that has been used by Deligne, Drinfeld, Gerstenhaber, Schlesinger, Stashev, Gulen, and many people. Now, this differential graded Lie algebra is typically discovered in a very ad hoc fashion. You don't have a recipe of discovering it, but on the other hand, it's not unique in any way. So quasi-isomorphic ones give you the same deformation theory. Now, this is the existence of such an object is essentially a theorem of Jacob Lurie and John Pridham, although they also changed the definition of deformation problem. So that's what I put here essentially. Okay, so a brief reminder here. So I already said what a DGOA is. So it's a triple CD and a bracket. So C is a graded vector space. Graded here would mean graded by the natural numbers, including zero, right? So there is a bracket. The bracket is graded skew symmetric. So switching two terms gives you minus and another minus sign depending on the degree, and satisfied graded Jacobi. And there's a differential which shifts the degree by 1, and it's a degree 1 derivation of the bracket. Now, how do we get the deformation functor out of this? Well, we do it in 2 steps. Again, these 2 steps were essentially discovered heuristically. So first, you consider the so-called Maurer-Cartan equations. You look at degree 1 elements in your DGOA, tensored with the maximal ideal of the Artin ring. Right? So it's nilpotent, and so we're looking at elements of C1 tensored MA that satisfy the equation du plus 1/2 of the U bracketed with itself being equal to 0. So again, D is the differential in the DGOA. U is the respective bracket, whatever it is in each case. So notice that we can do this for each Artin ring. In degree 0, C0 tensor MA is an honest Lie algebra, which is actually nilpotent. And so we can exponentiate it, and there is an action of the exponentiation of C0 tensor MA on the degree 1 piece by the so-called gauge action, given by the formula here. Again, all exponentials make sense because we are in a nilpotent setting. On the other hand, this is one of the places, actually, the key place where we use characteristic 0, because in the series that defines the exponential, right, we have various factorials. Now, so the functor that we assign is to every Artin ring, we assign the solutions of the Maurer-Cartan equation with coefficients in A mod the gauge action. So this is actually a set of, this set is actually the objects of a groupoid called the Deligne groupoid. And we say that the deformation functor is, well, the deformation problem is controlled by the DGOA if the deformation functor associated with the problem is actually isomorphic to the deformation functor coming from the DGOA. Now, in the late, well, mid to late 80s, there was a refinement of this principle due to Kuntsevich and Schlesinger and Stashev. Actually, Schlesinger and Stashev started writing a preprint on the topic, I think, in '79, and the last, it actually came out maybe 5 years ago. So the idea of this refinement is that actually DGOAs are a special case of a more complicated structure, L-infinity algebra, and this is where the tangential relation to Professor Drensky's work lies. So the DGOAs are in particular L-infinity, and actually formal geometry of the moduli problems should be controlled, should be thought of being controlled by an L-infinity algebra. And whenever you have maps of moduli spaces, for example, you can think of these as natural transformations between deformation functors. They are induced by L-infinity morphisms, by morphisms of L-infinity algebra. And again, the heuristics here is that this L-infinity morphism, which is in general a complicated object, should in some way encode the Taylor expansion of some morphism of formal pointed varieties. Again, just for completeness, I'm going to give you the definition. This is a bit of a technical subject, although some of the basic ideas are fairly simple. An L-infinity algebra is also called strongly homotopy Lie algebra or Sugawara algebra. It's a graded space with a bunch of linear maps. Typically, you may have infinitely many of them. In nice cases, you can have 1 or 2 or 3. So it's a collection of linear maps that these little q's, these qk, give you a degree 1 homomorphism from the kth symmetric power of v shifted by 1 to v shifted by 1. So the subscript C here indicates the core algebra structure. Here, if you want, instead of shifting by 1, so this is topological, this is some kind of suspension, instead of taking symmetric power v shifted by 1, you can think of the wedge power of v itself. And these collection of linear maps can be always extended to a co-derivation of the symmetric core algebra. So you can enforce the Kohl-Leibniz rule. Again, here is a formula, although it hides some of the information. So this capital Q is built out of using the different QKs and putting some signs. So we're going to require that this this capital Q, this co-derivation is actually co-differential, so that it squares to 0. Now, again, there is a practical case that's important for us, in which this is the case of a DGOA. So if we have a differential graded Lie algebra, there are just 2 of these maps being present. The Q1 is essentially the differential. Q1 of A shifted by 1 is minus dA. And Q2 is the bracket, again, with some shifts. Yeah. One can formulate a Maurer-Cartan equation in this setup involving not just Q1 and Q2, but all the higher powers, all the higher bits, and introduce a notion of homotopy that I'm not going to discuss, but for L-infinity algebras coming from a DGOA, this notion is precisely the same as the gauge equivalence that I mentioned before. Okay. So one can then require, so the heuristics of Schlesinger-Stashev is that you can think of this as some kind of higher bracket. So you can think of the Q as some kind of chain map, all right, which doesn't quite commute with the differential, but it commutes up to lower order terms. I've given also the definition of a morphism of two such structures. Again, I'm not going to, this is actually important. So if you want to give a morphism of two such structures, you have to require that these little HKs commute with the respective codifferentials. And practically, again, this boils down to a system of compatibility equation, the ones at the bottom of the page, that require compatibilities between K and K inverse, and the differential of K. Now, one can build a corresponding deformation functor out of this. So we're going to study in the next 3 minutes. I'll describe briefly some applications of this to a setup which is Higgs bundles with coefficients in a vector bundle. So we're going to fix a non-singular proper variety over C. Again, you can also think of this as a compact complex manifold. Even if it's not projective, most of the results, I mean, everything I would say actually would work in the complex case. We fix a vector bundle on it. So this would be our coefficient bundle. And a simple complex Lie group, rank L. Again, some of the things could hold also for reductive groups, but I'm keeping things simple. And we choose a basis for the generators of the invariants of the Lie algebra. So we take the polynomials with coefficients in G, and so look at the invariants of those under the adjoint action. So the group act by the adjoint representation, and we want the invariants. This ring is actually a polynomial ring by a result of constant, and there are homogeneous generators which are not unique, cannot be chosen in a unique way, but their degrees are well defined. So these are if you want, the coefficients of the invariant polynomial. So if you're doing SL n, you will be getting some traces of exterior powers. Now, so a V-valued G Higgs bundle would be a pair. A Higgs bundle would be a pair consisting of 2 bits, a principal G bundle, and a twisted endomorphism. So a section of the adjoint bundle tensor with V that satisfies an integrability condition theta wedge theta equals 0. So in some sense, those of you who study connections, for example, you can think of this as some kind of object that resembles a connection, except that there's just a zero, there's no the differential part of it, there's just an object that resembles the difference of two connections, if you wish. So a vector bundle version of this setup would be just take E to be a vector bundle as well, and theta would be a twisted endomorphism from E to E tensor V. So again, we can think of theta as a matrix, but now the entries of this matrix locally. So locally, when you choose a frame, your theta would be represented by a matrix of rational or homomorphic functions on your variety, and then the entries, well, would be having actually coefficients that are sections of the vector bundle V. So these are vector valued entries, but we have a commutativity condition theta wedge theta being 0, which allows us to think of them as a collection of ordinary matrices with entries in the sheaf of functions that actually commute. There are a number of cases that have been studied, but so the case when the dimension of X is 1 and V is the canonical bundle, so V is a line bundle, is the original Hitchens case that has been studied since 87, and there is a huge amount of work on this. If X is the projective line and V is V is all of D, another line bundle for sufficiently large D, this has been studied by the integral systems community, so under the guise of polynomial matrices, so by Mumford, McDaniel, Smolinski, Jacques Hurtubis, and so on. And a number of other cases that have been, so the generalized Hitchens system as well. So the first case that's actually contains a vector bundle of coefficients is when the vector bundle V is consists of the homomorphic one forms. This is due to Simpson, Carl-Simpson. There's some general results by Donagi-Gates-Gary and Donagi-Markman. Now, when V is the tangent, the homomorphic tangent bundle, this is the object. This object is called a Cohiggs bundle, studied by Biswas, Hitchen himself, Steve Ryan. So this is recent work. Actually, there is very recent work from a couple of months ago, well, from May, by Gallego, Garcia Prada, and Narasimhan, where they take the dimension of X to be 1, so Riemann surface, but you take higher rank V. So this is a kind of intermediate case. There are very few examples in this last category, right? So I'll just say that the number of general features, but the case when V is of high rank is much less understood and much less studied. And there are very few examples when either the dimension is higher than 1 or the rank is greater than 1. So first now I'll try to show you how you can cook up examples when the dimension is 1 and the rank is greater than 1. I'll show you the simple version of this. Take a special bundle E, which is the canonical plus O plus K inverse, and take a rank 2 bundle to be a K plus K inverse. Now, the endomorphism bundle of E is non-trivial, but it contains some trivial subbundles. So you can cook up a nilpotent Higgs field by taking sums of endomorphisms with coefficients in K and in K squared, sitting in those summands of the endomorphism bundle that are actually trivial. So there is a version of this that can be done for general simple Lie group G. In that case, you would construct examples by taking the rank to be the rank of the group, so the dimension of the Cartan. But that would require selecting a principal SL2 subalgebra. In other words, an SL2 subalgebra where your nilpotent elements are actually regular nilpotent, and that gives a particular decomposition of the Lie algebra in two ways, with respect to the grading and with respect to the SL2 triple, and that would give another collection of actually a huge collection of examples extending many things that we know. So this is these are very special Higgs bundles, and they have some again properties that separate them from the others. So Simpson and Martinengo identified the controlling DGOA here. Again, you can write it explicitly as some double complex. Now, essentially, the main result that I would like to say about, but I would not say much now, is that we can describe the abstraction space to deforming such an object, and there is a specific map from the H2 piece of the cohomology of your DGOA into the sum of symmetric powers of V, which requires, in a way, polarizing the invariance, taking the differential of invariant polynomial, thinking of it as an element of G duo tensor SDI minus 1 G duo, and pairing it with a suitable power of S and theta. Now, since this actually comes from constructing a particular infinity morphism that induces that goes from C to an abelian DGOA, and that annihilates abstraction. So this is extension of earlier work of Martinengo to a more general setup, and it uses the so-called abstraction calculus developed by Manetti. So since I don't want to be running over time, I believe I would just stop here because it's already at 12:06. But this is the key. So we have some control. Once we know the controlling DGOA, we can actually describe the abstraction space as well. We get an upper bound on the abstraction space, and in particular cases we can study these maps. So I think I would stop here and not take more time because the rest might be seen as a bit technical. So
okay, thank you, the speaker.
Thank you.
First, questions, comments, remarks?
Okay, I don't see.
Okay, I don't see.
Anything.
Thanks again to speaker. And
Yeah.
the next talk, the last in this session, is presented by Roberto La Scala. Please share your screen.
Yes. Host disabled participant screen sharing. You have to allow me.
Okay, Todor, okay.
As a
Now,
presenter.
a second, please. Yes, a second, please.
Could you hear me well?
Yeah, I hear you. Todor, make
Okay.
your cocos and everything is okay after that.
So, okay, now I can...
Okay.
Okay, that's the screen.
Yes.
Presentation.
Okay. But we start 2 minutes. Wait to start in time.
Yes.
Okay, the next talk is titled Ciphers and Differential Equations and will be presented by Roberto La Scala. Please.
So thanks for the introduction. The talk is based on a paper which is a joint paper in collaboration with Sharwa and Theory from the Scientific Analysis Group in India. The paper, of course, is dedicated to the anniversary of Vesselin. As a matter of fact, many stream and block cipher, which are really used in important applications, are recursive rules which defines the evolution over the time, say the discrete time in your computer, of a vector with entries in a finite field. This vector is usually called the state of the register of the cipher. This recursion is defined by means of some transition vector function, which is exactly the one corresponding to a system of explicit ordinary difference equation. I provide immediately a couple of examples for guiding us in the formalization of this notion, abstract notion. Trivium is a cipher which was developed in Europe within a project, and Trivium was published in 2003. As you will see, it has an extremely simple structure, but no decisive attack has been made to this cipher. The structure of this cipher is simply this three quadratic explicit ordinary difference equation. This equation defines the evolution of the internal state of the cipher. This notation is some notation for the system of difference equation, but this, notation shorts the corresponding infinite polynomial system notation, which is also used in many cases. The coefficients of the system are in the finite field, and we look for solutions which are sequences, functions from the natural numbers into this field with two elements. Being an explicit difference equation, of course, we have a one-to-one correspondence between the initial state of the solution and the solution itself. We will denote V0 this initial state, and for each clock t, we will denote by Vt the state at the time t of this vector. The state transition function is just the polynomial map which sends the state at time t to the state at time t plus 1. For this cipher, the key and the initial vector, which is some kind of additional vector, is just a part of the initial state. It's essentially its initial state. For this particular cipher, it's some part 160-bit of the initial state, which is in fact 288 bits. The remaining bits are fixed. But we may say that the key for this cipher, which are defined by means of system of difference equations, is the initial state. Together with the different system, we have some polynomial, which is the polynomial which is used to define the output of the cipher, so-called key stream. This key stream is a pseudo-random sequence of elements from the field, which is added to the plain text stream in order to obtain the cipher text stream. This is the way the stream cipher operates. At a clock t, the key stream is defined as the value of this polynomial over the state Vt. You see, the situation is non-linear because the equation governing the evolution of the internal state are quadratic. But for the key stream, we can simply use some linear polynomial. In fact, the key stream outputs the clocks not from the initial state, but from the initial time clock, but from some time which is larger. In this case is 1152. This is to protect the key, which is the initial state, from some attack which is based on the knowledge of the key stream. In cryptanalysis, some simplified, well-studied simplified version of Trivium is Bivium, which is just a couple of difference equations, and this simplified T-string polynomial. Note that the state transition function of Bivium and Trivium are invertible maps. That is, one can reverse the time. One can compute the initial state starting with any state. And this is a potential weakness for a cipher because instead of attacking the initial state containing the key, one can attack any internal state of the cipher. And this reduces the complexity of the attack, of course. On the other hand, the property of a system to be invertible and also to be reducible, it contains some subsystem over a subset of independent variables, can be considered a resource to define block cipher. Difference system can define not only stream cipher, but also block cipher. An invertible system defines, as I said, a block cipher. I give you just an idea how to do this. The initial state of the subsystem is the key of the cipher. The initial state of the system is the key plus the plain text. If we fix some some clock, some final clock, some number of rounds for these ciphers, the final state of the system contains the cipher text, which is this part VT, corresponding to the plain text V0. To decrypt, using the key subsystem, one can compute UT starting with the initial K U0. The inverse system is then able to compute the initial state and hence the plain text, starting with the final state. So the fact that the system, the different system is invertible allows the possibility to define a block cipher. An example is this key lock. This key lock is some cipher for electronic keys, car immobilizer. The patent of key lock was sold in 1995 for $10 million, but in fact, mathematics cryptanalyzed this some 10 years later. And the system defining the key lock are just these two equations, where one equation is used for the evolution of the key. But the point is that this cipher is weak, essentially because of this. This equation is too simple. This it's a linear difference equation, very simple form. It's too simple, and the period here is 64. So by means of this, cryptanalysts develop some mean to attack the cipher, and nowadays it is not longer considered secure. So let's come to formalization. The appropriate formalization to study system of this different equation from an algebraic, from the formal theory viewpoint, is this theory which is called difference algebra. So let K be any field, consider a finite set of variables for each integer t, and consider the polynomial algebra R over the finite sets, the countable set of variables, which is the joint of this finite set. Consider the algebra endomorphism sigma, which is the map that sends some variables clock t into the variable clock t plus 1. We call sigma the shift map. The algebra R endowed with the map sigma. Sigma is called the algebra of ordinary difference polynomial in the variable x1, xn. And given some order for the system of difference equations, say R1, Rn, we define, it is useful to define the subset of the initial variables, x bar, and the corresponding subalgebra R bar, which is finite generated in this case. So given some set of polynomial f1, fn, a system of explicit ordinary difference equations is by definition this system, which corresponds to an infinite system of polynomial equation. A K solution in sequence of these systems is an n-tuple of function, which are sequence ai from the natural number into the field K. We are interested in this kind. Of course, there are other kind of, in some extension field, we have other kind of solutions, but we are interested in solutions which are sequences over the base field. For each system, we define an important notion is to define this algebra endomorphism T bar, which sends one initial variables into the next one and the last one into the polynomial Fi. To this endomorphism, it corresponds a vector polynomial function. And this vector polynomial function is the one that sends some state for a solution into the state at the next time, at the next clock. We call T bar the state transition endomorphism, the formal version of the state transition map. Let's say symbolic. Denote by Vk the set of K solution of the system 1. We have a bijective map iota. Of course, this is the map which sends the solution into its initial state, and this is a polynomial map. Consider the endomorphism T bar and corresponding state transition map, we have the notion of invertibility of the system. The system is invertible if the state transition endomorphism is invertible, is an automorphism. In this case, of course, T is also a bijective map. So it's important to know if our cipher is invertible or not, because of this reason that if it is invertible, it is a little bit less safe. So Grover basis provides a simple algorithmic method to determine if an endomorphism over a polynomial algebra is invertible or not. And this is, I mean, the theorem. This theorem says that if you have an endomorphism over some polynomial algebra and you want to know if it is invertible or not, you have to encode the rules of which defines this endomorphism as an ideal, and you compute a Grover basis of such ideal. If the Grover basis is of this kind, you have immediately the rules that defines the inverse of the endomorphism. In particular, for explicit different system, we have this result. If we apply this result to the state transition endomorphism, you obtain this, where the Grover bases have such form. And this gives the way to define, the appropriate way to define the inverse of an explicit difference system. So definition is that up to reverse the order of the initial variables, the inverse system of an invertible system is by definition this, where this GI are the image of the polynomial f from I, which appears in the Grover basis under this endomorphism, this automorphism that essentially reverse the order of the variables. So we have the appropriate notion of inverse of an invertible system. By means of this, of course, this definition works, and you have that the map corresponding to the system on one, the inverse of the other. And this allows to compute the initial state starting with any state simply by using the inverse system. The inverse system allows you to reverse the time and go back. For instance, if you compute, can be easily computed by a Grover basis, which takes some milliseconds, you have that the inverse state equation of this cipher trivium, this system of this explicit system of difference equations is of such kind. This is the inverse. A cipher that is based on an explicit difference system, which is periodic or small period, is clearly weak. So we need this notion. Let T be state transition map of an invertible system. We call the system periodic if this map is periodic. In this case, of course, all K solutions are periodic function. And if K is a finite field, of course, all invertible systems are clearly periodic because this map is a bijection over a finite set. And an open problem up to my knowledge is to compute and maximize the period of a polynomial map of a vector space of a finite field in the nonlinear case. How to compute this, period, and to obtain maps of maximal period. In the linear case, of course, this is easy, and it is well known how to do. In the following, we assume that K is a finite field. So we have the notion of difference stream cipher, abstract notion. A difference stream cipher is an explicit difference system together with a polynomial. If A1, AN is a K solution, its initial state is called the key of the solution. If the vector Vt denotes the state of a solution, the function B, which is obtained by the evaluation of the key stream polynomial over this state, is called the key stream of this solution. It's the output of our cipher, this pseudo-random sequence of elements in our finite field K. We call F the key stream polynomial of the cipher. Of course, we can encode this system plus this polynomial as simply a system of this kind where the variables Y describes the key stream sequence. let's see. Now we want to describe what is an algebraic attack to such cipher. So let's see a stream cipher. B is the key stream of a K solution. We consider this idea. We consider this equation. We impose to our solution that they have some given key stream, because the key stream in the attack, when attacking a cipher, is assumed to be known. It's assumed that you know some piece of plain text stream and some piece of cipher text stream. So by difference, you know some piece of the key stream. So the key stream, if you assume that key stream is known, you want to know which solutions are compatible with this given key stream. In particular, which initial state of such solution. What are the initial state of such solution, which are the key? Because the goal of the attack is to know the key of the cipher starting from the knowledge of the key stream sequence. So an algebraic attack consists in computing the solution of the idea I plus j, where j are such condition about the key stream, and I are the equation of the difference. The equation of the different system describe the evolution of the internal state. But it may be convenient to compute directly the equation, not of the solutions, but the spatial solution, which accords with the key stream, but the equation of the initial state of such solution, which are the keys. I mean, the equation satisfied by the key, which are compatible with the observed key stream. To do this, we just need to consider again the state transition endomorphism corresponding to the explicit different system governing the cipher. And for any t, denote by f prime t the image of the power to t of this endomorphism, and you define this other ideal where you substitute sigma t f with this t bar to the tf, and this idea belongs to this finite generated polynomial ring R bar, and the equations satisfied by the initial state are just the solution for this ideal. The vector satisfying this polynomial equation. Of course, in practical algebraic attack, we don't know all the values of the key stream, which is an infinite number, but we know some piece of the key stream. But note, since the algebra R bar is Noetherian, finite generated and Noetherian, you can easily understand that it's enough to know for a sufficient number of key stream values, we don't lose any equation satisfied by the keys. So you can restrict your knowledge to some finite number of values in the key stream, and you don't lose. You are sure that you have all the equations you need to solve for the key. For computing now, so for computing the set of the keys, we can use Gröbner basis, or in the case that the field has two elements, we can use so-called SAT solver, because, or also BDD, binary decision diagram, are some methods for Boolean functions. And okay, for actual ciphers, we generally have that the solution, there is a unique key, which is compatible with the sufficiently long number of variables in the key stream. So we can apply so-called Nullstellensatz for finite field. And this Nullstellensatz for finite field essentially says that if you have a single solution to your problem, the Gröbner basis immediately gives you such solution. The Gröbner basis is of this form, so it gives the unique solution that you are looking for. And this works for any Gröbner basis, for Gröbner basis with respect to any monomial ordering. And this is a good news, because Gröbner bases have some cost depending on the monomial ordering you are choosing. So in the case of unique solution, you can choose for the best monomial ordering, which is, for instance, de Graaf-Lex. So you have some method that works really to compute this unique solution. But note that in some case, this image under this endomorphism, which is not non-linear because the system is non-linear, may be of too high degree. If this happens, you have some trick to do to avoid this problem. But I mean, the main trick is based on the following observation. If the system is invertible, you don't need to know the initial state, but you need to know any state of the system. And by means of the inverse of your system, you can recover the initial states. So this means that essentially you can reduce the clock t where the key stream starts to 0. It's like that you solve for the internal state corresponding to the clock where the key stream starts. And this reduces the degree of the equation that you have to deal with. And we use, in fact, this strategy when attacking Bivium. This reduces complexity of the problem because it reduces the degree of your system. If the image have still too high degree, you can solve not for the initial state, not for the keys, but for the solution on the whole, because this equation have all the same degree. But the problem here is that you have to deal with the polynomial system over a large number of variables. So you pay in another direction. When you compute Gröber basis, maybe you can perform your Gröber basis on some large number of variables. So a typical trick consists in evaluating, you are in a finite field, so you can evaluate in all possible ways some subset of variables. This is called some guess and determine strategy. And since you have a unique solution, most of the solution that the system that you have are inconsistent. The Gröber basis behaves very well over inconsistent system. But this SAT solver, which are based on Boolean function, don't behave as well good. The cost for such trade-off trade-off one Gröber basis with many is the number of evaluation, which is Q2S, where Q is the cardinality of the base field and S is the number of variables that you are evaluating, times the average computing time for a single Gröber basis. Okay, we perform some computation, some algebraic attack over Bivium, and by means of this algebraic attack over Bivium, we immediately see that the attack is really feasible, and the Gröber basis perform much better than SAT solver, which are considered very well in cryptography, but actually Gröber basis perform better. And we can conclude with this thoughts system of explicit difference equation of a finite fields model, many stream and block ciphers of real application interest. For instance, the stream cipher, which is inside your Bluetooth communication we are using now, belongs to such class. This modeling allows to study important properties of this cipher from a general viewpoint as the invertibility, periodicity, and to define algebraic attacks which are essential to assess their security. Because, I mean, if your cipher is nice, but it is unsafe, it is completely useless. So you have to estimate the cost of attacking them. So the notion of different ciphers allows to develop new ciphers simply by defining some system of difference equation and study their cryptanalysis, how difficult it is to attack them. For all details about this talk, you can look into this paper, which is already appeared on the Journal of Symbolic Computation. Thank you for the attention. I'm ready for any question. Thanks.
Thank you. Very nice talk. Let's thank the speaker.
Thank you.
And comments, questions, remarks? I don't see. Let's thanks again to the speaker. Let's thanks again to all speakers this morning session.
Thank you.
The next session will be starting 2 o'clock in the morning, in the afternoon.
Okay.
Break for lunch. See you.
Have a nice lunch.
Yes.
Ciao, Roberto.
Ciao, Vesselin. It's nice to be here to celebrate you.
Unfortunately, I have another meeting in the moment in the Executive Council of the Bulgarian National Fund. So I have here 2 computers. Yes. With one here, I listen to your talk, and with the other, I participate in the meeting.
Okay, but you see, it's most important is my feeling for you. That's I hope you receive it. Okay, let's hope to see you again. Ciao, Francesca. Ciao. Tutto bene, Francesca? Dove sei? A Palermo?
Sì, sì, a Palermo. Non ci possiamo muovere.
No, ancora no, per quest'anno ancora no, ma speriamo presto. Speriamo presto di incontrarci. Buon pranzo per noi. Buon pranzo per noi, un po' prestino però.
Sì, a presto. Antonio,
ciao,
pure. Ciao Antonio.
Ciao. Ciao a tutti.
Luisa, ciao Luisa. Buon pranzo.
Tutti gli italiani sono presenti.
I am invading the Italians.
Right.
Sì.
Ciao Luisa.
There was an expression by Castro that la revolución habla español. And now mathematics parlo italiano.
Francesca, ti sei tagliati i capelli?
Sì, sì, c'ho i capelli corti.
Io ho la foto, una foto che ho mostrato nella...
L'ho vista.
L'hai vista?
Andavamo a Rehovot, bellissimo. È stato un convegno bellissimo.
Sì, sì.
Sì, sì.
E avevi una bella capigliatura. Ciao Vesselin.
Ciao. Come stai? Tutto va bene?
Sì, tutto bene. Un bel convegno, molto ben organizzato. Okay. Very nice conference.
Ok.
In your honor, nel tuo onore, to celebrate you.
Okay, the celebration had to be in December, as you know.
Yes.
But they waited until I am not more a director, because otherwise it would seem that they want to show some respect to me when I am director. So they waited to finish my directorship and then to organize the conference.
Mm-hmm. But how is the situation in Bulgaria, in Sofia, for the...
Okay. We have some restrictions, not very strong. The people there not very, they don't follow very much the rules. But we are in one of the first places maybe in the first place in the European Union by mortality. Otherwise, yesterday in Sofia there were about 400 new cases of corona, and Sofia is about 1.5 million.
But in this conference, there are Bulgarian professor and Zayshev and other people in the audience physically. Or...
See, in the audience, I was in the opening and now I stay at home because I have some other duties. But usually there are a couple of persons who stay there in the room. Also, Misha Zaitsev is there because he prefers to stay there, not in the hotel.
Yeah, I see. Also, I saw him. I saw him in the classroom.
Yes. Also, the foreigners who are here, there are 2. One of them is Martin Kasabov, who was my master student, but now he's in Cornell. And he arrived here, and the other is Misha Zaitsev. All the other people from abroad, they are simply using the Zoom.
But Zaitsev is going to how is it going to give the lecture? The reason that I'm asking,
okay,
because
I think that
in the lecture of Martin,
from the main hall.
in the
The things
lecture
you
of
can see TCRT 2021 hall. Probably he used this hall, I think.
I'm saying that because in Martin's lecture, I don't know, at least for me, it was not easy to understand the voice.
I don't know. We see.
Okay. I don't know if.
But Misha speaks very clearly, okay?
Oh, yeah, yes. It was not
I know.
Yes. Okay.
Okay, and I quit for a while because I have to go to the other meeting. Well, we approve all the grants in mathematics, not only mathematics, but in science. So now this is important there.
Hey, so we'll see you later.
Yeah, sure. Okay.
Okay, it's your lecture.
Even before.
Okay.
Bye bye.
Francesca.
Bye bye, have a good lunch.
Luisa, sì.
Poi sei riuscita a rintracciare Giulia Maria? Ti ricordi mi chiedevi notizie?
Sì, ti chiedevo notizie, ma quando è stato? Non mi ricordo più.
Parecchio tempo fa, tipo in primavera.
Sì. In primavera, ma forse di più, ma perché non mi ricordo più perché cos'era.
Forse
no, comunque
non sei riuscita.
No. Ah, no, era per questo convegno. Forse me l'aveva chiesto. Sì. No, non sono riuscita a rintracciarla.
No, vabbè,
No.
solo questo ti volevo dire. Mi era venuto in testa
non
di
mi ricordavo più perché... sì.
Per questo fatto qua, vero? Il congresso.
Sì, perché forse sì, me l'aveva chiesto sì, di rintracciare. No, non l'ho rintracciata.
Vabbè.
Antonio,
tu hai notizie? Tu hai
Ciao,
notizie?
Antonio.
Giulia Maria? No, perché io ho perso completamente...
No, ma sono anni che non...
Anni.
Non ho
mi
idea.
ricordo più, infatti, perché no.
Sì, da quando è andata in pensione poi lei non ha fatto, non ha seguito più nulla, diciamo.
Esatto.
Va bene, non voglio...
anni,
forse sai chi può avere notizie? Claudio Procesi. Perché
sì.
lui è amico, sono amici, insomma. Poi magari qualche volta glielo chiedo.
Va bene. Vediamo, ciao.
Ci vediamo dopo. Ciao.
Ci vediamo dopo, ciao.
Здравствуйте, профессор Зайцев.
You want to switch to full screen? I think it's okay. It's okay.
Нормально, да. Прошу послать потом.
Да, я помню. На ваш адрес.
Да.
Good afternoon. Let's start our afternoon session of the conference Trends in Combinatorial Ring Theory, dedicated to the 17th anniversary of Professor Vesselin Drensky. Our first speaker is Professor Mikhail Zaytsev, and he will talk on the existence of polynomial identity exponent of codimension growth. Take the floor, please, Professor Zaitsev.
Thank you very much. First of all, I would like to thank the organizer for this opportunity to participate in this excellent conference. And I also join to all congratulations to Vesselin from previous speakers. So let me start. I will tell about numerical characteristics corresponding to polynomial identities of some associative and non-associative algebras. First of all, I repeat a few definitions, although it was mentioned many times in the previous speech, so I will be very short in this place of the talk. You consider algebras so they field f of characteristic 0. I present a few examples which I will use later below in the talk. First example is the full matrix algebra A containing from the entries Aij's. The second one is the polynomial identities polynomial ring A equal to f from t, for example, on one variable. The next example, we consider the 2 by 2 matrices with the 0 second row and consider this space as the Lie algebras under the commutator xy minus 1x. The next example is the Grassmann algebra or exterior algebra of infinite dimensional vector space. And it is recall that it is associative algebra generated by unit and countable number of generators E sub 1, E sub 2, and so on, and defining relations E sub I, Ej equal minus Ej ey. In particular, square of any generator should be 0. Polynomial identity, I recall again that we consider identities of algebras and numerical characteristics associated with identities. So let F be a field of characteristic 0 and let A be an algebra over F. In general, non-associative polynomial F on x1, xn is said to be an identity of A if it vanishes under any evaluation on A1, An of elements of this algebra A. For example, if A is polynomial ring, it's commutative, so the commutator x1, x2 minus x2, x1 is always 0. It's an identity. If we consider UT2 2 by 2 upper triangular matrices, it's easy to check that the product of two commutators is identically 0, since the commutator of two algebras, two matrices of this type, is strictly upper triangular matrices. And product of this any two matrices is 0, obviously. And finally, the Grassmann or exterior algebra satisfies the long commutator or Lie commutator of length 3. If we consider 2 by 2 matrices with 0 second row as a Lie algebra, then this algebra satisfies identity of its metabelian in the Lie sense that the commutator of two commutators is identically 0. So let's go on and recall the numerical invariance responding to the identities. Let f on x be absolutely free non-associative algebra, then the set ID of A of all identities of algebra A forms an ideal of this algebra, so-called T-ideal. Now denote by Pn the subspace of all multilinear polynomials on x1 and xn. Then intersection Pn cross ID of A is actually the set of all multilinear identities of A of degree n up to the renaming the variables. Denote by Pn of A the quotient Pn over intersection Pn cross ID of A, and define the nth codimension Cn of A as the dimension of this quotient Cn of A, the dim Pn of A. Few examples. If A is the free associative algebra, then any multilinear polynomial on x1, xn is a linear combination of monomials x sub sigma 1, so on, product x sub sigma n, and all these monomials are linearly independent. So total number of such monomials is n factorial, hence Cn of A is exactly n factorial. If A is a free Lie algebra, then it's not very obvious, but it's known that Cn of A is equal to n minus 1 factorial. If A is absolutely free algebra, then Cn of A is the product quotient 1 over n times 2 by n to n minus 2, choose n minus 1 times n factorial. Approximately, it grows like 4 to the n times n factorial. Here, the factor 1 over n to n minus 2, choose n minus 1 is so-called nth Catalan number. Catalan number, that is the number of all arrangements of brackets on the word of the length n. If A is the polynomial ring, then in this case, any product x sigma 1, x sub sigma n coincides up to the identities of commutativity to the product, ordered product x sub 1, so on, x sub n for any permutation sigma. Hence, Cn of A is precisely 1. If A is an important algebra, say A to the m is 0, then Cn of A obviously is 0 for any n greater than or equal to m. For Mutabillian Lie algebra, two-dimensional, Cn of A, it's almost obvious. It's not difficult exercise that Cn of L is equal to n minus 1. For Grassmann algebra, this is non-trivial result. First it was proved by Krakowski and Regev in 1973 that Cn of G is exactly 2 to the n minus 1. And also for upper triangular matrices, 2 by 2 upper triangular matrices, Cn of A is equal to this value. So approximately it's 2 to the n minus 1. It was computed first, I suppose, by Yuri Marstov in 1971. Formally, there are infinitely many examples where asymptotics, where the codimensions computed precisely, but actually it's based on the only few precise examples. So it's much easier to compute not precise value, but asymptotics of the codimension growth. Now I will tell a few words about types of growth which can appear as the codimensions. Given an algebra A, we say that the sequence Cn of A is polynomially bounded, or roughly speaking, it has polynomial growth. If Cn of A is bounded by some polynomial A times n to the t for some positive, actually integer, maybe we say positive integer A and t. In the previous examples, we see that polynomial ring f on t is a polynomial, has a polynomial growth. Mutabillian Lie algebras have polynomial growth. The next type of growth is so-called intermediate or sub-exponential. We say that if Cn of A grows faster than any polynomial but slower than any exponential function, that is n to the t is much less than Cn of A, and Cn of A, on the other hand, is much less than a to the n. Formally speaking, we say that it means that the limit of the quotient Cn of A over n to the t is infinity for any natural t, whereas the limit of the quotient Cn of A over a to the n is 0 for any real a strictly greater than 1. Then we say that Cn of A has an intermediate or a sub-exponential growth. Unfortunately, I cannot present trivial examples of intermediate growth. The reason will be shown later why there are no non-trivial examples. Exponential bounded growth. We say that Cn of A grows exponentially or has exponential growth if it's restricted to the a to the n for some positive real a greater than 1. In the previous examples, Grassmann algebra has exponential growth 2 to the n minus 1. Associative algebra UT2 has exponential growth approximately the same value 2 to the n minus 1. And next kind of the growth is over exponential. We will say that Cn of A is grow over exponential is if it's much bigger to the a to the n for any real a. That is the limit of the fraction Cn of a over a to the n is infinity for any a greater than 1. What about examples of over exponential growth? Free algebras has exponential growth, free in the sense it's associative, free Lie, absolutely free non-associative. All these algebras have over exponential dimension growth. Maybe non-trivial example can be presented like the product of variety A times N2 of Lie algebras. That is variety defined by the identity of the presented time. Commutator of two commutators of length 3 it should be equal to 0. For this variety, the dimension growth is over exponential. It's approximately the square root of n factorial. It was first concluded by Velichenko in 1984. For relative free, absolute free, solvable of length 3 algebra of countable rank, the dimension growth is also over exponential. It's approximately the fraction of n factorial over the logarithm n on the power n over 2. It follows from results of Viktor Petrogradsky published in 1995. And it's interesting to remark that if L is finitely generated solvable of length 3 Lie algebra, then Cn of L is exponentially bounded. It was first shown in my paper in 1997. And it's interesting to mention one result by Alexander Grishkov. He proved that if L is a Lie algebra with a non-trivial Lie identity, then for any real A greater than 1, there exists natural n such that Cn of L is strictly less than n factorial over a to the n if n small is sufficiently large. It was proved by Alexander Grishkov, I said it, in 1988. So we have 4 big classes of the growth: polynomial, which is strictly less than sub-exponential, which is strictly less than exponential, and strictly less than class of over exponential dimension growth. So now I will say a few words separately about all these classes. What about polynomial growth? First of all, it's interesting to mention one result. Initially, it was proved by Vesselin Drensky for Lie and Jordan algebras in 1989 and 1992. Much later, the same result was proved by Sergei Ratseyev in 2013. For all these classes, it was proved that if it had Cn of A grow polynomially, that is, if A is an algebra with polynomially bounded dimension growth, then Cn of A grow like the real polynomial. That is, its Cn of A is equal to some real alpha n to the t, and some additional summands of the order like over n to the t minus 1 for some natural t. And moreover, something we can say about the constant alpha. If A is a unitary algebra, then the leading term alpha is a rational number, and it satisfies 2 inequalities, which is written below. If A is a non-unitary, there are no limits for the constant term alpha. Later, Antonio Giambruno, Lamartine, and Viktor Petrogradsky realized all this, not all, the smallest and largest values of alpha by constructing the corresponding examples. If we look at the general non-associative algebras, then the situation is much worse. In 2808, me and Sergei Mishenko constructed first example of a non-associative algebra A with a fractional polynomial growth, that is Cn of A grow like n to the 3.5. more precisely, there exists a logarithm modulo n of Cn of L, which is equal, the limit exists and equal exactly 3.5. Later, in one paper by Antonio Giambruno, Sergei Mishchenko, Angelo Valenti, and myself, we have proved that for any real alpha between 0 and 1, there exists an example of algebra, non-associative algebra A sub alpha, such that the limit of logarithm modulo n of Cn of A is equal exactly precisely 3 plus alpha. Some unexpectable corollary of this result is that there exists non-Specht variety of polynomial per-dimension growth. I should mention that it was not first example non-Specht variety of polynomial growth. First example was constructed by Vesselin Drensky much earlier. In his example, the algebra was anti-commutative, while our example may be also commutative or anti-commutative. In 2018, Antonio Giambruno and me constructed example algebra A such that Cn of A is polynomially bounded, but the limit of Cn over logarithm n doesn't exist. So it's not real polynomial, it's only polynomially bounded function. Few words one can say about low polynomial growth, but maybe I will skip this part since it was shown by on the talk by Angelo Valenti. Sub-exponential of intermediate codimension growth. I mentioned that there are no trivial examples. The reason is that in associative algebras, Lie algebras and Lie superalgebras, the most classical classes of algebras, there are no algebras with intermediate growth, codimension growth. This means that either Cn of A is polynomially bounded or it satisfies inequality of the type. In associative case is at least 2 to the n. It follows from Kemmer's results 1978. In Lie case, the lower bound is the same. It was proved by Sergei Mishchenko. For Lie superalgebras, we can only prove that the lower bound of over exponential growth is square root of 2 to the n. In associative and Lie case, the lower bound is precise, but in Lie super case, it's not true. It's only lower bound. We have no counterexample less than 2 to the n. And it's interesting to consider finite dimensional algebras. If let A be a finite dimensional algebra of dimension d, then either Cn of A is polynomially bounded or Cn of A is some function which depends, exponential function which depends, lower bound depends on the dimension of this algebra A. This is a result of Antonio Giambruno, Mishchenko, and myself, 2008. If additionally A is a unital algebra, then the lower bound can be improved. We can say that it's either polynomially bounded or grow faster than 2 to the n. In general, non-associative case, there are a lot of examples of intermediate growth. I recall present few theorems. Theorem 1 by Antonio Giambruno, Mishchenko, and myself, published in 2008. We have proved that for any real alpha between 0 and 1, there exists an algebra R sub alpha satisfying the identity of left nilpotence of step 3, such that Cn of R alpha grow like n to the alpha. This is really sub-exponential function. This means that there exists the limit of double logarithm over n of Cn of R sub alpha is equal to alpha. All of these functions are non-decreasing, but recently Dushan, Repusch, and me have proved that there exists an algebra A with a sequence of the sequence of increasing sequence of integers A n1 and n2 sub 2 and so on, such that for odd indices j, the subsequence c and j of A grows almost linearly. I will say what does it mean later. Whereas for even indices j and cn sub j of A grows almost exponentially. What does it mean? This means that cn j of A for j odd is strictly less than and j plus some small slowly grows function double logarithm of nj. Whereas for even j, cn of j is faster than 2 to the fraction, which is almost linearly. This fraction nj over log of nj. It's a recent result published in 2020. Now I fixed your attention on the exponential codimension growth. Class of algebras with exponentially bounded codimension growth is very wide. As it was mentioned in my talk and some previous talks, all associative PI-algebras has exponentially bounded codimension growth. All finite dimensional algebras has exponential growth. I will say later about this results only a few words. Infinite dimensional simple Lie algebras of Cartan types, namely WNs, special algebras Cn, contact algebras Kn, and Hamiltonian algebra Kn, all of them have exponentially bounded codimension growth. The fine Kac-Moody algebras also has exponentially bounded codimension growth. List algebras and list superalgebras is an important commutator subalgebra. Novikov algebras, this is a result by Oskar Zhumagildaev, and many others. Now I will consider separately few classes of algebras. First natural class is classes of associative algebras. Let A be an associative PI algebra that is A satisfies a non-trivial polynomial identity. Then, as it was mentioned above, its codimension sequence is exponentially bounded, that is, there exists the real A such that Cn of A is less than A to the n. This is classical results of Amitai Regev, 1972. In this case, since Cn of A is exponentially bounded, the sequence of nth roots of Cn of A is a restricted sequence, and then there exists lower and upper limits. Lower limit is called lower PI exponent x lower A, and upper limit is called upper PI exponent, respectively. One of the main problems in this numerical PI theory is the question, is it true that for any algebra A not necessarily associated with exponentially bounded codimension growth, the ordinary limit, which is called in this case just PI exponent A, exists or not? At the end of 80s, Amitsur posed the conjecture that for any associative PI algebra, its PI exponent really exists and is a non-negative integer. Later, Regev conjectured that Cn of A should have the growth of the type constant C times n to the t times A to the n for some constant positive constant C, some half integer t, and some integer A. Here, the relation f is approximately equal to g to the n, means that the limit of the fraction f on n over g to the over n is limit to the infinity is equal to 1. Main results in this area in associative case. Jambrun and myself in 2 papers at the end of 19th in the previous century confirmed Amitsur's conjecture. Alan Perel and Amitai Regev published few papers, and later Antonio Jambrun and me published one more paper. So from the results of these papers, it follows that Regev's conjecture can be partially confirmed actually we have proved that for any associative PI algebra A, there exists positive constants alpha 1, alpha 2, and integer q, and half an integer t, such that Cn of A is bounded from below and from above some function of the type alpha and to the t q to the n. Note also the interesting remark that for finite dimensional algebra, associative algebra over algebraically closed field, the following equivalence holds. Exponent of algebra A is equal to dimension of A, if and only if A is simple. In general case, if A is not finite dimensional and not simple, exponent is an integer which is strictly less than dimension of A. In Lie case, in the series of the paper, first let L be a finite dimensional Lie algebra. In the series of papers by Drambruni, Regev, and the speakers, we have shown that if L is a finite dimensional Lie algebra of dimension D, then PI exponent of L exists, and is a non-negative integer less than or equal to D. And again, moreover, as in the Lie case, exponent of L is equal exactly to D if and only if L is simple. If L is an infinite dimensional Lie algebras, then the picture is much more sophisticated. First case, when if L is a least solvable Lie algebra, let L be a Lie algebra with important commutative subalgebra, and let L squared to the D, the power D is equal to 0. Then PI exponent of L exists, is an integer and doesn't exceed D minus 1. First, our counterexample to the conjecture of Amitsur was constructed by Mishchenko and myself in 1999. It was in one paper, it was shown that there exists a finitely generated solvable Lie algebra such that lower exponent is strictly greater than 3.1, whereas the upper exponent is strictly less than 3.9. Later, this result was clarified as follows. It was by the paper of previous authors plus Andrei Vereshkin, 2018-11. PI exponent of this algebra L really exists and is approximately equal to this number, 3.6 and so on. Actually, this is PI exponent is the root of some polynomial of the power of degree 3. I mentioned Kac-Moody algebras. If L is an affine Kac-Moody algebra, then PI exponent XPL exists and also is an integer. It follows from few papers by speakers in the end of 19th and beginning of the 2000th century. Simple Lie algebras infinite dimensional of Cartan type. First, let WK will be the Lie algebra of derivations of polynomial ring in K variables. Then, if K is equal to 1, then PI exponent of W1 exists and equals to 4. This is the result by Sergei Mishchenko, 1984. For K equals to 2, PI exponent formally either it was not proven that the PI exponent exists, but it was shown that lower PI exponent is strictly greater than or equals 13.1, while upper exponent is less than or equals 13.2. This is the result of Sergei Mishchenko Jr. It was proved 10 years ago. In general, there is no conjecture formulated by Viktor Petrogradsky that PI exponent of WK for any K integer, real positive integer K exists and equal to this value. This value is fractional for any K except K equal to 1. Lie superalgebras case. Examples of superalgebras with integer. First, I present examples of superalgebras with integer PI exponent.
If L is orthosymplectic algebra, Lie superalgebra OSP 1, 2 of dimension 5, then PI exponent of L exists, and this is equal also to the dimension of this simple Lie superalgebra. This is one of the smallest simple Lie superalgebras. There is a conjecture that any simple Lie superalgebra consists as a subalgebra or either SL2 or OSP 1.2, but this conjecture is still open. If L is Lie superalgebra with the important commutative subalgebra, namely L squared to the d plus 1 is equal to 0, then exponent of L exists is an integer and doesn't exceed 2 to the d, 2 times d. And this upper bound is twice more than for ordinary algebras, and it can be really realized. This is a result by Mishin and Petrogradsky. Another example of Lie superalgebras with the existence and integer PI exponent is class of algebras of the type when L is the J of H, where H is a finite dimensional simple Lie algebra with some Z2 grading, and G of H is so-called Grassmann envelope of H. This is an infinite dimensional Lie superalgebra, and exponent of this Grassmann envelope always exists and equals to the dimension of previous initial finite dimensional simple algebra H. This is result by Repov and the speaker 2013. What about simple Lie superalgebras? There is a class of the situation picture is quite different for Lie superalgebras. Maybe I will not show in details what does it mean. There is the class of Lie superalgebras, finite dimensional Lie superalgebras, which is called in Katz-Moody notation as P of T, in the Katz notation, sorry. This is the subalgebra of 2T times 2T matrices of this type, which is written on the screen. And this algebra is simple and with L0 and sub L1 component, even a not component of this type, block diagonal of diagonal blocks, square matrices of the size T special type. Product is defined as usual for Lie superalgebras starting from associative superalgebras. This algebra P on T is simple for all T starting from 3. For P of 2 is not simple, but it looks very close like P of T in general case. And theorem first initially proved 9 years ago by Antonio Giambron and myself that PI exponent of L exists and is strictly less the dimension, which is the dimension is equal to T squared minus 1, while exponent is strictly less. This is it was first example of simple non-associative finite dimensional algebra such that exponent exists but is not equal to the dimension of simple algebra. For P on T, we can prove that PI exponent of this Lie superalgebra P of T lies between 6.28 and 6.37. And the dimension is equal to this algebra to T. In the next paper by Repov and me, we have proved that so-called graded PI exponent of P of 2 is really fractional non-real number, that it's equal to 3 plus 2 squares of 2. Jordan algebras and superalgebras. In the series of papers by Antonio Giambron, Ivan Shestakov, and myself, it was shown that for any finite dimensional Jordan algebra A, its PI exponent XA exists, and is also an integer.
Moreover, also in this case, exponent of A is equal to dimension of A if and only if A is simple, of course, under assumption that F is algebraically closed. In Jordan superalgebras, situation is close to the case of these superalgebras. Namely, there is the series of algebras which is denoted by H on MTT-TRP. This is algebra consisting of matrices of the type zero component, even component, contains all diagonal matrices A transpose. All diagonal component is odd component, where B and C are not any but algebra matrices of this symmetrical, skew-symmetric transpose composition with the natural Jordan product of elements, homogeneous elements, which is written below. And recently, the following result was proved by Shestakov and me. This paper is accepted in the Israel Journal of Mathematics and will appear soon. That PI exponent of this simple Jordan superalgebras exists and doesn't exceed the t squared plus t times square root of t minus 1. In particular, exponent is strictly less than dimension, which is equal to t squared. In general non-associative case, first of all, I mentioned that any real alpha can be realized as a PI exponent of some non-associative algebra. Namely, in the paper by Academician and myself, it was shown that for any real alpha, there exists an algebra R sub alpha such that PI exponent of this R sub alpha is equal exactly to alpha. Note that the problem of existence of PI exponent has a negative solution. It was shown in my paper in 2014, where I constructed the series of counterexamples. Namely, for any real alpha greater than 1, it was constructed an algebra A sub alpha such that the lower PI exponent is equal to 1, whereas the upper PI exponent upper limit is equal to alpha. So the drop is maybe huge between real and lower and upper exponents. What about finite dimensional algebras? Recall that if dimension of A, some in general non-associative algebra, is equal to D, then the dimension Cn of A is bounded by D, the exponential function d to the n minus 1. It was first shown by Yuri Bakhturin and Vesselin Drensky, even in more general case. And there is a conjecture that for any finite dimensional algebra A, its PI exponent does exist, but it's still an open question. We can say only that if A be a finite dimensional simple algebra, then as it was shown by Antonio Zambron and me in 2012, its PI exponent always exists. So for finite dimensional simple algebras, the conjecture is true. Recall again that for associative Lie and Jordan algebras, PI exponent of simple algebra coincides with its dimension, whereas if A is a Lie superalgebra of Jordan, simple superalgebra, then exponent of A may be strictly less than the dimension. Interesting series of examples of simple algebras were constructed by Mishenko and Oksana Bogdanchuk. This result can be formulated as follows: the theorem for any m integer m greater than or equal than 3, there exists a finite dimensional simple unitary algebra A sub m of dimension m, such that exponents of these algebras exist and strictly increase the lowest one, exponent of A3 is equal to 3, which is strictly less than a exponent a4 and so on, strictly less than a pi exponent of am, up to the 4, and the limit of exponents of this algebras am is exactly 4. Few words about over exponential growth. Recall that for any integer t starting from 2, there exists a Lie algebra L such that Cn of L is approximately n factorial on the degree, which is a fraction t of minus 1 over t. This is a result, mentioned result by Petrogradsky in 1995. On the other hand, there are no examples of Lie algebras with over exponential growth, per dimension growth, strictly less than square root of n factorial. So it implies the conjecture that given a Lie algebra L, either the sequence Cn of L is exponentially bounded, or Cn of L grows faster than square root of n factorial. If we consider general non-associative case, not only Lie, then Jambrun and myself in 2018, we have shown that for any real alpha, positive real alpha less than 1, there exists an algebra A sub alpha such that Cn of A alpha grows approximately as n factorial the power of alpha. So previous conjecture for general non-associative case is wrong. Okay, maybe I will stop on this place. Thank you very much for your attention.
Let's thank Professor Zaitsev for the interesting talk. Are there any questions or remarks, please?
I'd like to ask whether there's a similar result concerning alternative algebras.
Actually, in our paper, Antonio Jambrun and myself and Shestakov, we tell a few words. There is some generic case when finite dimensional algebras has a similar property. In particular, we can say that if an alternative algebra has a finite dimension, then its pi exponent exists and it's also an integer. For infinite dimensional, I don't know.
Other questions or remarks, please? If no, then let's thank again Professor Zaitsev. And next talk is after 8 minutes.
I'm not able to make it full screen. Can somebody help? What is
Control L, if I'm not wrong.
Control L?
Yes.
It seemed to work. Ah. And if I scroll down, does it move?
Yes, it
Do you
does.
see a new page now?
It moves.
Okay.
Yes, Professor
Okay.
Dom.
Thank you. Thank you.
Let's wait 5 more minutes in order to start on time.
Yes, yes, sure.
I suppose you don't mind that.
Of course, I don't mind. I just have some trouble with.
Our next speaker is Professor Matjaž Domokos, and he will talk on invariant theory of varieties of associative algebras, degree bounds. Please take the floor, Professor Domokos.
Thank you. And I thank the organizers for their efforts that made this conference possible. In the opening ceremony, Plamen Koslukov mentioned that Vesselin Drensky, in addition to his official students, had a number of unofficial students. And I think I may qualify as one of those unofficial students, because when I started my PhD in Budapest, there was a fresh discovery of new polynomial identities of matrices by Hungarian mathematicians Jenő Szigeti, who will speak later today, Gábor Révész and Zsolt Tuza, and I was advised to start to work on this promising topic. However, the theory of PI-algebras was not a well-established branch of algebra in Hungary. So we started to read some papers, for example, lecture notes by Edward Formanek. And it was very fortunate to me that just at that time, Vesselin paid a short visit to Budapest. And later I had some longer visits to Sofia, where I learned a lot from him. And I enjoyed his warm hospitality and the hospitality of the Institute of Mathematics and Informatics of the Bulgarian Academy of Sciences, and got to know some other Bulgarian mathematicians. Well, I am not alone. As we heard in this conference, several colleagues told us about similar experience. And our cooperation with Vesselin continued over the years. I hope it will continue in the future. So God bless you, Vesselin, and let me say also in Hungarian, Isten éltessen. Now, the talk illustrates also what I've said, because it's about joint work with him. The title is Invariant Theory in Varieties of Associative Algebras, with a special focus on degree bounds. Of course, degree bounds for generators of various algebras of invariance. The basic setup is the following. We fix a field K of characteristic 0. G will be a group, V a finite dimensional K vector space. We shall denote the basis elements as x1, x2, xn. We take a representation rho of G on the vector space V. And then we have a naturally induced action of G on the tensor algebra of V, and also on the symmetric tensor algebra of V via graded K-algebra automorphisms. The tensor algebra of V is nothing but the free associative K-algebra on n generators, where n is the dimension of the vector space, and the symmetric tensor algebra is, of course, the commutative polynomial ring with n indeterminates. So these two are two extreme cases of so-called relatively free algebras. The tensor algebra is the free algebra in the variety of all associative algebras, whereas the symmetric tensor algebra is the relatively free algebra in the variety of commutative algebras. So more generally, we fix a variety R of unitary associative algebras. So this is just the class of algebras satisfying a given set of identities. The set of all identities satisfied by the variety will be denoted by I of R. This is a T ideal in the free associative algebra of countable rank. And to get a relatively free algebra of finite rank, we take the intersection of this T ideal with the free algebra in n indeterminates, where n is the dimension of the vector space, and take the factor of the tensor algebra modulo this ideal. Since this ideal IRV is GLV stable, hence G stable, so the action of G on the tensor algebra induces an action on the factor algebra FRV, on the relatively free algebra. And we take the set of those elements in the relatively free algebra, which are fixed by all group elements. This is obviously a subalgebra. So we have this picture that we have the tensor algebra of V, which surjects onto the relatively free algebra FRV, which surjects onto the symmetric tensor algebra of V. because we consider algebras with unity. And when we restrict to the subalgebra of G invariants, we again get surjections because GLV acts completely reducibly on the tensor algebra, while provided that the characteristic of K is 0. So we can think of the problem of studying invariants in the relatively free algebras. We lift somehow the commutative invariant theory we have when we look at SVG. Now, to discuss degree bound, I need to set up some notation. So given a finitely generated graded algebra A, graded by the semi-group of non-negative integers, we shall denote by beta of A the minimal non-negative integer D such that A is generated by its elements of degree at most D. So in particular, in the special case when we take the algebra of G invariants on a commutative polynomial algebra, where we consider the standard grading, so the variables all have degree 1, and the degree bound for the generators of the corresponding algebra of invariants, we will call this the Noether number for the G module V. And this Noether number has a global version where we take the supremum of these numbers as V ranges over all possible G modules. This will be denoted by beta of G. Now let me recall some classical results from the commutative theory. So whenever a finite group acts on a polynomial ring via linear substitutions of the variables, the corresponding algebra of invariants is always finitely generated. So this holds also in positive characteristic in the modular case when the characteristic divides the group order. This was proved by Emmy Noether in 1926. And in fact, 10 years earlier, she already proved that in characteristic 0, where we always have that the algebra of invariants is generated by elements of degree at most the group order. So with this notation just introduced, the statement here is that beta of G is less than or equal than the order of G. Some side remarks about some more recent developments related to this classical theorems of Noether. It turns out that the bound that beta of G is at most the group order holds also in positive characteristic, provided that the characteristic does not divide the group order. This was proved by Fleischmann and Fogarty independently. Another comment is that Noether's degree bound is sharp in the sense that beta G of G equals the group order for when G is cyclic. But Barbara Schmidt proved that this is the only case. So whenever G is not cyclic, then beta of G is strictly less than the group order. And among other things, she also proved that the Noether number is monotone in that sense that if H is a subgroup of G, then the Noether number, the global Noether number for H is less than or equal than the global number for G. In fact, Schmidt's paper contains some nice reduction steps, which was designed to prove that something like that the Noether number is bounded by a constant multiple of the group order, and the best possible constant is 3/4. This is shown already by Klein's 4 group, and this indeed holds. So the Noether number for a non-cyclic group is at most 3/4 times the group order. And also, if we look at this monotonity result, it says that one reason for having large Noether number is that we have elements of large order. So in this philosophy, it turns out that the Noether number is always strictly less than 1/2 of the group order, unless G contains a cyclic subgroup of index at most 2. So this is not 100% true because there are 4 small groups which have larger Noether number, which have Noether number at least half the group order and do not have cyclic subgroup of index 2, but the largest among them is the binary tetrahedral group A4 tilde, which has order 24. Okay, now our philosophy is that we view these theorems of Noether as a statement about the variety of commutative algebra. And now we replace the variety of commutative algebras with an arbitrary variety of associative algebras, and may ask whether corresponding theorems hold. And this question was answered by Harchenko in 1984, because he proved that the varieties in which it's true that whenever a finite group acts on a finitely generated algebra from the variety via algebra automorphisms, then the corresponding algebra of invariance is finitely generated. These are exactly the weakly Noetherian varieties. So the varieties in which each finitely generated algebra is weakly Noetherian, where weakly Noetherian means that we have the two-sided ascending chain condition for two-sided ideas. So such varieties we shall call weakly Noetherian varieties. So this was what we knew when we started our work. And on the other hand, this theorem of Harchenko leaves open the question about degree bounds. So now let's fix a variety and a finite group G, and we may ask if there exists Noether number for G in this variety. So I shall denote by beta of G R and call the Noether number of G in the variety R the supremum for the degree bounds of the generators of the relatively free algebra of the algebras of invariance in the relatively free algebras associated to the G modules V, where V ranges over all possible G modules. And then the natural question is that if R is a weakly Noetherian variety, is it true that for any finite group G, the Noether number of G in this variety is finite? And if the answer is yes, then of course we would like to get explicit bound for this Noether number in the variety in terms of the group or the group order and some numerical invariance of the variety. It turned out that some notable quantities of PI theory play a role here. So first, Lvov in 1969 proved that any weakly Noetherian variety R satisfies a multi-homogeneous polynomial identity, which is of the following form. It depends on three variables. And it says that for sufficiently large n, x2, x1 to the n plus 1, x3 can be rewritten as a linear combination of monomials where each monomial is divisible by x1 either from the left or from the right. The minimal such n we shall denote by n of R. The other quantity comes from Latishev in 1966 proved that the commutator idea of any relatively free algebra of finite rank in a non-matrix variety is nilpotent. Non-matrix variety means that the algebra of 2 by 2 matrices does not belong to this variety. Weakly Noetherian varieties are such. So we denote this nilpotency index as LRD for the relative, so this is the nilpotency index of the commutator ideal of the relatively free algebra of rank D. And finally, we have this so-called Dubnov-Ivanov-Nagata-Higman theorem, which says that any nil algebra of bounded nil index n is also nilpotent. Equivalently, the T ideal generated by x to the n contains the product x1, x2, and so on xd, and the minimal such d, depending on n, we will denote it as nu of n. And what we know about nu of n, that it's less than or equal than n squared, thanks to Razmislov, and it's greater than or equal than n times n plus 1/2 by a result of Kuzmin. So it's close to n squared. And it turns out that the answer to question 1 posed above is yes. So it's true that for any, if R is a Wittgensteinian variety and G is a finite group, then if we take all G modules, we take a G module and take the corresponding action of G on the corresponding relatively free algebra via linear substitutions of the generators, then the corresponding algebra of invariance is generated by elements of degree bounded by some integer. And in fact, we worked out an explicit such bound for this Noether number relative of G relative to this variety. Well, maybe it's complicated to read, but the ordinary commutative Noether number of G is involved. This number L from Latishev's theorem, so the nilpotency index of the relatively free algebra of the variety whose rank equals the group order. These are put in the argument of the Nagata-Higman theorem, and also this N of R, this number coming from the special identity satisfied by the variety, it also appears in the argument of the Nagata-Higman function. I just wrote down what this implies if we use, instead of nu, the bound from Razmislav's theorem, then it's slightly easier to read this bound. This statement works also for finite abelian groups, but for finite abelian groups, we found a second approach which yielded a somewhat different bound, which, depending on the variety of the group, it might be sometimes better. So in that case, we don't need to take into account the nilpotency index of the commutator ideal of the relatively free algebra. On the other hand, we really need the group order here. So in our proof, it cannot be replaced, say, by the Noether number of G. The Nagata-Higman function and the degree bound for this special kind of identity satisfied by the variety coming from the theorem of Lvov, it appears in the same way as before. So that's about finite groups. Now let's turn to infinite groups. But whenever G is infinite, then there is no finite global Noether bound. So this was observed by Derksen and Kemper. So as soon as G is an infinite group, for an arbitrarily large integer d, G has a G finite dimensional G module V such that the corresponding commutative algebra of invariants needs generators of degree greater than d. Of course, for a concrete G module V, the algebra of invariants might well be finitely generated. In fact, say for reductive groups, this is always the case. And the question is that perhaps there are some reasonable classes of G modules such that we can define a global Noether number relative to that class of G modules. And for reductive groups, there is such a suggestion. So denote by tau a finite set of simple G modules. And by at tau, the additive closure of tau. So these are finite direct sums of modules from tau. And then let's call the Noether number of G relative to tau the supremum of the degree bounds for the algebras of invariants corresponding to the representations from this class at tau. So we have infinitely many different representations here. We can have dimension, arbitrarily large dimension, but still this Noether number of G relative to this class tau is finite. This is an easy corollary of Weil's theorem on polarizations. Now let's turn again to the case of relatively free algebras. While in the case of finite groups, weakly Noetherian varieties were the good varieties, it turns out that here we need to consider linear potent varieties. So varieties of associative algebras that are linear potent of some fixed nilpotency index P. So let's denote by n sub P the variety of all linear potent associative algebras of nilpotency index at most P. It means that an algebra belongs to NP if and only if all Lie brackets of length at least P plus 1 are 0. Now, if we have such a linear potent variety, then it is true that for any G module V, the algebra of invariance of G on the corresponding relatively free algebra is finitely generated. And also this statement has a converse. So whenever we have a relatively free algebra of rank at least 2, which has the property that for all reductive groups G which act on this relatively free algebra via linear substitutions of the generators, then the corresponding algebra of invariance is finitely generated. This forces that the variety has to be linear potent for some nilpotency index P. It's important to remark here that the condition that a variety is linear potent implies that the relatively free algebras of finite rank are Noetherian, left Noetherian, by an old theorem of Latyshev. So the classical argument of Hilbert about finite generation of algebras of invariance of reductive groups in the commutative case goes through in this setup without essential changes. But still, I think it has some interest that in the commutative case, the argument for finite groups and reductive groups is not different. Noetherianity appears in the same way in the two proofs, whereas here, it seems that Noetherianity plays somehow a different role. For the finite group case, a weaker version of Noetherianity was sufficient. Now let's turn to the question about degree bounds. So now again, we take this philosophy that if we fix the variety R, well, the reason is to fix a linear potent variety R, and we can define the Noether number of G in the variety R relative to tau, where tau is a finite set of simple G modules in an analogous way as in the commutative case. And we might ask that, is it true that just like in the commutative case, this new Noether number will be finite? And it turns out that the answer is yes. Namely, what happens is that we start with tau. We can define a new class of simple G modules, which is bigger. Namely, we take, I denote it by the P tensor power of tau. So we take all tensor products of at most P elements from tau, and they take the simple summands of such modules. So this is the P tensor power of tau. Then we know that we have this finite Noether number for G with respect to this new class of simple modules. And we have an upper bound in terms of that number for the degree bound relative to tau in the variety R. In the commutative case, the finiteness of these Noether numbers relative to tau was a consequence of Weil's theorem on polarizations. Here, the situation is different because Weil's theorem on polarizations does not seem to generalize for linear potent varieties. In fact, there is a natural generalization of Weil's theorem on polarization, but it works for varieties satisfying a Capelli identity. And typically, a linear potent variety does not satisfy the Capelli identity. So there's a different approach here. So I just stated the degree bound, but in fact, it's a consequence of a process by which we can construct generators of these algebras of invariance. And this construction works for arbitrary groups, not just for reductive groups. So let me turn to this. So we have fix P a positive integer and a variety R, which is linear potent of index P. and an arbitrary subgroup G of GLV. And what we will do is that, so we have this G module V. Now we assign to this G module V another G module in a somewhat canonical way. This will be denoted by W. And we solve the commutative invariant theory problem for W. In other words, we find generators of the algebra of G invariants in the symmetric tensor algebra of W. And using generators of that algebras, we can give explicit generators of the non-commutative algebra of invariants in the relatively free algebra generated by V. So it goes in the following way. Let's denote by V to the D the linear span in the tensor algebra of the Lie brackets of the variables of length D. So we have these finite dimensional subspaces, and I take the direct sum of these subspaces as D ranges between 1 and P. And let's call this W. So this is clearly a G submodule. It's a GLV submodule of the tensor algebra. It's a finite dimensional GLV submodule of the tensor algebra. And then take the tensor algebra of this W. This is a multigraded algebra. It's naturally multigraded by p tuples of non-negative integers. Namely, if we think of this TW as a free algebra, then we have one group of variables which belong to V to the 1, another group of generators which belong to V to the 2, and so on, a group of generators which belong to V to the P. And we count the degrees with respect to each groups of variables separately. That's how we get the multigrading. Now, W, by its definition, is a subspace of TV. Therefore, the embedding of W into the tensor algebra of V extends to a GLV equivariant algebra surjection from the tensor algebra of W onto the tensor algebra of V. And then the tensor algebra of V surjects to its homomorphic image the relatively free algebra in the variety R generated by V. So let's denote by pi this composition. So pi is a GLV equivariant algebra surjection from the tensor algebra of W onto the relatively free algebra FRV. Finally, I need to mention that, of course, the symmetric tensor algebra of W is multigraded in the same way as the tensor algebra of W. And if we take a multi-homogeneous component of multi-degree alpha in the symmetric tensor algebra of W, there is a natural GLV equivariant embedding of this component into the multi-homogeneous component of multi-degree alpha in the tensor algebra. We just send a product of generators to the corresponding symmetrized tensor. And then with these notations, the following statement holds. So suppose that we take this commutative algebra of invariants G acting on the symmetric tensor algebra of W, and take the action of G respects the multigrading introduced above. So this algebra has this algebra of invariants has a multi-homogeneous generating system. So take such a multi-homogeneous generating system. Now, each such generator can be lifted to an element of the free, to the tensor, non-commutative tensor algebra of W via this symmetrization operator. And then we can push down these elements from the tensor algebra of W to the relatively free algebra by using this surjection pi introduced above. And in this way, we get, if we start with the elements of the generators of the commutative algebra of invariants, we get a bunch of elements in the relatively free algebra, and we claim that these elements generate the algebra of invariants in the relatively free algebra. So we get, because of the construction, we get invariants, and they will generate the resulting algebra of invariants. In fact, these will be homogeneous generators. So this statement follows from a somewhat more general statement about algebras of invariance in universal enveloping algebras of Lie algebras. So let's turn to that. So let now L be a finite dimensional Lie algebra, and G is a group of automorphisms of this Lie algebra. Then the action of G on L via Lie algebra automorphisms induces an action of G on the universal enveloping algebra of L via K algebra automorphisms. Recall that there is a K vector space. Now we take the symmetric tensor algebra of L and the universal enveloping algebra of L, and there is a well-known K vector space isomorphism between the symmetric tensor algebra of L and the universal enveloping algebra of L. This is called the canonical bijection in Dixmeyer's book. First, we go from the symmetric tensor algebra to the tensor algebra via this symmetrization. And then we have the natural surjection from the tensor algebra of L onto the universal enveloping of algebra of L, as it is usually defined as a factor of the tensor algebra. The composition of these maps, this is the canonical, this gives the canonical bijection, and that this is a vector space isomorphism. This is essentially the Poincaré-Berkowitz theorem. But interesting thing is that this is a vector space isomorphism, but it's not an algebra homomorphism. But despite this, it turns out that if we start with, so we take the algebra of G invariants in the symmetric tensor algebra of L, and take homogeneous generators of this algebra, under the canonical map, this canonical linear map, these generators of this commutative algebra of invariants are mapped to generators of the algebra of G invariants in this usually non-commutative universal enveloping algebra of L. So this is looks strange because omega itself is not an algebra homomorphism. However, this is true, and the proof is not long. And this can be applied in our situation as follows. So note that, now let's go back to the tensor algebra of a vector space V. And if you take the direct sum of all these subspaces of V to the D, so let me remind you that V to D consisted of Lie brackets of generator of length D of the generators of the tensor algebra and the linear span of those Lie brackets. So this is just the free Lie algebra of rank dim-V. And if we factor this free Lie algebra of length D by the direct sum of those V to D where D is greater than P, this can be identified with the free linear potent Lie algebra of nilpotency index P. So let's call this free linear potent Lie algebra LPV. But so in this way, this vector space is naturally identified with this space which we call W before. So the tensor algebra of W can be thought of as the tensor algebra of the free linear potent Lie algebra, and the symmetric tensor algebra of W as the symmetric tensor algebra of the free linear potent Lie algebra. So this previous statement about universal enveloping algebras of Lie algebras can be applied and is relevant for our context because GLV is a subgroup of the automorphism group of the free Lie algebra. So by the previous statement, from we can get generators of the algebra of G invariants in the universal enveloping algebra of this free linear potent Lie algebra. On the other hand, by the free property of the free Lie algebra, the identity map from V to V extends to a surjective Lie algebra homomorphism from the free Lie algebra onto the Lie subalgebra of the relatively free algebra of V in the variety generated by V. And this extends to an algebra homomorphism from the universal enveloping algebra of the free Lie algebra onto the relatively free algebra. And since the image of this homomorphism gamma contains the K-algebra generating system of the relatively free algebra, therefore this gamma is surjective onto the relatively free algebra and also GLV equivariant. Therefore, the algebra of invariants in this universal enveloping algebra is mapped onto the subalgebra of invariants in the relatively free algebra. So that was, that's how we get a proof of this statement. Yeah. I think that was all that I want to say about degree bounds, but finally, let me mention briefly results of different kinds. So it's no longer about degree bounds. It's about the Hilbert series of algebras of invariants of groups acting on relatively free algebra. So the Hilbert series of the algebra of invariants is just a formal power series in which the degree D coefficient gives the dimension of the degree D homogeneous component of the algebra of invariants. And it turns out that for any proper subvariety of the variety of all associative algebras. So here we don't have to put strong assumptions like weak neutrality or neutrality. We can take any non-trivial variety of associative algebras. Although the algebra of G invariants on relatively free algebras typically won't be finitely generated, but the Hilbert series of the algebra of invariants is always a rational function. Yeah, so in the commutative case, we have the so-called Hilbert-Serre theorem, which says that the Hilbert series of a finitely generated graded algebra is always a rational function of that kind. So we have a polynomial in the numerator and the product of 1 minus q to some powers in the denominator. Here we don't have the finitely generated property, but still this statement holds. And this follows from, here is this example that we really need to take proper varieties, because for the free algebra, the analogous statement is not true. So for example, two variable Hilbert series of the free algebra of rank 2 is this. So it's a rational function, but if we consider the natural action of SLV on the tensor algebra, the corresponding algebra of invariants has this Hilbert series. So this was proved by Almquist, Dix, and Formanek. So this Hilbert series is no longer a rational function. Yeah. So this theorem follows from a version of a theorem of Belov due to Alain Berele. So Belov proved that the Hilbert series of a finitely generated relatively free algebra is always a nice rational function. And Alain Berele extended this result to the multigraded Hilbert series of relatively free algebras. And this can be used to prove this rationality results about algebras of invariants in relatively free algebras. So that's all what I wanted to say. So thank you very much for your attention.
Let's thank Professor Domokos for the nice lecture. Are there any questions or remarks?
I have a how the in the relatively free algebras, if you look at the maximal degree needed in order to generate the T-ideal, there is such a number which is not known in many important cases. How this number enters into the picture?
I don't know. So it hasn't entered in our investigations, and we didn't think about
in
it.
The letter, it doesn't enter at all.
So the only way so this N of R, this is about the finite group case and weakly Noetherian varieties. So this is so the degrees of certain identities showed up in our results. For example, in a weakly Noetherian identity, we took a theorem of Lvov's guarantees that there is an identity of this shape, and if we take the one in which this n here is the smallest possible, this n appeared in our bound. But of course, this is independent of your question, that what is the largest degree of an identity needed to generate the T idea. Also, in the case of reductive groups, the linear potency index P appeared in our degree bound because it was something like P times some bound coming from a commutative algebras of invariants. So the nilpotency index P played a role, but otherwise.
Yeah. In the nilpotency I see, but otherwise, okay, thank you.
But maybe it's not an answer to your question, but for example, if you just take the variety generated by this single identity, then we know that this is the maximal degree needed to generate the T ideal, and it is exactly what appears.
Right.
Or also in this case, we can start with such an identity and just take the T ideal generated by that one, and then it appears.
Okay, other questions or remarks?
Would it be reasonable to be looking at exterior products instead of symmetric products and look for invariance there?
It's certainly reasonable, and in fact, I recently saw some works about this. I don't remember the exact content. So the infinite dimensional Grassmann algebra and the T ideal of the infinite dimensional Grassmann algebra also appears in a theorem in this kind of non-commutative invariant theory, because the natural generalization of the Shepard-Todd-Chevalier theorem holds exactly for those varieties which are linear potent of index 2. So which satisfy the identity that the Lie bracket of x, y, and z is 0. So these are exactly the varieties where it's true that for any pseudo-reflection group, the corresponding algebra of invariants in the relatively free algebra is again relatively free. So isomorphic to the relatively free algebra we started with.
Okay, other remarks or questions? If not, then let's thank again Professor Domokos for the interesting talk. And now it's time for a coffee break by 16.
Thank you.
Thank you, very interesting.
Thank you. Szia, Jenő!
Szia, Matyi, nagyon jó volt az előadásod.
Igen. Most mindenki lát minket, azért azt ne felejtsük el. Na, akkor hajrá, ki is, nem is akarlak zavarni, kiszállok. Mármint, hogy itt maradok, nézlek csak.
Ja, remélem sikerülni fog ez a share screen. Egyelőre nem lehet, úgy látom. De most már lehet. Jó.
Igen, mert még eddig én voltam.
Na látod, Matyi, mit csináltam?
Igen, látom. Még azt nem akarod kirakni full screenre?
Hát ezt nem tudom, hogy hogy kell.
Hát az előbb nekem valaki segített. Nyomd be azt, hogy Ctrl-L.
Ctrl micsoda?
Ctrl-L.
Nem történik semmi.
Aha. Ez most egy PDF, vagy mi ez?
Ez egy közönséges PDF.
És nekem sem sikerült az előbb, hogyha fölmegyek a menübe, izébe a PDF-nél, akkor ugye van elvileg egy olyan, hogy View, és ott azon belül van a full screen mód, de az előbb én sem láttam azt, és akkor...
És hol van ott, ahol fölmész a menübe? A oldal megtekintésnél? Nem, ott egy oldalas. Most jobb lett?
Hát, jó, hát most kisebb rész látszik belőle, de most nem tudom, te egy laptopról csinálod ezt?
Nem, itt van számítógépről.
Everything is okay, you know. Nice to meet you.
Hello, Czetka, hello.
Hello. Everything is okay with your text.
Yes, but I think it's not full screen mode. And
it was just some minutes ago. Just some minutes, it was a full screen.
Mm-hmm.
Now it's
yes,
better.
Now it's okay. Okay.
I'll try this one.
Okay, hello everyone. It's time to start our afternoon session after the coffee break. So our next speaker is Yeniu CDT, and he's going to talk about solving equations in the symmetric group. So please.
Thank you. And it is a great pleasure to take part in this conference dedicated to Vesselin Drensky's anniversary. And I thank the organizers for giving me a possibility to present a talk here. And the most important thing is that I wish many, many more years to Vesselin, full with brilliant results. So my talk is about solving equations in the symmetric group. And my name is Jenő Szigeti, and I am from the University of Miskolc, Hungary, and the same is valid for my co-author. So the solving equations is the starting point of algebra, and there is a well-known history of equation solving, starting from Cardano and then Tartaglia and so on and so on. So it is really a natural idea to consider equations in groups. Of course, we have only one binary operation, and we can use the inverse. It is very surprising that I found only a limited number of results about explicit solutions. There is a good number of papers about algorithmic approach, but I did not find really results about explicit solutions. One of the earliest results, it is due to Frobenius, about the number of solutions of this equation x to the power m equal to 1. And the result says that if the order or the number of elements of the group is divisible by m, then the number of solutions of this equation is also divisible by m. There are many different proofs of this classical result. One is from Isaacs and and Robinson. This is maybe the most understandable and the simplest proof. There are some other results about these equations in the symmetry group. Don't forget that the symmetry group is one of the most important finite groups and consists of all permutations. A general equation containing constants and group operation for a single unknown permutation is here. And I can say that the degree of this equation is k. Here we have exponents. The alphas are the constants and the exponents are r1, r2, rk. The exponents are +1 or -1. Of course, we can assume that the first exponent is +1. Otherwise, we can rewrite this equation for the inverse, and then the new first exponent will be +1. So it is a natural assumption that the first exponent is 1. And the first impression is that to solve this equation in general in the symmetry group or in other groups is hopeless. And we'll see that even in the low degree cases, the problem is not easy. So the quadratic case, the easiest case, when k is equal to 2, we have two possibilities for the exponents. So here is the first possibility, and here is the second possibility for the exponent. Here is +1 and +1, the two exponents. Here, +1 and -1, these are the exponents. In the first case, we can rewrite this equation in this form. And to solve this equation means that we have to extract a square root of this permutation in the right side. And to extract a square root from a permutation is not difficult. I used to give it as exercises for my students. So we can extract a square root from a permutation if and only if for any I, the number of cycles of length 2i is even. So of a given even length must appear even times in the permutation, and this is necessary and sufficient for extracting a square root. And after extracting a square root from the right side, then we can get x easily. So this is the first case, and the second case is even more easier. Then this equation can be written as in this form, and here x is the unknown. So it has a solution if and only if the permutation alpha sub 2 and alpha sub 1 and the inverse of alpha sub 1 are of the same type, or are of the same in the same conjugacy class. So this is easy to check that whether they are in the same, they have the same type or not. So and to find all the solutions in the first case and also in the second case is not difficult. So there is no sense to go into more details. The situation in the case when the degree is greater than 2. So don't forget, here is the equation. Here is our equation. This is our equation. And if the degree k is greater than 2, then the problem is difficult. A nice summary about the general situation about the equations can be found in Lindman's paper, an early paper. And an important direction of research in this problem is to find the solutions of the given equation, not in the base group, but in an extension, in an appropriate extension of the base group. There is a more or less well-known conjecture, the Kervoar-Laudenbach conjecture, that it asserts that if the length, this is the sum of the exponent of this equation, is non-zero, we consider this equation over an arbitrary group, then this equation has a solution in a group H containing G. Here, of course, we assume that if one of the coefficients is 1, then the two coefficients preceding the two exponents preceding the coefficient and following the coefficient, the sum is not 0. In this case, when we talk about the Kerr-Laudenbach conjecture, we assume this. There is a general extension theorem of Gerstenhaber and Rothaus, and about finite groups, and it has a consequence that this conjecture holds for all finite groups. For k equal to 5, the conjecture was solved by Evangelidou not long ago, but for other cases, the conjecture is not solved. But it is not the problem that I want to present, because it is about the extension, about finding the solution in an extension of the base group. So here I consider the cubic equation. This is the cubic equation, and I try to present results. I try to solve it. Of course, the full solution is I am far from the full solution. So if we consider this equation, then we can rewrite this equation. And we have 4 possibilities according to the choice of these exponents. So here are the 4 possibilities. The exponents are 1, 1, minus 1, 1, minus 1, and plus 1, 1, minus 1, minus 1, and finally plus 1, plus 1, and plus 1. These are the 4 possibilities if we start with if the first exponent is equal to 1. And it is easy to check that these equations can be rewritten in the following forms. Alpha times y times beta equal to y squared. This is in the first case, and alpha and beta as here, and now the new unknown is y, which is x times alpha 2. And similarly, the other equations also can be rewritten in this form. Only the 4th equation, this one, when all the exponents are plus 1, can be rewritten in a different form. Here the exponent is minus 2. So we can focus our attention to these 2 equations, and it is enough to solve these 2 equations to get the general solution of the original cubic equations. But here we were not able to attack these problems, so we made an assumption, an extra assumption, which is maybe natural. So we assumed that y equal to 1 is a solution of these equations. And of course, if we assume that it has at least one solution, it is more general and it is a weaker assumption, but it was not enough to attack this problem. So if we assume that y equal to 1 is a solution of this equation, of the first one or of the second one, then it means that the second constant beta here is the inverse of alpha. So if we substitute 1, then alpha times beta equal to 1, it means that beta is the inverse of alpha. And using elementary combinatorial argument and basic number theoretical facts, we can obtain results about the solution of the first equations, star alpha, and the 2 star alpha also. We prove that in some cases we have only one solution, y equal to 1, and there are other cases, of course, depending on the structure of cycle structure of alpha, then we have many solutions. And we can prove similar results for the second case, for the second equations, only a bit weaker results. So let us consider the so-called conjugate equation of this form. The first remark is that the conjugation is an automorphism of the symmetric group, so the solution, the number of solutions depends not only on depends only on the conjugacy class of alpha. So it is an important observation. And now we need some definitions. Of course, everyone knows what is the type of a permutation. Here, G sub I denotes the number of cycles of length I in alpha. So this is the type of a permutation. And for an integer D, we define a set of integers. I called it the D range of alpha. And what is this? How can I explain this? Consider or take some distinct cycles of alpha, such that each of the considered cycles, the length is divisible by D, and add the length of these cycles, and do it every possible way, and we'll get this set. This is the sums of these cycle lengths. So don't forget that here we consider only cycles having length divisible by D. And now, using this set, maybe this set is not really transparent, but it will be enough for us to make really explicit statements about the solutions. And the first theorem about the equation, about this one-star equation, is the following. If we have a permutation, and here is the type of the permutation, and we assume that for any odd integer and for any D, such with this property that D times R is in this set, in this range, then we have GD equal to 0. It means that there is no cycle of length D, and we have that the greatest common divisor of 2 to the power D minus 1 and R is equal to 1. If we have such a condition for all D and for all R, then equation 1-star alpha has only the trivial solution. Unfortunately, this theorem seems to be not transparent, but it is enough to obtain more transparent results. The second theorem is somehow a consequence of the first one, and it is absolutely visible, so we can see the conditions. Let alpha be a permutation with type G1, G2, Gn, and assume that there is no fixed point of the permutations. It means that G1 is 0. And for all A less than B, such that A and B are cycle lengths, it means that GA and GB are not equal to 0, then A and B are relatively primes. So we can formulate it in a more understandable way. Two different cycle lengths of the permutation are relative primes. And also assume that if A is a cycle length, GA is not 0, of alpha, a cycle length of alpha, it implies that the number of cycles of length A is between 1 and 2. So GA not equal to 0, that it means that we have a cycle, and this means that we have at most 2 cycles of this length. And we also assume that this power of 2 to the power A over P minus 1 is not divisible by P, and it is true for any prime divisor of A. Here it is an integer. P is a divisor of A. And P is greater or equal than 3, the prime divisor. If we have such a permutation, then the equation star, here is the equation, the conjugate equation, has only the trivial solution. And of course, we can easily check the conditions in this theorem. And now it has a corollary, a simple corollary. If alpha is a cycle, is a full cycle of length n in Sn, this is a cyclic permutation, and we know that 2 to the power n over p minus 1 is not divisible by p for any prime divisor p of n, then our equation, our conjugate equation, has only the trivial solution. This is a corollary of the previous theorem. Of course, it is easy to exhibit an example. N equal to 3 times 5 times 11 is an example of such an integer. So in order to prove these theorems, we need some combinatorial arguments and some basic number theory, but we do not use any advanced things. So we use only elementary things. And now, the next thing is the converse of this corollary. So here is our conjugate equation again, and assume that p is a prime divisor of the integer, such that this power, 2 to the power n over p minus 1, is divisible by p. And if we consider this cyclic permutation, then our equation has a non-trivial solution. And the proof of this theorem is explicit. We can construct the solution. We can construct a solution of order p, of this order. And it is also easy to exhibit examples. Such integers are 6, 20, 21. Here is the explanation. So the proof of theorem B1 is absolutely constructive. So we have to construct the solution. And now the next theorem is about the complete solution of the equation in the case when it has non-trivial solution. Of course, when we prove that it has only the trivial solution, then it means that it is a complete solution of the problem. But here in theorem B2, we have a different situation. If p greater or equal than c is a prime divisor of 2 to the power of 2 to the power m minus 1, and we take n equal to p times 2 to the power m, and consider this cyclic permutation, then we can determine all of the solutions of star alpha. Of course, the previous theorem works, so we know that it has a solution, but here we can exhibit all the solutions. And the theorem says that if we have any solution y, which is non-trivial, then the powers of this y give all of the solutions. These powers is the complete set of solutions of the equation, of the conjugate equation star alpha. And of course, we can easily exhibit an example again. If n equal to 6 and p is equal to 3, then it is a special situation, special case of B2, and here are the solutions. It is easy. And of course, we can take one more step. Here, I can say it is a proposition. If n equal to 12 and we consider this permutation, which is the product of two cycles of length 6, then we can give all the solutions of this equation of our conjugate equations. Here are the solutions. We have 8 non-trivial solutions and 1 trivial solution. So the first 2 solutions commute, and the powers of the first 2, the third powers of the first 2 solutions are equal to identity, and the 9 solutions, we have all 9 solutions can be obtained in this form. So this is just a easy consequence of the previous corollary, and of course we need some calculations And now the other equation was the other conjugate equation looks like this: y times alpha times y times alpha inverse is equal to alpha to the power -1. And this equation is more difficult than the equation with +1. Our first observation is that let us try to find a solution. Observation partially explains why we have only weaker results about the solutions than in the first case. So our first two theorems have certain analogues, but the second, the B1 and the B2 theorems, we were not able to find analogues. So the proofs of the following theorems can be derived from the corresponding theorems about the one-star equation. And let me repeat the definition of the D range of alpha. And here we consider these two-star equations. This is also a conjugate equations with -1 exponents. Here we have a very similar first theorem about these equations. If we have a permutation of this type, and we assume that for all odd integers R and all D with DR in this D range, we have GD equal to 0, so there is no cycle of alpha of length D, and the greatest common divisor of -2 to the power D -1 and R is equal to 0. If we have such a condition, then equations 2-star alpha has only the trivial solution. Again, the problem is that it is not really transparent. To check this condition is not straightforward, but there is an immediate corollary of this theorem, and this corollary is somehow more transparent, but it is about a concrete situation. So if alpha is a product of two cycles, one is of length A and the other is of length B, and the A plus B is equal to n, of course. So if alpha is here and A and B are integers such that A is less or equal than B, and A is not a proper divisor of B, A can equal to B, and A, B, and A plus B are not divisible by 3. And we assume that -2 to the power E over P -1 is not divisible by P. Here E is one of these elements, A, B, and A plus B. For all E and for all P, we have this non-divisibility condition. And here we have to take only prime divisors P, which are greater or equal than 5. So if we have such a condition, if we have such an alpha, then our conjugate equations 2-star has only the trivial solution. And an example is A equal to 35 and B equal to 77. And now, again, here is the next theorem about the conjugate equation with exponent -2 on the right side. So let alpha be a permutation of a given type, and assume that there is no fixed point. And if we have two cycle lengths A and B, then these two lengths are relatively prime. And also assume that if A is a cycle length, then the number of cycles of length A is at most 2. And there is a non-divisibility condition similar as for the one-star equation. So if we assume that -2 to the power A over P -1 is not divisible by P for any prime divisor P greater or equal than 5 of A. And if we have such conditions, then we consider the solutions. If Y is a solution of 2-star such that no cycle length of Y is divisible by 3. So here it is an extra condition that here we consider solutions for which we have no cycle length divisible by 3. Then the solution must be equal, must be the trivial solution. So this is somehow weaker than the result in the case of one-star equation. But we have an interesting corollary. If we have the same conditions for alpha as in the previous theorem, then, and y is a solution, then we have that y to the power, and here we have a other power 3 to the power delta n is equal to identity. Here delta n is the maximum exponent of 3 such that it is less or equal than n, but here delta n can be replaced by n. It is equivalent. So for this y it is equivalent. So a solution satisfies such a, I can say it is quite a strong condition. So we can say something about the solution of the two-star equations. And that's all. And so I am not a group theorist, so it was an excursion for me and for my co-author to do this. And we used only elementary observations and elementary combinatorial arguments. And I do not went into the details here, but I think it was enough to have a taste of this kind of results. Thank you very much for your attention.
Okay, thank you. Are there questions, comments, remarks? Okay, if not, then let's thank the speaker again for the nice talk. And we have a break till 4:50 Bulgarian time. So we have a 20-minute break.
Hi, everybody.
Hola, hola.
Hi.
¿Qué tal?
Hello, can we start? Okay, so then it's my pleasure to announce the next speaker for this session, Alberto El Duque, and he's going to talk about non-group gradings on simple algebras. So please.
Thank you. Thank you very much. I would like first to start thanking the organizers for this opportunity, especially Flamenco Slukov for the invitation. And it's very nice to participate in this conference dedicated to celebrate the 70th anniversary of Vesselin Drensky. I must admit that I'm not quite sure when was the first time I met Vesselin. It was many years ago, but I'm not quite sure when was the first time. What I do know is that every time I talk to Vesselin, I end up learning something, either mathematical or otherwise, historical, geographical, whatever. So I'm very happy to being able to participate in this celebration. And I would like to, so Vesselin, I wish you many more fruitful and healthy years. Okay, so I would like to talk about some recent work that gives a negative answer to a question that has been around for some years. It's about the existence of gradients on simple algebras which cannot be realized as group gradients. So this is the aim of the talk. And this is the outline. So Well, there have been several talks about gradients on associative or non-associative algebras in general. I will restrict to Lie algebras. So some of the definitions have already been given, so I will review the definitions I need quickly. Then I will move to some gradients called pure gradients. These are group gradients on Lie algebras properties. And the gradients I will later construct are not group gradients, but share some of the properties with these pure gradients. So then I will show you the first example of a non-group gradient on a simple Lie algebra, and it will be a gradient on the spatial orthogonal Lie algebra on a vector space of dimension 26. So the simple Lie algebra of type D13. And finally, I will show you how to extend this example, modifying a few things to get an infinite family of non-group gradients on some simple Lie algebras. So this is the idea. And so we'll start just reviewing a few things about gradients on Lie algebras. And well, the systematic study of gradients on Lie algebras started with this paper by Patera and Zassenhaus in 1989. Of course, gradients on Lie algebras have been quite important from the very beginning of the theory of Lie algebras. Even the classification of the finite dimensional simple Lie algebras over the complex numbers relies heavily on a Cartan subalgebra, the corresponding root space decomposition, which is a gradient by a torsion-free group, and the properties of this root space decomposition, and the combinatorics related to this root space decomposition. Other types of gradients, like gradients by the integers modulo 2, are quite important in studying symmetric spaces in differential geometry. And gradients by the integers are important in Jordan theory, because even any Jordan algebra, or more generally a Jordan pair, we can consider a Lie algebra graded over the integers with just the 0, 1, and -1 components being different from 0. And then if more components are allowed to be non-zero, then we have some extensions of Jordan algebras. So gradients have been quite important for Lie algebras and for Jordan algebras and other kinds of algebras. But a systematic study was started with this paper by Patera and Zassenhaus. And most of the definitions we use nowadays appear there. For instance, they consider gradients in this very general setting, set gradients. So a set gradient in a Lie algebra is just the composition of the Lie algebra into a direct sum of non-zero vector subspaces in such a way that whenever we take two of these components, either the bracket is trivial or the bracket is contained in another component, whole bracket. So this is a very general definition. And these subspaces are called the homogeneous components. And two of these gradients are said to be equivalent if there is an isomorphism between the Lie algebras that takes homogeneous components to homogeneous components in the second algebra. So this is well known, and already in this paper appears in this generality. Of course, we are more used to gradients by groups, or more generally by semigroups. And the definition also appears in that paper. Given a group, or more generally a semigroup G, a G gradient on the Lie algebra is a decomposition as before, as a direct sum of vector subspaces which are labeled by the elements of the group or semigroup in such a way that the bracket behaves nicely with respect to the label. So the bracket of the homogeneous components of degrees G1 and from 0. It is said that this gradient can be realized as a group gradient, or more generally as a semi-group gradient, if we can embed the gradient set S into the semi-group or group G, so that defining LG equal LS, if G is the image of S under the embedding, and otherwise LG is 0, we get a G gradient on L. This is very natural and provides this definition of gradient being realized. And what happened in this first paper by Patera and Zassenhaus is that they made a mistake with these things that I will come shortly. But for now, let's stick to this set gradient. So start with a gradient just by a set. So I consider that all homogeneous components are different from 0 in this situation. And so we have the size of the gradient set is the number of homogeneous components. In this situation, the universal group of the gradient is the group defined by generators and relations. The generators are the elements of S, and relations are given by the multiplication in the Lie algebra. So there appears a relation S1, S2 equals S3 whenever the bracket of the homogeneous components labeled by S1 and S2 is not 0 and contained in LS2. So the relations are imposed by the way homogeneous components multiply and lie in another homogeneous component. So this is the universal group. And of course, since this group is generated by the elements of S, there is a natural map from the gradient set S into the universal group. And it is quite straightforward to check that this gradient gamma can be realized as a group gradient if and only if this map is 1-to-1. And in this case, if gamma can be realized as a group gradient, in particular, it can be realized as a gradient by the universal group. And it is the most natural group. Okay. So the fact that the gradient can be realized as a group gradient is related to the fact that the natural map from S into the universal group is 1-to-1. Another interesting thing is that whenever the Lie algebra is simple, the universal group is always abelian. This will be important later on. And the other concept that I will need later on, is the notion of the diagonal group of a gradient. So again, gamma is a set gradient. So I'm not imposing a semi-group or group gradient, just a set gradient. So given any gradient, all these definitions appear in this seminal work of Patera and Zassenhaus. The diagonal group of gamma consists of the oromorphisms of the Lie algebra L that behave as scalar multiples of the identity on each homogeneous component. So the restriction to each homogeneous component consists of just multiplying by a non-zero, because it is an oromorphism, non-zero scalar. And directly from the definitions, we see that whenever we have an element in the diagonal group, then we have a scalar for any element in S. So we have a map, a non-zero scalar for any element in S, and this extends to a character of the universal group with values in the field. And conversely, any character determines a unique element in the diagonal. So the diagonal group is isomorphic to the group of characters of the universal group with values in the field. So all these definitions and properties appear in this seminar. But as I was telling before, there is an incorrect assertion in the first theorem of that paper. This is the D part of theorem 1, where it is stated that given any set gradient on a Lie algebra, there is always an abelian semigroup and a 1-to-1 map from the S, from the gradient set into G, so that gamma can be realized as a G gradient through this map. So they thought, Patera and Zassenhaus, that any set gradient on a Lie algebra can always be realized as a semi-group gradient, not necessarily as a group gradient, but at least as a semi-group gradient. And the proof is a bit involved, and but this is not correct. So over the years, this is a paper that appeared in 1989. So years later, many years later, I managed to get a counterexample, so in 2006. And what I did was to construct this counterexample. Well, I was looking at the proof in Patera-Zassenhaus paper, and there was a point that was very tricky for me and obscure. So I couldn't understand well particular steps. So I started to construct a Lie algebra in more or less a free way from the components that appear in the proof. So what I did was to define a nilpotent Lie algebra of dimension 16, where all the homogeneous components are one-dimensional. So we get a basis with 16 elements, and the subspaces spanned by the elements of the basis form a set gradient, and I could prove that this is not a semigroup gradient. This gradient cannot be realized as a semigroup gradient. But this was a complicated example, but once we knew that there were examples, it was easy to realize that there were many more examples of this situation. So 3 years later, I provided more examples of set gradients that could not be realized as semigroup gradients. The first example is in dimension 4 with a solvable Lie algebra. Here you have a basis and see that the bracket is very nice. And the gradient consists of 3 homogeneous components. The first one has dimension 2, the component spanned by A and U, and the others have dimension 1. Okay, and so this is solvable. And it's quite easy. You just take, if you try to embed this into a semigroup gradient, it turns out that the component corresponding to this homogeneous component, the label in the semigroup must be an element G such that G squared equals G because of the first bracket. And then you work a little bit, and it's quite easy to check. It's much easier. This example is much easier than the previous one. And also, I managed to get an example. Well, this is a counterexample of minimal dimension. In dimension up to 3, all set gradients can be realized as semigroup gradients. And I managed to get another example in a semi-simple Lie algebra, which consists of 2 copies of SL2. Well, assume that the ground field is algebraically closed to avoid some other problems. But we think of the first ideal as SL2, and the second you should think in terms of SU2. So you have the natural standard basis for SL2, HXY with the natural bracket, and the natural basis for SU2, where you have 3 elements and the bracket of any 2 elements is the third one, and you permute cyclically these things. And here is the bracket with 5 homogeneous components, one of them of dimension 2, and all the other homogeneous components of dimension 1. And again, it's quite easy to check that this is this gradient, this set gradient, cannot be realized as a semigroup gradient. So these are easier examples, easier counterexamples than the previous one. But then the problem appeared, and what about simple algebras? Are there counterexamples for simple algebras? So already in the paper of 2006, where the first counterexample was described, this question was raised. Can any set gradient on a finite dimensional simple Lie algebra over the complex numbers be realized as a group gradient? This question appears in the first chapter of the monograph with Misha Koshetov on gradients on simple Lie algebras, because it was still unsolved and it's been unsolved until now. So this is the question. One interesting thing is that Christina Draper proved that if G is a semigroup, if we have a semigroup gradient on a simple Lie algebra, then the support of this gradient always generates an abelian subgroup of the semigroup. So we can forget about semigroup gradients and consider only group gradients. That's why here I don't speak about semigroup gradients, but directly about group gradients. So if there are semigroup gradients, this can be realized as group gradients as well. So for simple Lie algebras, it is enough to consider group gradients. So what I plan to do is to show you an example that the answer to this question is negative. There are set gradients that cannot be realized as group gradients, and the construction involves some combinatorics, and I hope you will like it. Well, some simplifying assumptions in what follows. Until the end, I will assume that the field is algebraically closed of characteristic 0. So if you prefer, we'll be working over the complex numbers, and we will forget about other possibilities until the very end. The Lie algebra L will always be finite dimensional and simple. So no other algebras will be considered. And whenever we have finite dimensional and simple Lie algebras over the complex numbers, we can consider Cartan subalgebra and the corresponding root space decomposition. So all this is well known and will be used. So, okay, let's go to these pure gradients, whose definition is this. It's a definition by Vesselin, 1982. And this is a definition about gradients by abelian groups on simple Lie algebras, finite dimension. All these simplifying assumptions work. So a gradient by the abelian group G is said to be pure if one of the homogeneous components different from the one labeled by the neutral element of the group contains a Cartan subalgebra of L. Okay, so there must exist a Cartan subalgebra contained in one of the homogeneous components different from the neutral homogeneous component. Okay, at that time in the 70s, some very nice gradients were discovered. For instance, Alexevsky discovered a gradient of the simple Lie algebra of type E8, the largest exceptional simple Lie algebra. Group gradient, the gradient group is the integers, 5 copies of the integers modulo 2. And each homogeneous component is a Cartan subalgebra of dimension 8. So it is a splitting of E8 as the direct sum of 31 Cartan subalgebras is one of dimension 8, of course. So there appear some very nice gradients that later on were called Dengolf decompositions, and they were considered this decomposition. People working in group theory and studying the classification of finite dimensional simple Lie groups consider this kind of decomposition. So decompositions where homogeneous components contain Cartan subalgebras or even were equal to Cartan subalgebras were in the air at that time. So this is the definition of pure gradients. So, okay, I will fix one of these Cartan subalgebras, corresponding system of simple roots. Once we fix a system of simple roots, we can consider the positive roots, and we can consider the torus, the associated torus, which consists of the oromorphisms that are whose restriction to the Cartan subalgebra is the identity. I will need the two torsion part of the torus. This is the T2, and I will need a larger subgroup because I will need oromorphisms that behave not as the identity on the Cartan subalgebra, but as a scalar on the Cartan subalgebra. But because of the properties of the roots, this scalar must be 1 or minus 1. So I will consider this larger subgroup, the oromorphisms, that when restricted to the Cartan subalgebra are either the identity or minus the identity. And then, well, what happens with these oromorphisms such that the restriction to the Cartan subalgebra is minus the identity? Well, essentially that there is a unique up to conjugation. So the order is always 2. It permutes positive and negative root spaces. For each root, it permutes the corresponding L alpha and L minus alpha. And a system of generators can be found in the root spaces corresponding to the simple roots in a precise way. And since these are always systems of generators of the whole algebra, these determine completely the sigma. So in other words, sigma is unique up to conjugation. And the subgroup, this extended subgroup that I mentioned before, is the semi-direct product of the torus associated to the Cartan subalgebra and the cyclic group generated by any one of these sigmas that appear. And moreover, the centralizer of a sigma like this in the torus is precisely the subgroup consisting of the elements of the torus of order at most 2, the two torsion part of the torus. So we have all these things. And these things are important because I want to study the diagonal group of these pure gradients. And in the diagonal group consists of the holomorphisms that act as scalar multiples of the identity on homogeneous components. But in a pure gradient, there is a Cartan subalgebra contained in one of the homogeneous components. So any element in the diagonal group acts as a multiple of the identity, a scalar multiple of the identity on the Cartan subalgebra. And then the restriction to the Cartan subalgebra is necessarily the identity or minus the identity. And then since the Cartan subalgebra is contained in an homogeneous component different from the neutral homogeneous component, there must exist an element in the diagonal group such that the restriction to this Cartan subalgebra is not the identity. So we have one of the holomorphisms that we considered in the previous slide. And then what happens is that the diagonal group of any pure gradient is the Cartesian product of one of these holomorphisms, sigma, and the intersection of the diagonal group with the two torsion part of the torus. So this is always the case. So in particular, the diagonal group of any pure gradient is always a finite two-elementary group. And this will be important later. So we know what the diagonal group of a pure gradient looks like. But what pure group gradients look like? Well, we fix one of these Cartan subalgebras, one of these holomorphisms. We fix the root lattice, fix a system of simple roots, the corresponding positive roots, negative roots. We have the torus, and the torus attached to this Cartan subalgebra can be identified with the group of characters of the root lattice. And so the torus is isomorphic to this group of characters, and then the two torsion part of the torus corresponds to the characters that are trivial on twice the root lattice. But the quotient is two elementary, so any character here takes values in 1 minus 1, because this is a two elementary group. So we have some identification here, and in particular, any character of this two elementary group corresponds to an holomorphism of the Lie algebra that acts as a scalar multiple of the identity on each root space, and the scalar is given by the corresponding character. So this is more or less well known, and it's easy to deal with. Okay. But this gives a bijection between subgroups of this two torsion part of the torus and subgroups of the root lattice containing twice the root lattice. And this is clear. So to any given subgroup, we take the subgroup of the torsion part of the torus. We consider the subgroup on the right consisting of the intersection of the kernels of the corresponding characters. And conversely, given a subgroup of the root lattice containing twice the root lattice, we take the subgroup of the two torsion part of the torus that corresponds to the holomorphisms given by characters that kill the subgroup E that appears there. So this is a nice bijection here. And with these technicalities, take any subgroup lying between the root lattice and twice the root lattice. So this is a free, torsion-free group, a free abelian group, and consider the two elementary group given by the quotient Q over E and a copy of the integers modulo 2. Okay. Now for each positive root, we pick a non-zero element in the corresponding root space. And now we define a grading where the grading group is this one here, this two elementary group. And here are the corresponding homogeneous component. If the component in the integers modulo 2 is 0, well, we just take elements of the 4x alpha plus sigma, this fixed oromorphism that we have considered of x alpha, for the corresponding coset of modulo E. And if it is 1, well, we have to distinguish two cases, but we have to take minus, and in case the corresponding coset is the trivial coset, we have to add the Cartan value. So the homogeneous components are obtained either with positive roots and the oromorphic sigma, and elements constructed like this, or the Cartan algebra and elements constructed like this. And this is what pure gradients look like. They are always gradients by a two elementary group, and constructed in terms of one of these oromorphisms, sigma, unique up to conjugation, that we have considered. The extreme cases correspond to the situation in which E equals Q, and then this part disappears, so it is a gradient by the integers modulo 2, which is quite natural. And the other extreme case is when E equals twice the root lattice, so we have equality here, and then we get a gradient that exists for any simple Lie algebra, which is a gradient by two elementary group of rank n plus 1, where n is the rank of the Lie algebra. Okay, so back to the diagonal group. Well, this E that we have considered may be too big, too large. And we have to consider a smaller subgroup containing twice the root lattice, but containing in E. And well, these are some technicalities. I don't want to enter into these technicalities, but we can, let's say, simplify the E to get a smaller E and get an equivalent gradient. And the way is quite natural. So what happens is that given any such subgroup E inside the root lattice, we can get usually a smaller root, more simplified group, so that the gradients are equivalent, the corresponding pure gradients are equivalent, and the diagonal group is given in terms of this simplified subgroup. And remember that this T sub E corresponds to the characters that kill E, in this case, E circle. And this can be strict. Okay. So just in order to continue, since my example will be in a special orthogonal Lie algebra, just will fix some notation, picking a suitable basis of the 2n-dimensional vector space. We are dealing with the special orthogonal Lie algebra of degree 2n, can be identified with the algebras of 2m times 2n matrices, split into blocks, n times n blocks, where in the diagonal we have any matrix and minus the transpose, and in the off-diagonal parts we have skew-symmetric matrices. Here we have a natural Cartan subalgebra, which consists of the diagonal elements here in this algebra of matrices. We have natural elements in the dual of H, because we have the forms, the linear forms epsilon I, and epsilon I just picks, applied to an element in the Cartan subalgebra, just picks the ith component. Okay, so we have the epsilon 1 up to epsilon n, and this is the root system. It's well known. All roots that appear are plus or minus epsilon I, plus or minus epsilon j for different I and j. As a system of simple roots, I will take, as usual, epsilon 1 minus epsilon 2, epsilon 2 minus epsilon 3, epsilon 3 minus epsilon 4, and so on, until epsilon n minus 1 minus epsilon n, and then I have to add another root, epsilon n minus 1 plus epsilon n. If we consider this system of simple roots, then epsilon 1 turns out to be the highest weight of the natural module, and 1/2 of the sum of the epsilons turns out to be the highest weight of one of the two half-spin modules that appear, and I will need one of these half-spin modules, as you will see in a minute. And the oromorphism sigma, we can fix the oromorphism that just permutes rows and columns in this block form of the matrix. So with all this, let me give you a nice example of a group grading. This will be a group grading, a pure grading on the special orthogonal algebra SO8. And for E, I take twice the weight lattice of the half-spin module with this highest weight. And this twice the weight lattice is twice the root lattice plus the integral scalar multiples of the sum of the epsilons that appear here. And therefore, the corresponding pure grading, the grading group is consists of 4 copies, the Cartesian product of 4 copies of the integers modulo 2. And it turns out that the positive roots split modulo our E into 6 pairs of orthogonal roots. And here the 6 pairs of orthogonal roots. So here we have all the positive roots of SO8 with respect to the system of simple roots that I have considered, and they appear in this way. And we look at the definition of pure gradients, what pure gradients look like, and this is the situation. We have an homogeneous component, which is the Cartan subalgebra, and all the other homogeneous components are two-dimensional toral subalgebras. In this case, we cannot simplify E, so the diagonal group is also isomorphic to the Cartesian product of 4 copies of the integers module. Okay. So let's go to the example of non-group grading. And this will be an example in the special orthogonal Lie algebra of degree 26, corresponding to a vector space of dimension 26. And the idea to get this example is to get a decomposition of the positive roots in exactly the same way as I obtained here. But in SO26, there are many more positive roots. And to do this, I will use the lines in the projective plane over the field of 3 elements. So we have the field of 3 elements. So the lines in this projective plane have 4 elements, each one, 4 points. Any 2 points like in a unique line, and any 2 lines intersect in a unique point, any 2 different lines. So we can number the lines we can number the points from 1 to 13, and I've made a numbering, and these are the lines. If you don't believe me, you can check that any 2 numbers between 1 and 13 appear in a unique one of these lines, and any 2 lines intersect in a unique point. So you can check that I'm not cheating you, okay? And now what we do is the following. For each line, we take the 6 pairs of orthogonal positive roots that appear for SO8. Because for each line, we have a copy of SO8 inside SO26, the special orthogonal Lie algebra of degree 26. So I take for each line, the 6 pairs of orthogonal positive roots that appear in the corresponding copy of SO8 inside SO26. So all in all, we have 13 lines, and for each line, I get 6 pairs of orthogonal positive roots. So we have 78 pairs. And I consider the same splitting that I had for SO8. One homogeneous component is the Cartan subalgebra, and all the other homogeneous components are 2-dimensional toral subalgebras. Each one lies in a copy of SO8 inside SO26. So this is the situation. And okay, so the proposition, this is a set grade. So every time we take the bracket of two homogeneous components, the bracket is 0 or it is contained in another homogeneous component. And well, apart from trivial cases, we have to deal with two pairs of orthogonal roots. Each pair of positive orthogonal roots appears in a line. So we have two lines involved. So there are two possibilities that the intersection of the two lines consists of a single point. And then things are quite easy. Actually, the bracket is contained in another homogeneous component, actually in only a part of other homogeneous component. Because there is a unique non-zero bracket there. And that's it. And the other possibility is that the two lines coincide. But if the two lines coincide, we are inside a subalgebra isomorphic to SO8. And we have two homogeneous components of a group gradient on SO8. So the bracket behaves very nicely with respect to this gradient. So everything works. Okay, now this is the problem. The problem is to check that this is a non-group gradient. How to do this? Well, if it could be realized as a group gradient, it would be pure. Because we have Cartan subalgebra as one of the homogeneous components, and it cannot be the neutral homogeneous component. So, but using the same arguments valid for pure gradients, we know that in this case, the diagonal group is always a two-elementary abelian group. Because the arguments do not use really that the gradient is a group gradient. And we can compute the diagonal group. And to compute the diagonal group, we have to deal with characters. And to deal with characters corresponding to this E. But this E can be obtained and in a very precise way, working with the combinatorics that appears here. So it turns out that given any line, all the sum of the epsilons corresponding to the line always lie in this E. So we can sum over all the lines that contain the element 1. And then we get these elements that are in red in our E. And then instead of 1, you take 2 and do the same and subtract. So you do some easy arguments, counting and subtracting, and what we get is that E is very large. It contains many elements. And therefore, E is large, and therefore the diagonal group is small, very small, 4 elements. But the diagonal group, if this were a group gradient, the diagonal group would be the character group of the universal abelian group. This gives that the universal group is very small, but we have many homogeneous components. If it were a group gradient, it would be a group gradient over the universal group. So there would be at most 4 homogeneous components, and we have hundreds of homogeneous components. So it is very, very far from being realized as a group gradient. Well, I know I've run out of time, so let me just very quickly show that, well, I have been using lines in a projective space. So I can do the same as long as I can split the numbers from 1 to n into lines of 4 elements with the property that any 2 points lie in a unique line. The corresponding combinatorial objects are called Steiner systems of type S2 for n. And these Steiner systems exist only if n is congruent to 1 or 4 modulo 12. The lowest situation is n equals 13, which corresponds to the projective lines, the lines in the projective space. So this is not a coincidence. And so if instead of using these lines in the projective space over the field of 3 elements, we use any of these Steiner systems, we can play exactly the same arguments and get non-group gradient on the corresponding special orthogonal Lie algebras. One of the homogeneous components is always Cartan subalgebra, and the other homogeneous components are total two-dimensional subalgebras. So let me finish with a couple of remarks. Well, I told you at the beginning that I was going to consider only algebraically closed fields of characteristic 0. Actually, everything works over arbitrary ground fields in any characteristic different from 2. So we have examples in any characteristic. And now, as for semigroup gradients, now that we know that there are non-group gradients on simple Lie algebras, are there simpler examples? It would be nice to have simpler examples. So thank you very much for your attention. I'm sorry I'm 3 minutes late. Thank you. And of course, congratulations, Vesselin.
Thank you very much for the nice talk. We still have some time for questions, so please, any questions, comments, remarks?
I have a question. Yes. A naive question guided by the non-cross product constructions of Amitsur. The question is whether there is some kind of generic situation or generic construction that will say that if you pick at random a set grading, it will not be a group grading. Something related to what you said at the end, I think, of your lecture.
Yes, yes. Well, for SL2, any set grading can be realized as a group grading. So, but if the dimension is large enough, my feeling now that I have this example, is that probably if one is able to get a set grading in a random way, which is not easy, because being a set grading imposes strong restrictions, probably we can find many more non-group gradients. So yeah, this is my feeling now. Anyway, with respect to these cross products and so on, for Lie algebras, if we have group grading on a simple Lie algebra, the support generates an abelian subgroup. So we always restrict to abelian subgroups, and so I guess, well, for associative algebras, it is easy to construct non-group gradients on matrices and so on. So, but Lie algebras have this extra restriction that the grading group has to be abelian and these kind of things. But yeah, my feeling now that I come out with this example is that there should be other ways of doing. But anyway, this is a nice kind of grading with very nice properties. All homogeneous components are total subalgebras with certain regularity, and so there is some nice combinatorics behind this. But there should be others. There should be others, and in smaller, simple algebras.
Okay, thank you.
Are there more questions or comments? If not, let's thank the speaker again.
Thank you. Thank you.
And we have a 4-minute break till 5:40 Bulgarian time.
Muy bien. Muy interesante.
Can you see this now?
Yes, we see it.
Okay.
Опитайте да видите дали може да сменяте слайдовете.
Да.
Добре. И 3 минути имаме още. Okay, I think it's time to start. So it is my pleasure and honor to introduce the next speaker, the main figure of this conference and the person who gathered us all here. So this is, of course, Vesselin Drensky, and he will talk about locally important derivations of polynomial and other free algebras. So please.
Thank you very much, first for organizing the conference, then for coming here, then also for the nice words which I listened all this week here. So there were so many wishes for health and for work that I have to work very hard, also on Saturday and Sunday, to have to be able to do everything which you wish me. And now the talk is about local unipotent derivations. This week there was a lot of invariant theory, a lot of local unipotent derivations, so I missed some of the things which I planned to include. So, of course, all the students, they know what is the Leibniz rule when you have the derivative of a product of two functions. So this is the rule here. But you see in some textbooks, the derivative is denoted in another way, not in this way. For example, in the Newton notation, this is with dot. In our Lagrange notation, this is prime. And but in the sequel, I shall work only with algebraic closed fields of characteristic 0. The algebraic closed is not so important, but the characteristic very often is important. And now, what is a derivation of a ring or of an algebra? This is something which is not so common for non-algebraists. And if you have an algebra which is not necessarily commutative or associative, we have a linear map, and it's a derivation if it satisfies the Leibniz rule. And the simplest example which you have, if you have an associative algebra or a Lie algebra, then if you take the commutator is the operator which is a derivation is called inner. So this is the join action. And the main property that if you take the vector space of all derivations, I don't know this there, then this is a Lie algebra with respect to the usual operation for Lie algebras. And the story, if you open the book by Nowitzki about polynomial derivations and their Ringman constants, which was published 27 years ago, you can see there, the book is available online. By the way, here I give some references, but don't try to copy them immediately. I believe that the organizers, they post the presentations online. Also, there will be a video of the talks, so you'll be able to do this, to copy the references after this. So you see that this is a piece of the book that the derivations, they appeared, of course, not only in analysis geometry, but also in algebra, in Galois theory for differential equations, and also some other things. The differential algebra started in the 50s, so it's as old as I am. There was a book by Reed, another book by Kolchin, also Kaplansky had a book. Here are the references to these books. Also, there is a survey about this. This is 15 years ago. It's available online. So there is also some history there. So it's faster to read the history in the paper instead to see in the books. And the derivations of the polynomial algebra, they are simply in the following way. They are linear combinations of the partial derivatives multiplied by some polynomials. So the algebra of derivations, it appears so this is about 170 years ago. Cayley, in 1857, he published a paper where he considered the algebra of the derivations. This is a piece of his paper. Here, this is the operation, but I prefer to say this in a modern language. So you have the algebra of derivatives, a derivation of the polynomial algebra in one variable, but you have another operation. This operation is like it's given here. So you take the derivative of this one, and here you don't do this. So this algebra, this is left commutative. So this is a non-associative algebra satisfying this identity that if you have this product x1 and then brackets, you can change the place of these two things. Also, this algebra, this is right symmetric. Right symmetric means that if you have the associator, the associator, you can change the places in these two positions. Cayley also he started to consider this algebra in terms of rooted trees, and this idea to use rooted trees for different kinds of algebra is still applied quite intensively even now. And the Weil algebra, this is the algebra of the polynomial of differential operators with polynomial coefficients. Okay, this algebra is called after Hermann Weil, who, if you read the Wikipedia, introduced them to study the Heisenberg instanton principle in quantum mechanics. But after the talk of Unit Makar-Limanov, you see that this algebra appeared maybe not explicitly even before. So this algebra, of course, it appears in many places in mathematics, as Leni Makar-Limanov taught. This is one of the most studied algebras in algebra, in mathematics at all. So it has defining relations in this form. You have two sets of generators. the x's are the variables, y's are the partial derivatives, and you have these relations. If you have the x's and the y's, they commute, and the y's and the x's, they give either, the commutator gives either 1 or 0, depending whether they are the same or different indices. So the Witt algebra, this is the algebra of derivations of the algebra of Laurent polynomials. So you are allowed to have only also negative degrees. This algebra was considered by Cartan more than 100 years ago, and then was studied in the case of finite fields by Witt. So, and what is a Walker-Newport derivation? If you have a derivation which sends every element in 0 if you apply several times, then this derivation is called Walker-Newport because this is Newportian acting on explicit elements. And the constants in the usual case of algebra, of analysis, they are the only elements which vanish when you take the derivative. So, by some analogy, the elements of the kernel of a Walker-Newport derivations also are called constants, and the kernel is also an algebra which is called the algebra of constants. And in the second evolution, you consider only Walker-Newport derivations. So, why we study Walker-Newport derivations in the case of polynomial algebras? The first thing is that relations with the automorphism groups, because if you take the exponent of a derivation, so this is an automorphism. Here, of course, this one is in the general case should be infinite, and this is the case when we have this in the case of the algebras, when you have some convergency. But here everything is okay because you see if it acts on an explicit element, the high degrees disappear. So this is not a series, this is simply a finite sum. So it's correctly defined. Also, there is some relation with the automorphisms in the following way. If you have the additive group of the field and you map this to the automorphism group, as you have some homomorphism, then there is a Walker-Newport derivation such that the image here, if you start with some number alpha, the image and the automorphism, this is the exponent of the corresponding Walker-Newport derivation. And of course, the algebra of the fixed points of the action of the additive group of the field coincides with the algebra of the constants. So, of course, this gives immediately some relations with invariant theory, because if you have, if this map sent the additive groups of the field to the matrices over the vector space, which is spanned by the generators of the polynomial algebra. So you have a linear map. Then this delta, which is defined as the logarithm, is a Walker-Newport derivation, which acts as a Newportian linear operator on the d-dimensional vector space. And such linear Walker-Newport derivations, they are called Weissenberg derivations. Weissenberg, he published a paper where in 1932, he gave a wrong proof of the theorem that the algebra of invariants is finitely generated for any linear group. Hermann Weil, he wrote a review for the paper in Zentralblatt für Mathematik. He found a gap in the proof, and now what is lost from this paper, this is the following theorem, which is really very nice. This is the theorem of Weissenberg, that the algebra of constants is finitely generated for any Weissenberg derivation. So for any derivation which acts as a linear operator, as Newportian linear operator on the d-dimensional vector space. And now there is some relations with the 14th problem of Hilbert. It was discussed already in some of the talks, but the Hilbert problem, it was motivated by invariant theory. and is stated in the following way. You have a field which is a subfield of the field of rational functions, and the ground field is contained in F. Is it true that the intersection of the field with the polynomial algebra is a finitely generated algebra? Of course, the main motivation for the problem was from invariant theory. If you have a subgroup of the general linear group, is it true that the algebra of invariant is finitely generated? Of course, the 14th problem, the 14th Hilbert problem, is an object of many books, many survey articles, a lot of study. You can see, for example, the book by Nowitzki, which I already mentioned. There is a book by Arno van den Essen about polynomial automorphisms of the Jacobian conjecture. There is a book by Freudenburg about Walker-Nilpotent derivations. And also, it's a pleasure for me to say that Freudenburg, he also wrote a survey article on counterexample of the Hilbert 14 problem for our journal Serdica 20 years ago. And which are the negative solutions to the 14th Hilbert problem? I don't speak about the positive solutions. The positive results, there are really a lot. They were mentioned several times. But the first counterexample was given by Nagata in 1958. And he has two counterexamples. The first one is simply some field such that the intersection is with the polynomial algebra is not finitely generated, but another, this comes from invariant theory. So he found an action of the 13th sum of the direct sum of 13 copies of the base field acting on the algebra of polynomials in 33 variables, such that the algebra of invariant is not finitely generated. And you can translate this in the language of Weissenberg derivations, that there are 13 Weissenberg derivations, such that of the algebra of polynomials in 33 variables, such that the intersection is not finitely generated. And of course, you can immediately ask the problem, what is the minimum number of variables such that there exists a group such that the algebra of invariance is not finitely generated? And also, the other question, which was also inspired by the result of Nagata, is what is the minimum number of Weissenberg derivations such that the intersection of the algebra of constant is not finitely generated? Of course, there are lower bounds for these numbers. For example, the 14th Hilbert problem has a positive solution in the case of two variables. This is a paper by Zariski. And as a corollary, you can obtain from here that for Walker-Nilpotent derivations in three variables, the algebra of constant is also finitely generated. So it doesn't matter whether these derivations are linear or not. This goes for any Walker-Nilpotent derivations. And which are the best results for the upper bounds? Freudenburg, he has a theorem which states that there is a subgroup of the unit triangular group such that the algebra of invariants in the case of polynomial algebra in 11 variant is not finitely generated. So this was 14 years ago. He also has another paper a little bit later. Mukai, he has three Weissenberg derivations such that the intersection is not finitely generated. Here, the number of the variables is 18. And of course, you have the problem, if you have two Weissenberg derivations, what happens if the intersection of the constants is finitely generated or not? So there are other examples which are related with derivations which are not finitely generated. the algebra of their constant is not finitely generated. Roberts, he constructed a counterexample based on another principle. Later, it turns out that the counterexample is equal to the algebra of constants in 7 variables of a derivation delta which is Walker nilpotent. So they are here the reference of the papers. And this idea was used further in several papers. The minimal counterexample is in the case of 4 variables. Okay, this theorem is only 1 hour. I should correct this. The algebra of constants in the Walker nilpotent derivation, which is written here, in the case of polynomial algebra in 5 variables, is not finitely generated. This is a Diego and Freudenburg. And of course, it's natural to ask what happens in the case of 4 variables. Is there a Walker nilpotent derivation such that this algebra is not finitely generated? And also, I'll finish the discussion with a counterexample in any dimension bigger or equal to 3. So Kuroda made this 16 years ago. And the theorem is that if you have some positive integers which satisfies this inequality, and you have the field generated by these 3 functions, here you have the degrees of the elements. They depend on these variables. Then if you take the algebra of generated by these 3 rational functions and intersect with the polynomials, this algebra is not finitely generated. This is in the case of 3 variables, but this is immediately that it also works for any number of variables, bigger or equal to 3. So I'll continue a little bit with the Weizenberg derivations and the invariant theory. This derivation, which is a Walker nilpotent operator on the d-dimensional vector space, its Jordan normal form consists of Jordan blocks, and the cells, their matrices with 0 diagonal of this form. So up to a conjugation and change of the basis, there is only a finite number of essentially different Weizenberg derivations for any dimension. And of course, you can ask, if you have a given Weizenberg derivation, find the generators, compute the Hilbert series or Poincare series. So here, the people in invariant theory, they use usually the word Poincare series, but the people in commutative algebra think that Poincare series is something else. So I prefer to say Hilbert series. And also, if you take the Jordan matrix of a Weizenberg derivation, you can map the group of unit triangle 2x2 matrices to the set of these exponents, and this defines a correspondingness of the unit triangular group to the action and gives an action on the dimensional vector space. And here it's known that the algebra of invariants coincides with the algebra of the constants. So here you can use this in both directions. You can apply methods to invariant theory to study the algebra of constants, and in the other direction to apply the Walker nilpotent derivations to invariant theory. In some sense, there is a principle in the case of Lie groups and Lie algebras that the Lie algebras, their simplification of the Lie groups because the problem is linearized to study there. So here you have also some linearization if you study not the group, the multiple group of unit triangle matrices, but the additive group of the base field. And Nowitzki made a conjecture that if you owe the cells of the Weissenberg derivations in two D variables, 2 by 2 matrices. So this means that the variables with odd index, they go to 0, and with even index, they go to the corresponding element of odd index. Then the algebra of constants is generated by the elements from the kernel, which is obviously the variables with odd indices and some determinants. By the way, this conjecture is our illustration of bad connections between invariant theory and other parts of algebra, because it can be translated almost immediately in the language of invariant theory. And now there are 9 proofs based on different methods, which confirm the Nowitzki conjecture and also have some generalization. Khoury, his first proof used Grobner basis techniques. Bedratyuk, he used invariant theory. Derksen and Panyushev, they have unpublished proofs which also use invariant theory. With Makar-Limanov, we have a proof which is really elementary. I think it can be followed by an undergraduate student. Also, there are some other proofs. Even now, I have a proof which appeared only a year ago, which uses ideas of non-commutative algebra. And you can go further. For example, if you have 3 by 3 cells, Jordan cells, Bedratyuk, he published a paper when he found the generators of this algebra. This consists of the elements which go to 0 immediately, some determinants. So here, this is everything as in the case of the algebra of the Nowitzki conjecture. And here you have determinants and some more expressions. So this result was obtained translating some results from invariant, classical invariant theory. And of course, you can see a lot of references. The book of Nowitzki, it has a chapter about local-unipotent Weissenberg derivation. Derksen and Kemper, they have also in their book by computational invariant theory a chapter there. Dolgachevsky has also one chapter. And concerning the computational methods to compute, for example, the Hilbert series, you can see the books. And also we have a paper which is written by a big team of people. If we exclude Genov, who passed away 3 years ago, all the other people there here in the audience in the moment, where we developed some methods, purely algebraic methods to work with invariant theory, and especially with the Weissenberg derivations, and invariant theory also with some other groups. You listen here the talk by Liza Christova about this. Also, Alan Berry involved here also here. But in this case, we simply use some papers by Elliott, published about 115 years ago, devoted to the Diophantine equations solution in non-negative integers. And now, the relation with the automorphism group of the polynomial algebra, maybe the main problem is describe the group of the automorphisms. Here, of course, describe means many different things. For example, find generators, find defining relations, etc., etc. The structure of the group. This problem was started in the 40s for the needs of algebra and algebraic geometry. But you see, algebra, this is something which studies different objects, but very often study the objects, the main problems are the same. So there are paper by Newson published 100 years ago, and more 100 years ago, where he described the automorphism groups of the finitely generated free groups. So if you see what happens in the case of free groups, if you see what happens in the case of free Lie algebras, the free associative algebra, the free non-associative algebras, you have the same problems, but the results sometimes they sound in different way. And now, which are natural candidates to be generators of the automorphism group? Of course, you have the affine automorphisms. The affine automorphisms, they simply send the generators in linear combination of the generators plus a constant. And of course, this part here, this matrix is invertible. You have the triangle automorphisms, where every automorphism, the variables, they are sent up to a constant to itself plus some polynomial which depends on variables which are with higher indices than this one. So these are fj, they don't depend on the first j variables. And the subgroup of the automorphism group generated by affine and triangular automorphisms, it consists of the tame automorphisms. Of course, the other automorphisms, they exist, they are called wild. So, of course, you have immediate the problem, are all automorphisms of the polynomial algebra tame? The answer for two variables, it was proved in 1942 by Jung in characteristic 0. Van der Koek made this in the general case. Also, he described the group of the automorphism in the case of two variables. And there are many proofs of this theorem. There are several proofs which are easy, which use Walker-Newportian derivations. Renscher has the first proof. Also, Rimanov, he has a proof which use Walker-Newportian derivation. This in his lecture note, which is available. Also, I included his book, his proof in my book on free algebras and PI-algebras. And also, Renscher, he classified all Walker-Newportian derivations of the algebra of polynomials in two variables. So the Walker-Newportian derivations, they are the following way. You change the variables in the corresponding way, and then the first variable goes to 0 and the other goes to a polynomial on the second one. So, and these are the usual derivations, the simplest one. So you have that if you have two variables x and y, x goes to 0 and y goes to a polynomial of x. Yeah, up to a change of the variables. But what happens when you have more than two variables? Of course, you have such an observation that if you have a constant which is non-zero, and the Walker-Newportian derivation, if you take another derivation which sends the polynomials to the images and then the ground derivations times the constant, then you have also Walker-Newportian derivations with the same algebra of constants. And maybe the most famous automorphism, this is the Nagata automorphism. Nagata, 50 years ago, he conjectured that this automorphism, which he has, is wild as a polynomial, as a automorphism in the polynomial algebra in three variables. If you consider polynomial algebra in two variables with coefficients which are depends on z, then he proved that this automorphism is wild in the class of this thing. What is the difference? Here, in this place, if you present this automorphism as a product of elementary triangular or affine automorphism, you should keep the variable z fixed all the time. And here, you have more space to work. For example, you can send X to some, you can send Z to something which is different from Z, and then to go back. So you have more room to work when you have 3 variables instead of 2 as here. And this conjecture was answered affirmative by Shestakov and Tomirbayev in 2 papers, a little bit before it was announced in the Russian Contradieu. But it's really very important that it was proved using methods which are not from commutative algebra, but extremely non-commutative and non-associative. They used here Poisson algebras. So here, usually, the people in ring theory, they are consumers. They use ideas from commutative algebra and try to prove or to show that this is not true, using some result, what happens in commutative algebra. And here we have the opposite influence. Some methods developed in non-commutative algebra, they are applied to solve really a deep problem for commutative algebra. And what is the relations with working nilpotent derivations? If you take this derivation, x goes to minus twice y, y goes to z, goes to 0, obviously this is working nilpotent. This element w, which is xz plus y square, this is in the kernel, it's a constant. So if you take this product, this is a working nilpotent derivation, and its exponent is exactly the Nagata automorphism. So here there are also some important results concerning Nagata automorphism or this kind of automorphism due, for example, to Makar-Limanov. But I skip this. So the automorphism is stably tame. It becomes tame if you add one more variable to the set of variables, and you assume that this variable is fixed, so goes to 0. So here this should be 0. On this automorphism, it's okay. So if you have a triangular automorphism, a triangular derivation, so you have an element of the kernel, then if you take this product, this is a working nilpotent derivation, and the corresponding automorphism, it turns out to be stably tame. This is a result by Martha Smith. And of course, if you have some suspect that these automorphisms are wild, they became tame when you extend the variables. This means that there is no room to work in the original algebra. Here you have exactly this phenomenon. For example, you use this extra variable to work in some moment. This extra variable goes to something which depends only on the first number of variables, and the compositions of all these automorphisms send this variable back to its place. But also, if you have some stably tame automorphisms, and we cannot prove that they are wild, they are tame, you can consider this as suspect to be wild automorphisms. Of course, the existence of wild automorphisms is when you have more than 3 variables, this is an open problem. Also, if you have a positive characteristic, this is also an open problem. And here I state some theorem which was related with polynomial identities of matrices, but the impact is for the polynomial algebra. So you have the polynomial algebra in 2 sets of variables. You set the variable y to 0, and the other variables, they are affine with respect to x. So they are linear combinations x with coefficients which are depends on the other variables. And assume that this is a walking nilpotent derivation. You have an element which is a constant, and the corresponding exponential automorphism here is stability tame, and its extension is tame when you have n variables y, and you extend, you add one more variables, and if you have only two variables, so here it should be n is here, m is here, so I should change the places here. So this is a joint work with me, with one of my students, Dimitar Stefanov and Arne van den Essen. By the way, here we had a funny story with this paper, because with my students, Dimitar Stefanov, we solved a problem which we asked with Kanta-Gupta, and since in that moment my student prepared his master thesis, we didn't write immediately the paper, and Efim Zelmanov wrote me, you should be asked to be a referee of a paper by Arno, which was written on a problem by Gupta, by Drensky and Gupta. I told Zelmanov, you see, just now we are writing the same paper, so don't send me the paper. No, I sent it, but you sent it in an envelope without opening my envelope, because in that time he sent this a hard copy by mail. And later we wrote our paper with Dimitar Stefanov. We sent it to the same journal. In some moment we got two positive reports, that the paper by Arno is accepted and our paper is accepted, but it should be made as one paper. And it turns out that we have one paper which is accepted twice, but it's not written. And in some moment we wrote a joint paper, and the proofs were almost the same. So this used the approach of Martha Smith about the stability automorphism and the theorem of Suslin, that if you have more matrices of size 3 and 3 and more, every matrix with determinant 1 with entries from the polynomial algebra is a product of elementary matrices. And why this thing started? So with Kanta-Gupta, we studied the automorphisms of the pure trace algebra of two generic 2x2 matrices, and we found some automorphisms there. And since this algebra is the polynomial algebra in 5 variables, these are the corresponding family of automorphisms in the polynomial algebra in 5 variables. So the question was whether these automorphisms are tame or not. And it turns out that we don't know whether they are tame or not, but we know that they are stable tame. So this is, and also there are, of course, many other walking nilpotent derivations. But usually, in most of the examples, the walking nilpotent derivation fixes some of the variables. And here there is an example of Freudenburg, which doesn't have this property. This is defined as a determinant for the case of 3x3 matrices. And it doesn't fix any variable independently of which is the generating set of the polynomial algebra in 3 variables. And now I go to the walking nilpotent derivations in the non-commutative case. This also was discussed. I'll say few results only. In the case of 2 variables, all automorphisms are tame, and the groups polynomial automorphism to variables and the automorphism of the free associative algebra into variables, they are isomorphic. This was proved by Makar-Limanov 51 years ago, and 50 years ago, independently by Anastasia Chernikevich. And as a corollary from here, it's easy to see, and combining with the result of Rechner, you can see that the working unipotent derivations of the polynomial in the free associative algebra in two variables are the form one of the variables goes to 0 and the other goes to a polynomial of the other variable. Of course, with depending on the base, if you choose the proper base of the free associative algebra. And what is the difference between the working unipotent derivations of polynomial algebra into variables and the polynomial in the free associative algebra into variables? In the case of polynomial algebra, you have such a phenomena. There are many working unipotent derivations with the same algebra of constants. So if you take one derivation and you multiply it with a constant, you get the same algebra of constants. But it turns out that this is completely different in the case of the free associative algebra. If you have two working unipotent derivations with the same algebra of constants, then up to a multiplicative constant, they are the same. So this is, we found this maybe 10 years ago, but postponed the write the paper, and finally 2 years ago we wrote the paper. And in the case of three variables, David Anik, he had an automorphism which was conjectured to be wild. This automorphism fixes the variable z, and here sends x to x plus z times something, y to y plus the same thing, but with z from the other side. And this automorphism is of the form the exponent of working unipotent derivation. The working unipotent derivation is of this form. It's an x, y, and z to this one. And Omirbaev, he proved that the Anik automorphism is wild. By the way, this is interesting that if you go to the polynomial algebra, you simply forget that you have non-associativity. You have an automorphism of the polynomial algebra, and it turns out that this automorphism is tame. So here, the non-commutativity is essential. And now I'll finish my talk with something which was already discussed today by Mateusz Domokos. So you know that in the theory of PI-algebras, PI-algebras are considered to be similar to commutative algebra and finite dimensional algebra. So, but if you consider invariant theory, these conditions, there are more differences. It was stated, for example, in the talk by Sylvia, also in the talk by Mateusz, and some other. But now you have a lot of conditions which are equivalent. You have a variety of unitary associative algebras over a field of characteristics 0, and you have equivalent conditions. So you have a reductive group, and you have that the algebra of invariants, you can define the invariants in the same way as in the commutative case, are finitely generated for all dimensions D and all linearly reductive groups. And this algebra is finitely presented. This means that the relatively free algebra is finitely presented. This means that the T ideal in D variables is finitely generated as an ordinary ideal, not as a Specht with the Specht property. It's enough to consider only the case of two variables. So you have the relatively free algebra of rank 2. If this algebra is finitely presented, then everything is okay. The variety is working unipotent, working Noetherian. Working Noetherian means that every finitely generated algebra satisfies the disjoint chain conditions for left ideals and similar for right ideals. It satisfies some angular polynomial identity. The angular polynomial identity is, as in the case of Lie algebras. It satisfies an identity of this form, which is linear in x1 and in some high degree of x2. And it starts with x1, so you have here a non-zero coefficient. Another condition is this variety doesn't contain the algebra of 2 by 2 triangular matrices. The variety satisfies a polynomial identities in two variables, which is linear in x1, something similar to this, but it's not necessary to have this one with coefficient non-zero. The variety is linear potent, which satisfies such a condition. You have that the algebras of constants of all Weissenberg derivations for all size d are not finitely generated. Of course, it is a non-zero derivation. And it's enough to have only one derivation which is non-zero and only one dimension. Then you have that the algebraic invariance of the diagonal group, which is the one-dimensional torus, is finitely generated. That you have some other condition concerning the rational action of SL2 on the d-dimensional vector space for some explicit d. And also you have something about the commutator ideal. You have in the language of transcendence degree, so you have 14 conditions for this. These conditions, they are due to many people here. You have Latishev, you have Lvov, you have Viktor Markov, you have Herlompovich Sapir. They wrote a very nice survey article, which is on logic, but also contains a remark about this. Also, there is some of this is due to Kemmer. A stronger version of result of Kemmer is due to Zelmanov. Also, there is a result by Vonesen. And we had this with Matish Domokosh, one more condition. We had something with Gupta, with Kanta Gupta. And some of the last two conditions, they are due to Bidrachuk, in a joint paper with Bidrachuk, which is still in process of writing. You have also several survey articles by Formanek, by me, and Herlompovich Sapir, when you have all these things. So here, these are the references. So there are 14 papers, I think. Okay, thank you very much.
Thank you very much for the interesting talk. Do we have any questions or comments, remarks?
Vesselin, when you have a locally nilpotent derivation in three-dimensional case on polynomial algebra in three variables, the kernel is actually polynomial ring in two variables. That's some theorem by Mianish.
Yeah, I know.
Oh, okay. You just didn't
I simply decided not to.
Yeah, you didn't mention it. Yeah. Okay.
Yeah. I mentioned your name there.
Yes. Many times.
But you didn't mention the result.
Yeah. Okay.
So, for example, you have the description of the automorphisms which fix this element which fix by the in the Nagata automorphism.
More questions or comments? Okay, if not, let's thank the speaker again. And we'll have a 9-minute break now.
Good afternoon, everyone. I think it's time to get started with our final session for the evening. So our next speaker is Codebel Fidelis Bezzera, who is going to talk about Z-graded identities on the Grassmann algebra and arithmetic tools. So the floor is yours.
Okay, I can start. Okay.
Yeah.
Okay. Good morning, good afternoon, good evening, everyone. First of all, I'd like to thank the committee, in special the Professor Flamenco for the invitation to participate in this Congress in honor of Professor Drensky's birthday. Congratulations, Professor Drensky, and I'm so happy to be here. Okay, my total title of my talk is The Great Identity on Grassmann Algebra and Arithmetic Tools. To kick off, the purpose of this talk are to provide robust information concerning the code 2 and 3 induces the gradient on Grassmann algebra, whose support of this extra tool to coincide with a subgroup of Z. And the second one, to describe the grade identity for each of them. At the end in this talk, we will note an interesting connection between elementary number theory and PI theory. This is trying to work with Alan Guimarães, Flamenco and Antônio Brandão. Okay, let's begin by a look at our work environment. The Grassmann algebra is the algebra generated by vector space L, whose the base is formed by A1, A2, A go ahead, such that the multiplication in this algebra is induced by this relationship. It's well known that this set is a base for Grassmann algebra. Hence, we have this decomposition for Grassmann algebra in two subspaces. E0 is the subspace generated by 1 and our monomial with EVK, and A1 is the subspace generated by some well-known bits and pieces about the Grassmann algebra. One can view Grassmann algebra as a constant of the tensor algebra L. This comes from elementary linear algebra. The disadvantage of this definition, it depends on the characteristic, sorry, 1 minute. Okay, 1 minute. Sorry, my son, sorry. Okay, the disadvantage of this definition is dependent on the characteristic of ground field. It's well known the subspace A0 is equal to the center of the algebra, and the A1 is the anti-commuting part of Grassmann algebra. The Grassmann algebra is the most natural example of superalgebra. Here, superalgebra means Z2 grading on Z2 grade algebra. It's not only important for PI algebra, but it's very important in algebra in general, geometry, analysis, and physics. Okay, in this talk, we consider the group G is a abelian group. This symbol is the free associative algebra generated by this set. This algebra has a natural grading by group G, where the homogeneous component of degree G is the subspace generated by this monom, okay? So that the multiplication between J1 and 2Jn is equal G. An element in this algebra is called graded polynomial, and this element in this symbol, it's assumed that this set and tuple satisfy this, okay? Set and tuple is called an NF admissible substitution. Associative algebra. And the grade identity, the grade polynomial identity for A is the polynomial in the free algebra that satisfies this equality, okay, for every F admissible substitution. The set format for all grade identity of A is called TG ideal of A. In particular, if J is trivial group, we will call the definition of ordinary polynomial identity. Okay. In this talk, we consider only homogeneous grading on Grassmann algebra. Such grading is on Roos basis of vector space L is formed just by homogeneous elements. Such grading have been studied by many authors. In the ordinary case, you can see the Grassmann algebra is PI algebra. It satisfies these identities. Over infinite field of characteristics different from two, Kraskowski and Hegel in 1973 and Latchev in 1963 obtain a basis of PIs of Grassmann algebra. When the ground field is infinite, it is necessary to include one more identity in the base. See Backward and Hank in 2011. Okay. To conclude the preliminary part of my talk, we must consider the grade identity. For n prime p, the grade identity for the Grassmann algebra by the group ZP were studied by DiVincenzo and Da Silva in 2019, Centron in 2011, and Fonseca in 2018. In these first three works, the author considers P equal 2. For any old prime, we can mention the works done by DiVincenzo, Koshelkov, and Da Silva in 2017, and Guimarães, Dias, and myself in this year. Okay, moving on the other groups, we consider two works. Centron in 2016 described the homogeneous grading on Grassmann algebra by finite abelian groups under additional conditions. And Guimarães in 2020 already investigated grading and graded identity by the additive group of the real number. This work is very interesting because the author started a study on grading by groups that may even be non-enumerable. Okay, now let's have a look at the Z grading on Grassmann algebra. I'm not sure if you know this, but the idea is very similar as Z2 grading, but the sum run in integer numbers. First of all, I begin attribution of degree of the generators in the following way. In the first grading, denoted by AK, the generator has degree 0 if I equal 1 until k, or 1 otherwise. The second one, the degree, the generator have degree 1 if I is equal 1 until k, or 0 otherwise. And the last one, denoted by this, the generator has degree 0 for I even, or 1 otherwise. This provides three types grading by the group Z on Grassmann algebra. Guimarães and Koshelkov in 2021 studied this grading and describe the basis of the grade polynomial identity of each of them. It's clean. There are more ZX22 than this last one. For example, this. But this example is not interesting for me because it is very similar to the previous one. So there exists a general way to construct some grading on Grassmann algebra by the group Z. In this slide, we'll define the so-called I-induced disagreement. For this, fix this symbol for natural number and this symbol for natural number union 0. For some natural number R, we get R internumber and R symbol that can be natural number or infinite symbol. In this condition, we can consider a decomposition of vector space L in this way, such that satisfy this equality, okay? What can draw your attention that your grading are homogeneous. Thereby, we split the generator of vector space L in the following way. The degree of the generator is Nj if and only if this is occur. And we extend the degree of our monomial in Grassmann algebra in this way. As you can see, it provides us X2 of the gradient on Grassmann algebra, denoted by this, and it's called R-induced disagrading. Finally, the support of this grading, denoted by this, is the collection of all elements of the whose homogeneous component is non-zero. Okay, here we consider two cases, I equal 2 and A equal 3. For A equal 2, we consider this question. What are the conditions on the index M, N, U, and V for support to be a subgroup of Z? Certain answer was obtained using elementary number theory. It was obtained by Guimarães, Brandão, and myself last year. In this condition, the support of this grading is the Z if and only if U equal V equal infinity symbol, M and N have opposite sign, and GCD between M and N equal D. In this talk, we consider D equal 1. That is, the grading has full support. Okay, have a look at the grading identity in this case, okay? For this, we consider two TZ ideal. The first one is the TZ ideal generated by this polynomial, when the degree of this variable is arbitrary. And the second one is the TZ ideal generated by these two polynomials. The first one is the commutative between x1 and x2, where one of them has degree even, or otherwise the polynomial x1, x2 plus x2, x1. With a field of characteristic 0, it's possible to show this table, okay? As you can see, if the product between M and N is even, the X structure has the TZ ideal equal I1. Otherwise, A is equal I2. Okay, not in this table, an interesting connection between elementary number theory and PI theory. Okay, there is one more thing I'd like to talk about. Let's change for the case I equal 3 and look at where we can improve. The question is very similar, but the answer and the description of a base are all of them grade identity for such X22 are a bit more complicated than two induced. The answer in this question in this slide, okay? In this part, the characterization on three induced was obtained by Guimarães, Kushilkov, and myself in this year. In this case, the support of this grading is the Z if and only if A and C have opposite sign. The K1 and K2 is infinite symbol, and we can see two cases. The first one, this X2, this two induced X2 is equal to Z, or otherwise B is not in this support, but K2 is more or equal than the line -1. Here, the line is GCD between A and C. As in the previous case, we consider D equal 1, okay? Moving on grade identity, we define the TZ ideal denoted by PK, generated by 6 polynomials. Pay attention that the definition of this TZ ideal depends on K. If K is even, we consider only polynomial 2, and K is odd, only polynomial 3. Here, the variables as Z have degree odd, Y have degree even, and X have arbitrary degree. Okay. Using techniques similar to the two induced, it's possible to obtain the following incomplete table, okay? Note that the last two cases are not yet obtained. But we need two more results. The next results are motivated by the grade identity described by Dipichenko, Kushilkov, and Da Silva by the group ZP. The first guy is this. The product between these elements is even, and the other guy is this. The product between these elements, this number, this natural number is odd. Okay. We can draw relation to this symbol. Okay, this symbol here, here, in the previous guy, here. In this case, we have the use of elementary number. Okay. Thereby, we have the complete table in this case. Okay. So let's conclude my presentation. I will write some additional comments. First one, the description of an induced whose support is a subgroup of Z and their grade identity respectively is reduced to two things. The first one, the problem of the description of grade identity on Grassmann algebra by affinity cycle group, and the second one, the usage of techniques derived from number theory. Okay, the second comment is there are other Z grade on Grassmann algebra different from I induced, whose support is a subgroup of Z. In the last one, the general case is still open. However, we are investigating the problem when the ground field is infinite or when the support is not full. The next slide will main reference. The first one, we got the description of the two induced. The second one, the three induced. The third one, we are getting similar results. Organize this paper to present to a special issue dedicated by this event. This is my job. Thank you so much.
Thank you. Thank you. Are there any questions, comments? I do not see anything, and I don't see anything in the chat. So let's thank the speaker again. And we're going to continue in 9 minutes. So thank you.
All right. יש עוד שתי הרצאות קצרות ונגמר הכנס. 8:05. אז אפשר ללכת לים, למצדה הזאת של זאת. טוב. ואם צריך להזמין. ואם הם רוצים שנזמין. כן. לא, יום שישי יכול להיות לחץ. יום שישי יכול להיות לחץ. עומס, עומס. טוב. כן, כן.
Eli, you have the mic on. Eli. Your mic is on.
Wow.
So we heard all of it. But it was in Hebrew, so we didn't understand.
So shall we look for Irina?
Yeah, I cannot see her.
Hi, Michelle.
Unmute your microphone, Michelle. Unmute the microphone and we will listen to you. Your microphone off.
Michelle? Your mic is off.
Yes, I know. But you were complaining to Eli that his mic was on, so you have to make up your mind. Hi, Vesselin.
Hi.
Oh, nice to see you, huh?
Yeah.
Yes, it's very nice. Vesselin Lise wants to give you her wishes.
Okay. Bonjour, comment vas-tu? Bien. Michel, I remember that when your boy was small, you had the same frequency as the baby in the next door. So when the baby in the other door started to cry, you thought that this is Lulu.
Yes. I was trying to remember when we first met. I don't remember the year, but I remember the circumstances. Kanta had invited you.
Yes.
Then she contacted me and said, maybe I would be interested, and I was, but I had the impression she wanted to get rid of you for the holidays, end of the year. So I checked with Lisa and she said, this is fine, he can come. We don't mind.
But the official version was that in that time I wrote you about some of my results. Since I had a paper in French, I wrote the piece in French. So, and when I were in your office, and you were out of the office, and I had to answer in French the telephone calls of all your friends and relatives. Okay, maybe it's time for the next speaker.
Okay, so I'll mute my phone.
We're still waiting for the next speaker, so maybe we'll have a couple of minutes more to see if Irina.
She's already here.
She's
Sorry,
already,
I had a problem. Just the most inappropriate time, but I hope it's okay now. How can I?
Okay, our next speaker then is Irina Sviridova, who is going to tell us about Hooke theorem for various types of identities. I believe you should be able to share now your screen.
I'm trying.
Nice.
Okay, we see it now, yes.
Is it possible to see?
Yes, just if you can maximize
sorry,
it.
I'm sorry, but it's... Is that?
Yeah, so just if you can maximize the screen with Control L, and it would be perfect. So the floor is yours, please.
Is it? Is it? Oh. Something wrong.
Ира, можно сделать чело?
It's better not to touch. Just
Okay.
to leave. Like it now because I have already okay. Is it possible to see and to hear me?
Yes, it is. Yes, it is.
Okay. I'm really very grateful for organizer to give me this opportunity to participate in this conference. I'm sorry with this really technical problem in my computer. So just Several words about Vesselin because I can say nothing. Vesselin was really the first famous mathematician for me, young person, 25 years ago when I participated my first international conference, and he was really just, I mean, the first famous mathematician after my university professors, but I was really very charming of him, of his personality, and until now I just fashion of him. And he's a very nice person and really perfect mathematician. And one of the particularity of him is his very wide interest in mathematics. I will speak in some probably early interest of him. I'm not sure that he is yet interested in this theme, but I know that he started just to promote this stream of research. But I will speak about polynomial identities, and especially the object and the theme of my talk will be purely combinatorial. As a result, really is purely combinatorial, just like the proof that we use is also purely combinatorial. In this sense, this talk I think is more appropriated for this conference from in our books. And this is the joint work with my doctoral student, Renata Alves da Silva. We consider PI-algebra. I'm sorry, I will waste some minutes for some boring definition. This will be absolutely boring part probably for a majority of audience. But what to do? I think I need to give some definitions nevertheless. Well, we consider PI-algebras, and we are inside the classical situation. We deal with the associative algebras or the field of zero characteristic, and as usual, just we define free associative algebra generated by infinite set F, and just the element of free associative algebra, associative polynomial, is called polynomial identity if it vanishes in any evaluation of the algebra A. In this case, if algebra satisfies some non-trivial polynomial identity, it's called PI algebra. And it's natural to consider the set of all identities for some fixed algebra, just we will denote it by it A. And it's well known that this T ideal of the free associative algebra, just the ideal closed under all endomorphisms, just the free algebra. And usually when we relating with identities, there are some just more objects connected with considering. If you have PI algebra, we have the ideal of identities of its PI algebra, which is T ideal of a relatively free algebra. We have a variety, which is a class of all associative algebras satisfying these identities. And we can consider clear the relatively free algebra of this variety, and this can be obtained as a quotient of the free algebra with respect to this T ideal. And it's well known absolutely that if the field is of the zero characteristic, then identities is completely defined by multilinear identity. That's why in our case, there is a sense considered only multilinear identities of our algebra. And in this case, what is advantages? Advantages that we can apply representations of symmetric group for this case, and it's very natural. We consider multilinear polynomials of degree n, and it n will be multilinear identities of degree n of algebra A, and P on A is a cospace of this space of identities of multilinear identities, multilinear part of the relatively free algebra. And so this must be, yeah, relatively free algebra of degree n. Well, and usually when we have some n object here, the variables we can act by permutations on them, and here action is natural. It permutes variables of our multilinear polynomial, and this action naturally induced the structure of left SN representations on these two spaces, on the spaces of multilinear identities and on spaces of the on the multilinear part of relative free algebra. Usually, we consider the core space Pn of A because it's much less than identities. It's well known that's a dimension of the space of multilinear polynomial associated case is Factorial, and the dimension of identities of multilinear identities is approximately the same. Synthetically, it's the same. And contrary, the dimension of the core space of Pn of A is much less than a factorial. Really, it's exponentially bound. And for us, it will be a crucial result. Really, the fundamental key, or just a fundamental stone on which based all things that we'll consider. Well, and when we have SN representation, in the case of characteristic zero, we have as a tool all representation theory of the symmetric group. In this case, characteristic zero, all modules are completely decomposable. And here we have multiplicities, and P lambda is denoted by irreducible left representations with the character, irreducible character K lambda. And lambda, just all irreducible representations are up to isomorphism corresponding to partitions of the N. It's well-known results, and just I put here the character of this representation of the Pn of A. Just recall that this is a multilinear part of relative free algebra of algebra A. It's called the character is called and co-character because it's a appropriate instrument just to discuss the behavior, in general, asymptotic behavior of a module in this case. Well, and just a bit what how really we connected, how really we obtain identities, yes, and not identities. Because in Pn of A, we have really just polynomials which survive after applying all identities. So if we have lambda, just to any partition, we correspond the Young diagram. Here, I will denote as usual h of lambda, the height of the diagram, just the number of parts of partition. And the irreducible module can be done by this way, where T lambda is a Young tableau shaped lambda, and for any Young tableau, just we correspond to subgroups of symmetric group. This is a group of which acts on columns, column stabilizer, and the groups which acts on rows, row stabilizer. And having these groups, we just obtain the idempotence. It's quasi-idempotent of a group algebra of symmetric group, and we obtain really the polynomials which generate as left as modules irreducible irreducible representations. So it's really the images of identities, not identities, the bricks of our theory, which is used to study identities and which to study identities. Well, it's the combinatorial thing here. The combinatorial feature feature of this is that FT lambda is purely symmetrical variables with a number of the same row. And from our side, it's not very difficult to see that this model also can be generated as a can be generated by some polynomial which alternates on variables which are involved. And this is really the reason which we use the effort which we use to prove our results. And our results really just are going to discuss here the generalization of very classical, very famous and very known result, which is called Hooke's theorem. It was, as far as I know, due to Amiso and Vega, firstly, in classical case for polynomial identities. For any associative algebras, there exist integers, non-negative integers d and l, such that character belies to the infinite hook of this measure d and l. What is this infinite hook of shape dl? It's just the union of all diagrams of this form, and the factor character just inside this hook means exactly that for any lambda which is outside of this hook, any polynomial which corresponds to this Young tableau, to this of this shape, will be identity of our algebra. Just so can survive only things that are inside this hook. And as a consequence, detalization of this theorem, we can consider street theorem. Really, I put here some equivalent conditions, and these equivalents are due to different authors. And just there's the list of authors here. That's why. And if you have a variety of associative algebras in the field of characteristic zero, the following conditions are equivalent. The variety is generated by some finite dimensional algebra, just all identities defined by some finite dimensional algebra, or by some finitely generated PI algebra. Our variety of algebra satisfies some Capelli identity, and the characters belong to the strip. It's the height of all diagrams which is not disappear is less or equal than k for some k natural. Really, this is the same k that is here, the order of Capelli. It's not difficult to observe this combinatorial effect. I recall what I mean to say Capelli polynomial. It's a polynomial which is multilinear polynomial which is alternating on one collection of variables of length k. Well, and as a corollary, we have also very famous theory, classical theorems that also were used in polynomial identities theory. There are some in other applications really. So-called Hamisu theorem. That states that any associative PI algebra in characteristic zero satisfies some degree of the standard identity. Standard identity is really just the collection of alternating variables. And this theorem is exact corollary of the strip of the Hooke theorem. Really. Just it's immediate. It's consequence, not so immediate, but it's consequence of this Hooke theorem. In particular, any finite dimensional, finitely generated PI algebra satisfies standard identity. Here, the degree m equal 1. But some other applications of all this stuff is one of them more famous is the Kemmer super trick. It used to prove that any variety is generated by the Grassmann. The principal idea of this trick how we obtain really and where from we obtain the Grassmann envelope of finely generated PI algebra, how we restrict the number of generators of relatively free algebra of our variety. It's exactly due to the form of the hook. It's exactly because we have the Hooke theorem. Really, the Hooke theorem also used in other theorems of PMers, just in representability theory, but I won't touch this theme here. In other consequences, break consequences of the Hooke theorem, it's a growth theory, which study the connection between characteristics of structure parameters of algebras, properties of them, identities, and numerical characteristics of ideas such as codimension, which is dimension of our Pn of A, co-length, which is sum of multiplicity, behavior of multiplicity, and so on. And really, all this growth theory, this grows from Hooke theorem. It's used essentially Hooke theorem, especially at least to have upper bound, as far as I know, just the unique effective way to obtain some upper bound to asymptotic behaviors, such things. It's just considered shape of diagram, which provides the Hooke theorem. Well, really, Hooke theorem has a lot of other applications, and I will recall also that the key result to prove the Hooke theorem, and just probably the key reason that the Hooke theorem exists is true. It's this fact that the dimension of the relatively free codimension of the PI algebra are exponentially bounded. It's a famous Righet theorem, and it's also really the combinatorial fact, because this evaluation appears because if algebra A satisfies some multilinear identity of degree D, then this identity provides some type of slight commutativity, which permit to bound to restrict the number of monomials which participate on the base of this space. And what is really very interesting, in classical case, it's known, everything of it is known for a lot of years. And what is really very interesting, what happens when we add some additional structures to our PI algebra. And some type of additional structures which are very popular, not only for in PI theory, but in general in mathematics, not only in algebra, but just grading. I consider it's clear we can consider grading by semigroups and other some type gradings, but I consider grading by group. Just we can consider group graded algebra. We can consider an algebra with the action of the Hopf algebra with some restriction without that. We can consider an involution on our algebra, which is anti-automorphism of the second order. And if we have zeta-graded algebra, as called super-associative algebra, then we can also consider naturally super-involution on the superalgebra and a graded evolution. Graded evolution is not so interesting, really, just more natural object from the physical point of view as a superevolution, but nevertheless, graded evolution. It also appears in very interesting points, and it's worth to study. It's interesting to see that with respect to this theory, it behaves exactly the same way with superinvolution, just almost there is no difference. Well, we can consider identities, we can define identities and all these things by two different ways. Just it can be defined by actions, some way, and I will omit rapidly because it will be our approach. And we have another approach, and really our action of our additional structure is really defined as an action of some group, some subgroup of the group of invertible linear operators of our algebra. And that's why we can consider really just usually and in our cases, we have the complete decomposition of our algebra as a sum of eigenspaces. And we can consider this structure to define really the notion of identities and to define, I think, the structure which is combinatorially much more convenient than when we have the action. Well, what we do in this case, we really just divide the set of variables, the generators of our free algebra, by disjoint set. For graded, for the grading, it's just the graded variables. For involution, it's symmetric and skew-symmetric variables, and for super-involution and graded involution, it's symmetric, skew-symmetric, odd, and even variables. And what is the identities in this case, graded or star graded identities? It's just we consider a polynomial of free associative algebra and its identity, graded star identity of our type. For our algebra, if it vanishes in any evaluation which respects the type of our variables, and this must be respected. Well, in graded case, in this case, we reduce to study to the multilinear polynomials of degree NE on any type of variables. In the case of graded identities case, just the order of the group. Involutional super identities k val is equal to 2, and in the case super involution, graded involution, we have 4 types of variables. And in this case, we just define what is the multilinear identities, what is the cospace, what is the corresponding relatively multilinear part of relatively free algebra. And in this case, it's very nicely just we have that both of these objects, they have a natural structure of the left FSN model of the direct product of corresponding symmetric groups. They act independently by permuting corresponding type of variables. It's very natural action and very natural structure. And we can consider character, and as we inside the zero characteristic polar field, we have the same situation as for classical case. We have completely decomposable character. Here, the irreducible character is corresponds to multi-partition, tuple partitions, and we can define multi-hook corresponding just any hook to any type of identities, to any partition. And then we have the next theorem, that's the previous results of the one of the participants of this conference. The first one was after the classical result, the result of Antonio Giambrone and Amitai Regev for Z2 graded super identities and identities with involution. We have a hook theorem in the natural way. Then by Alan Berry proved this theorem in the case of the action of the Hopf algebra, finite dimensional Hopf algebra and algebra A. We also in this case have hook theorem and have an out of exponentially bound for codimensions. And as a consequence of this theorem, for a case of algebraic closed field and when G is a finite group, we can obtain that the hook theorem also holds for graded identities. And just to finalize, I think I must finalize already. Yeah, I'm sorry. Just this the last slide. Our results we recently obtained with my doctoral student. This result for identities with the same result, the hook theorem for identities with super involution, and graded involution. As a consequence, we also obtained the analog of Amitzur theorem. Here is interesting that here we have the product of degree of standard polynomials, which depends, any polynomial depends on the proper type of variables. They separate, they just, usually it's not simple to distinguish them. Well, that's all I want to present here. Thank you a lot, and happy birthday, Vesselin.
Thank you. Thank you very much for the talk. Are there any questions or comments? It was a great talk. Thanks. Okay.
I guess I have a question.
Yep, please.
You talked about using the standard identity for hooks. So in Amitzur-Regev, they have these polynomials called Amitzur-Regev polynomials, I guess, to determine.
Yeah.
Do you do such a thing also?
Yeah, it's really, you see, this is one of the interconnections that many others just I mentioned as some consequence, but really it's not consequence, it's some equivalent statement really. And I'm sure that, it's combinatorial fact probably, but usually it's not so trivial to prove, but it must be true that all these algebras, all these varieties satisfy some type of theorem. They must have some type of Amitzur polynomial, Amitzur identity. And it must be reasonable. It must be looks like in a natural way, I think, but usually it's not simple to prove, especially if you have no classification theorems. And combinatorics there, because when you have a hook, and these Amitzur polynomials, they just, I worked with him, but for some special varieties, for example, for prime varieties, and it's interesting. It has really great combinatorics, and the one polynomial that exactly kill all box or just rectangle, and but it's not simple just to work with him to prove that our satisfy such type of identity. But it must be true, and probably it can be done using the hook theorems. I think it's possible just to do, but it's not immediate. It's clear that it's connected, but the combinatorics there, it's in general case is not trivial.
Thank you. Any other questions or comments? Okay, so let's thank Irina again. And we can maybe just take a couple of minutes before we start with the next and final for the evening talk. All right, so our final speaker tonight would be Michel Racine. I think you should be able to share at this point.
Is everything okay?
Yep, great. It looks great. So he's going to tell us about the derivation algebras of algebras over a ring. So please.
First, I would like to thank the organizers for giving me this opportunity to offer my best wishes to Vesselin. Many healthy years. What is new in the talk is joint work with Holger Petersen and Skip Garibaldi. Let me start with a bit of history. Jordan algebras were introduced by a German mathematician, Pascual Jordan, who was an assistant of Hilbert when Hilbert was interested in mathematical physics. And observables in quantum mechanics were self-adjoint operators on the Hilbert space, and Jordan was trying to axiomatize this. And so he gave the following axioms over a field of characteristic not to. So you have a unital algebra, an element 1, which acts as a unit. The algebra is commutative, and you have a third axiom, which to me was never particularly informative. More interesting are the examples. If you have an associative algebra and you want a commutative product, well, you take the average of the two ways you can multiply two elements, and you get a linear Jordan algebra, which we denote A+. If A has an involution, then the symmetric elements are a Jordan subalgebra of A+. And a third example, when you have a vector space with a quadratic form, and you take its Clifford algebra, then of course you have a Jordan algebra CVQ+. And it's easy to check that the beginning of the decomposition of the Clifford algebra, namely the field times 1 direct sum the vector space, is actually a linear Jordan subalgebra of CVQ+. Now, Jordan subalgebras of an associative algebra, the plus algebra of an associative algebra, is said to be special, and otherwise J would be said to be exceptional. The first real result in the field is a theorem of Jordan, von Neumann, and Wigner. If you take a finite dimensional linear algebra, which is formally real, all this over the reals. By formally real, I mean that if you have a sum of squares which is equal to 0, it must be the trivial sum of, 0 squared plus 0 squared and so on. And this is true if and only if J is isomorphic to one of the followings. JVQ for Q in an isotropic quadratic form on a finite dimensional vector space V. The symmetric elements of Dn, where D is a composition division algebra over the reals, and these are exactly the reals, the complexes, or the Hamiltonian quaternions. Composition algebras have an involution, a distinguished involution bar, such that the symmetric elements are exactly the field times the unit element. And here star is just the bar transpose involution. And finally, a third algebra, the symmetric elements of C, where C is the Graves-Cayley division octonion algebra. Now, Jordan von Neumann and Wigner asked Albert, is this last algebra, is it really Jordan? I mean, it came up in the classification, but they couldn't show it was Jordan. And is it exceptional? And Albert answered yes to both questions. And Albert's paper was published immediately after the paper by Jordan von Neumann and Wigner in the Annals in 1934. Now, Vesselin told us about derivations, and so it's, for me, an endomorphism of J, which satisfy the Leibniz rule. And Schwelle and Schaefer proved that if F is algebraically closed of characteristic 0, and J is the symmetric elements of 3 by 3 octonionic matrices, here, because the field is algebraically closed, C must be split. Then the derivation algebra is a simple Lie algebra of type F4. Now, we would like to do the same thing over a ring, but what if the base ring doesn't contain a half? In the second half of the 60s and the beginning of the 70s, McCrimmon laid the foundation for what I will call Jordan algebras, but strictly speaking, I probably should call them quadratic Jordan algebras. So if we've got a unital commutative associative ring and a K-module J with a quadratic map U, which sends J into the endomorphisms over K, and the distinguished element, all my algebras will be unital except Lie algebras, of course. If we linearize this U and note that at the end here, I have two ways of expressing it. The V will come in handy. Then JVU is a unital Jordan algebra if for all x and y's these three axioms hold. U of the identity is the identity map. The second axiom is the so-called fundamental formula. And the third axiom, again, is not informative unless you start working with this. And this should hold for all scalar extensions. Now, examples. The first is if you do have the half, then you can show that any linear Jordan algebra can be given a Jordan algebra structure, and conversely. So these Jordan algebras do not give you anything new. I mean, they coincide when the half is in the base ring. If you have an associative algebra, then UAB, defined to be ABA, endows A with a Jordan algebra structure, which I'll again denote A+. And in that case, the VABC is just ABC plus CBA. And another example is the split Albert algebra, HC3, where C is the Zorn algebra of the ring K. So these are, I think, at one point, these over fields were called Zorn vector matrices here. K is the base ring, and M is since we're in the split case, a free K module of rank 3. And there, it has a multiplication which uses both the dot product and the cross product. Now, what should derivations be in that case? An endomorphism will be a derivation if, for all x, d commutes with the, well, the commutator of d with the u operator is u dx comma x, and d annihilates the identity. This may seem to you a strange definition. The connection is with isotopes, and I don't really have time to talk about isotopes. The derivations are the Lie algebra of the automorphism group, and it's another way to define a derivation in the quadratic context would be to say it's you look at the Lie algebra of the structure group and insist that it should map the identity to 0. Now, if 2 is a unit of K, the two definitions of derivations coincide. Another key property is that the derivation algebra is invariant under faithfully flat base change. That is, the derivation of, if you've got a faithfully flat extension R of K, the derivation of J tensor R is isomorphic or canonically isomorphic to the derivation of J tensor R. Now, I will not define Albert algebras. They're defined by looking at cubic algebras and imposing some non-degeneracy conditions. For the experts, this more or less follows along the lines of McCrimmon's papers on Springer, Freudenthal, Titz algebras. Now, rather than defining it, I will give the key property for what I want to do of Albert algebras is that any Albert algebra over K can be split by a faithfully flat extension. Now, excuse me. Rowan yesterday talked about first decompositions, and this is what we want to do. So for a split, because you can split it and because derivation algebras are invariant under base faithfully flat base change, we look at such matrices, and the first decomposition in this case coincides with this decomposition of J, where you've got the base ring times the 3 diagonal idempotents. So you've got rank 1 modules, and then you've got the off diagonal elements. And I've chosen to write the indices J12, J23, and J31, but there is nothing wrong with writing J21 and 32 and 13. And so I will write that in general for distinct i's and j's, Jij is just Cij, where C is in the composition algebra C. So here the split composition algebra C. What the following proposition says is, in terms of Alberto El Duque's talk earlier today, is that the derivation algebra of a split Albert algebra has a group grading by the dihedral group. So what does one do? You take an arbitrary derivation and you look at where does it map the idempotence, and what conditions must these, their consistency conditions that must be met. So what you do is you produce 3 copies of the composition algebra, which give you J1, J2, and J3, and subtracting that part, you're left with a derivation that annihilates the idempotence. So these we call G0. The proposition says that this is a direct sum. G0 is a Lie subalgebra of the derivation algebra G, and the GIs are G0 modules. The GIs for I greater than 0 are isomorphic to C as a K module, so they're of rank 8. We would like to say more about G0. So for a derivation in G0 and any pair ij and a third index L such that ijL is equal as a set to 1, 2, 3, there exists a unique dij, which is an element of the orthogonal Lie algebra of the norm of C, such that the action of D on Aij, I probably should have said that since D annihilates the idempotence, it fixes the off-diagonal first spaces, that this is given by Dij of A square bracket ij. Now, these Dij's satisfy Dji is equal to Dij bar. In other words, you act on Dij on an element in the ij, and then you bar. This is just to allow us to use ij and ji, whatever suits us. And the condition 3 here, the D, say IL of a product, this is the product in C, is actually equal to Dij of A times B plus A times Djl of B. This is usually called local triality. And if it works for fixed IJL, namely if 2 holds and 3 holds, then 3 will hold for any equation that you obtain by letting the symmetric group act on the indices in 3. So what we have now is a map which maps G0 to the orthogonal Lie algebra of the norm form. Before I say more about this map, I should point out that the converse is true, namely that we have a split Albert algebra, and if we're given Dij's for distinct pairs in 1, 2, 3, which satisfy 2 and 3, then the linear map defined by mapping the diagonal idempotence to 0 and acting on elements of the form Aij by Dij is a derivation of J contained in G0. In other words, the 2 properties, 2 and 3, are enough to guarantee, with, of course, the fact that the Eij's are annihilated, that this is a derivation. Now, if we look at the map which sends G0 to the orthogonal Lie algebra of the norm form. In fact, there are 3 such maps, but let's fix an index and look at this map. So this is the map that we've been talking about in the previous 2 slides. Well, it has a kernel, unfortunately. If it didn't have a kernel, we would have had an injection of G0 in O and C. And the kernel is all elements of the form V, U, EJ, 1, the unit element of the Jordan algebra, and with U in the 2 torsion part of K. So a consequence is that pi will be injective if and only if K has no 2 torsion. And in that case, any element of the triple DIL, DLJ, DJI determines the other 2 uniquely. From this, we can easily get the following corollary, that for any octonian algebra over K without 2 torsion, then if we're given an element of the Lie algebra of the norm form, there exists unique automorphisms phi1 and phi2 of the Lie algebra such that E of the product of AB, A and B being elements in C, is equal to E phi1 of A times B plus A E phi2 of B. And this holds for cyclic permutations of E, E phi1, E phi2. Let me say that if you are interested in what happens when there is 2 torsion, or in particular in characteristic 2, Alberto El Duque has a paper on triality about 20 years ago, where he does an excellent job with characteristic 2. Now, if 2 is a unit, not only is there no 2 torsion so that pi j is injective, but it is also surjective and therefore bijective. So if 2 is a unit, then we have an isomorphism between G0 and the orthogonal Lie algebra of NC. This needs not be true even if K has no 2 torsion. For example, it's not true for the integers. And if there is no 2 torsion, you can use what has gone on before to show that Drj is a Lie algebra of rank 52. One reason to study this was the theorem of Chevalier and Schaefer that I quoted at the beginning. This, of course, had been extended to other fields, not necessarily algebraically closed. So in our context, we have that if J is a split Albert algebra over K and K has no 2 torsion, you don't need that 2 be a unit. Then G or Drj is a split Lie algebra of type F4. What do I mean by that? Well, you have a root decomposition with multiplication, which in another context one would call a Chevalier basis. And as a corollary, we obtained that if J is an Albert algebra over an arbitrary ring with no 2 torsion, then the automorphism group is smooth. There's a smooth K-group scheme, and its Lie algebra is of type D4. Now, I did not say this correctly. the fact that the automorphism group of J is a smooth K group scheme, that has nothing to do with what came before, but it's what allows us to, what came before is what allows us to make the last part of this corollary true. In fact, in my last slide, the following result for fields was obtained by Beauregard, Lowes, and Martin. And it says that if J is an Albert algebra over a field, then the derivation algebra is a simple Lie algebra if F is of characteristic not 2, but has an ideal of dimension 26 if F is of characteristic 2. And the result about the smoothness of the group scheme it can be found in this paper. Now, we also examine what happens in the case of two torsion, but you can't, this theorem tells you 2 is going to be playing a very, 2 plays the role for Jordan algebras that 3 plays for alternative algebras. And you expect this kind of thing to happen, and it does. I don't want to go over time, and therefore I will not say any more. Since I think I have still a minute or two.
Yes, you have, yeah.
Thank you. Since I'm the last speaker, then I would like to take this opportunity to thank the organizers for a very successful conference organized under rather large constraints of time zones, geography. But of course, for this, Vesselin is to blame, because wherever he went, he made friends, and he made sure he kept them. So he has friends all over the world. My only complaint is that, and it's not about this conference, is that these Zoom meetings haven't managed to have Zoom banquets. So I'll do the best I can under the circumstances. Here's to your help, Vesselin. Santé.
Thank you.
Thank you. Thank you very much. I think we all are extremely grateful to the organizers, to Pavel Koshukov and Ivan Shipchakov and Eliza for setting up the event. Are there any questions for the talk?
Yes, I would like to ask a very short question concerning this map pi j.
Yes.
Michel, good to
Yes.
see you, by the way. You said if you're working with the integers, pi j is not surjective.
Yes.
Do you know what the image is? Is this a difficult?
No, I should, let me say something for specialists. You see, if 2 is a unit, there are derivations which are especially nice. They're called standard derivations, and their span is an ideal in the Lie algebra of derivations. And if 2 is a unit, then one can show that the derivation algebra is the same as the standard derivation algebra. And the difference between the case where it's not a unit is that you do get the same root spaces. It's in the Cartan subalgebra that something is missing. Not much, but just a little bit.
Okay.
We can talk about it some more, Olga.
Okay, very good. Thank you very much.
That answers your question. I mean, it is not
Absolutely
true that all derivations are in the standard derivation algebra. That's the true answer.
Okay, thank you.
Thank you. Any other questions or comments?
Seth asked whether it's possible to make a picture of all of us. I don't know how to do this.
But not only the names.
Yes.
If we open our the videos, is it possible technically to be made a picture of all of us?
Most probably yes, but the host must provide for everybody to appear, probably very small
Yes, just
pictures of everybody.
yes, not to recognize each other, but to have with all of us.
And then it will be easy to take capture of the screen.
If not, then
Okay, we'll try to make a picture, but then all of you need to turn on their cameras, and our computer specialist here will try to make a picture of everybody that is on Zoom right now. But all of you need to turn on their cameras.
And then from the options, you choose the gallery, so it will show everybody, or almost everybody, probably two screens.
Yeah, this is the problem. He'll try to show everybody. Just wait a bit. And then the people that we are in the room will be on one small picture, all of us. I'll switch the cameras in a second.
Elitsa, try and
Yes, I'm not the one that is doing it. Todor is here and he will do it. I will just let you know at what moment you have to smile to look good in the picture. There are 10 people that are without cameras, so they won't be on the picture. Is that okay? So that we don't have to wait more here. Okay, we'll just include the people that have their cameras on. Do you agree?
Agree.
Switching here the camera so that you can see our room. Може би ние да дойдем по-напред, а?
Шехмус, your camera, Шехмус.
now you can talk.
I'll wait for them.
Okay.
Well,
They won't know.
yeah.
Just say hi. You can raise your hand.
Well, let's let them finish. They're doing something.
Okay, but I just want to show you there's a place to raise your hand.
Yeah. Oh, is that what you do? Those three dots?
Well, that isn't on yours. On mine it is.
Cheese. One more. Okay, cheese.
Here's the chats. This is stuff they've been saying. You could write something in there.
Right. Well, but they're taking a picture now.
Oh, that's what they're doing. But there should be a place where you can raise your hand so they know you want to talk. I don't know where it is on yours.
Is it over?
Okay. So should I still be smiling?
It's over. The picture.
Okay. So I'd like to give the floor to Ivan Chipchakov for a few words now.
Okay, thank you. Dear participants and guests at the conference, dear colleagues, as Shakespeare just said, always ends, that ends, all is well, that ends well.
I did raise a hand if they know.
Nevertheless,
there.
So our conference is also coming to an end. As I noted 4 days ago, it is dedicated so, as I noted 4 days ago, the conference is organized on the occasion of Vesselin's 70th birthday. And now, have the modesty of hoping that it deserves to be dedicated to.
Well, if they let me talk, then I'll say something. Otherwise,
Vesselin.
I'll let it go.
Of course, a good forum, a good mathematics forum needs spectators with good, well-prepared and well-presented talks, as well as it needs an audience of careful understanding and active listeners. Therefore, I would like to thank all participants at our conference, as well as the guests of the conference for their interest in and attention to the work of our sessions. Concerning the hybrid form of the conference, I would like to thank the members of the IT group supporting the conference for their excellent work, which ensured reliable communications during our sessions. Needless to say, the organizing committee appreciates the sponsorship of the Bulgarian National Science Fund. Our thanks are also due to the governmental body and to the members of several units at the Institute of Mathematics and Informatics for their help with various aspects of the conference organization. This, above all, let me wish, on behalf of all of you, let me wish Vesselin sound health, all the best, and further success in his current and forthcoming research. Let me thank, on behalf of the organizing committee, to each participant the same, and let me hope that our research roots will meet us again in future successful and fruitful forums. Thank you again. Thereby I close the conference.
There seems to be a participant who wants to say something.
Yes, it seems that Pat Romanek is this participant.
Yep.
He wishes to say. Please. Please, Professor Romanek.
Ed, switch on your camera.
Аз не знам кой трябва да. Той дига ръка. Може би не знае, че микрофона му е заглушен. Please unmute your microphone if it is muted.
Yeah, also true, yeah.
Ами не, това е дигане на ръка.
Okay.
At your raised hand, if you want to say something, your microphone is off. You should make this on to unmute it.
Well, apparently Ed is confused. Сейчас, Викочка, секунду. Okay, well, everybody is silent. It's Lenny. I just wish Vesselin to visit me again. That was every time his visit is very fruitful, and I will be happy to have you again. Yeah, okay. And with this, I have to leave. My boss, which is my wife, has some plans. Bye. Regards.
Okay, bye.
Hello, do you hear me?
Yes.
Okay, it said Formanak. So I'd like to first explain why my picture isn't there. I guess a lot of you know how poor I am with computers. And I had a computer that had a built-in camera, which I hardly ever used, but the computer died and I got a new one and it didn't have a camera. And I didn't know that. And so we're doing the conference and I'm looking for the camera and there's no camera. But anyway, I'd like to congratulate everyone. For me, it was a conference where I knew almost half the people, which is extremely rare. And also almost all the talks, I knew a little bit of what was going on. And I have one question for the organizers is, will any of the talks be online? Because I missed some of them due to my lack of ability with the computer and also having to get up in the middle of the night. So if there were some online, that would be a big benefit. Anyway, congratulations, Vesselin.
Okay, thank you, Ed.
All videos will be uploaded will be uploaded, and there will be links at the website to the records.
I want to say that we have not seen one very important participant of the supported group of the conference. Please give my best regards to Zhenya for everything she made and is making for you, around you, and for all of us who know her.
Okay. Now she has teaching, so I forward your wishes.
Best wishes to all of you colleagues, and as we say, the end of the conference.
Thank you, the same to you, Czeska. The conference is already closed. Everything which goes on is after conference session. Post conference.
Okay, thank you very much to everyone.
Bye. I'm leaving.
Okay, thank you. Bye.
Bye.
И на самом деле фантастическая конференция. Поздравляю от всей души с днем рождения.
Спасибо, спасибо.
Самое главное в наше время здоровья.
Мой шеф говорил по этому поводу, значит, он сказал бы так: ты главный виновник, а ты не виноват.